Outline of a theory of colors. Si vera nostra, sunt aut falsa erunt talia licet, nostra pervidam defendimus post, fata nostra, puri qui nunc, ludunt nostri judices erunt. Pg Roman 37. Introduction. The desire of knowledge is first stimulated in us when remarkable phenomena attract our attention. In order that this attention be continued, it is necessary that we should feel some interest in exercising it, and thus by degrees, we become better acquainted with the object of our curiosity. During this process of observation, we remark at first only a vast variety, which presses indiscriminately on our view. We are forced to separate to distinguish, and again, to combine, by which means at last a certain order arises, which admits of being surveyed with more or less satisfaction. To accomplish this only in a certain degree in any department requires an unremitting and close application, and we find for this reason that men prefer substituting a general theoretical view or some system of explanation for the facts themselves, instead of taking the trouble to make themselves first acquainted with cases in detail, and then constructing a whole. The attempt to describe and class the phenomena of colors has been only twice made, first by Theophrastus I, and in modern times by P.G. Roman 38 Boyle. The pretensions of the present essay to the third place will hardly be disputed. Our historical survey enters into further details here. We merely observe that in the last century, such a classification was not to be thought of, because Newton had based his hypothesis on a phenomenon exhibited in a complicated and secondary state, and to this, the other cases that forced themselves on the attention were contrived to be referred when they could not be passed over in silence, just as an astronomer would do if from whim he were to place the moon in the center of our system. He would be compelled to make the Earth, Sun, and planets revolve round the lesser body, and be forced to disguise and gloss over the error of his first assumption by ingenious calculations and plausible statements. In our prefatory observations, we assumed the reader to be acquainted with what was known respecting light. Here, we assume the same with regard to the eye. We observed that all nature manifests itself by means of colors. To the sense of sight, we now assert, extraordinary as it may in some degree appear, that the eye sees no form, inasmuch as light, shade, and color together constitute that which to our vision distinguishes object from object, and the parts of an object from each other. From these three, light, shade, and color, we construct the visible P.G. Roman 39 world, and thus at the same time make painting possible in art, which has the power of producing on a flat surface a much more perfect visible world than the actual one can be. The eye may be said to owe its existence to light, which calls forth as it were a sense that is akin to itself. The eye, in short, is formed with reference to light, to be fit for the action of light, the light it contains corresponding with the light without. We are here reminded of a significant adage in constant use with the ancient Ionian school: like is only known by like, and again of the words of an old mystic writer, which may be thus rendered: if the eye were not sunny, how could we perceive light? If God's own strength lived not in us, how could we delight in divine things? This immediate affinity between light and the eye will be denied by none. To consider them as identical in substance is less easy to comprehend. It will be more intelligible to assert that a dormant light resides in the eye, and that it may be excited by the slightest cause from within or from without. In darkness, we can by an effort of imagination call up the brightest images. In dreams, objects appear to us as in broad daylight. Awake, the slightest external action of light is perceptible, and if the organ suffers an actual shock, light and colors spring forth. Pgxl here, however, those who are wont to proceed according to a certain method may perhaps observe that as yet we have not decidedly explained what color is. This question, like the definition of light and the eye, we would for the present evade, and would appeal to our inquiry itself, where we have circumstantially shown how color is produced. We have only therefore to repeat that color is a law of nature. In relation with the sense of sight, we must assume too that every one has this sense, that every one knows the operation of nature on it, for to a blind man it would be impossible to speak of colors. That we may not, however, appear too anxious to shun such an explanation, we would restate what has been said as follows: color is an elementary phenomenon in nature, adapted to the sense of vision, a phenomenon which, like all others, exhibits itself by separation and contrast, by commixture and union, by augmentation and neutralization, by communication and dissolution. Under these general terms, its nature may be best comprehended. We do not press this mode of stating the subject on anyone. Those who, like ourselves, find it convenient will readily adopt it. But we have no desire to enter the lists hereafter in its defense from time immemorial. It has been dangerous to treat of color, so much so that PG Roman 41, one of our predecessors, ventured on a certain occasion to say the ox becomes furious if a red cloth is shown to him, but the philosopher who speaks of color only in a general way begins to rave. Nevertheless, if we are to proceed to give some account of our work to which we have appealed, we must begin by explaining how we have classed the different conditions under which color is produced. We found three modes in which it appears, three classes of colors, or rather three exhibitions of them. All the distinctions of these classes are easily expressed. Thus, in the first instance, we considered colors as far as they may be said to belong to the eye itself, and to depend on an action and reaction of the organ. Next, they attracted our attention as perceived in, or by means of colorless mediums, and lastly, where we could consider them as belonging to particular substances, we have denominated the first physiological, the second physical, the third chemical colors. The first are fleeting, and not to be arrested; the next are passing, but still for a while enduring; the last may be made permanent for any length of time. Having separated these classes, and kept them as distinct as possible with a view to a clear didactic exposition, we have been enabled at PG Roman 42, the same time to exhibit them in an unbroken series, to connect the fleeting with the somewhat more enduring and these again with the permanent hues. And thus, after having carefully attended to a distinct classification, in the first instance to do away with it again, when a larger view was desirable. In a fourth division of our work, we have therefore treated generally what was previously detailed under various particular conditions, and have thus in fact given a sketch for a future theory of colors. We will here only anticipate our statements so far as to observe that light and darkness, brightness and obscurity, or if a more general expression is preferred, light and its absence are necessary to the production of color. Next to the light, a color appears which we call yellow; another appears next to the darkness, which we name blue. When these in their purest state are so mixed that they are exactly equal, they produce a third color, called green. Each of the two first named colors can, however, of itself produce a new tint, by being condensed or darkened. They thus acquire a reddish appearance, which can be increased to so great a degree that the original blue or yellow is hardly to be recognized in it, but the intensest and purest red, especially in physical cases, is produced when the two extremes of the yellowed and blued are PG Roman 43. United, this is the actual state of the appearance and generation of colors. But we can also assume an existing red, in addition to the definite existing blue and yellow. And we can produce contrariwise by mixing what we directly produced by augmentation, or deepening, with these 3 or 6 colors, which may be conveniently included in a circle. The elementary doctrine of colors is alone concerned; all other modifications, which may be extended to infinity, have reference more to the application, have reference to the technical operations of the painter and dyer, and the various purposes of artificial life. To point out another general quality, we may observe that colors throughout are to be considered as half-lights, as half-shadows, on which account, if they are so mixed as reciprocally to destroy their specific hues, a shadowy tint, a gray, is produced. In the fifth division of our inquiry, we had proposed to point out the relations in which we should wish our doctrine of colors to stand to other pursuits important as this part of our work is. It is perhaps on this very account not so successful as we could wish yet, when we reflect that strictly speaking these relations cannot be described before they exist. We may console ourselves if we have in some degree failed in endeavoring for the first time to define them, for undoubtedly we should first PG Roman 44 wait to see how those whom we have endeavored to serve, to whom we have intended to make an agreeable and useful offering, how such persons, we say, will accept the result of our utmost exertion, whether they will adopt it, whether they will make use of it, and follow it up, or whether they will repel, reject, and suffer it to remain unassisted and neglected. Meanwhile, we venture to express what we believe and hope from the philosopher. We believe we merit thanks for having traced the phenomena of colors to their first sources, to the circumstances under which they simply appear, and are, and beyond which no further explanation respecting them is possible. It will besides be gratifying to him that we have arranged the appearances described in a form that admits of being easily surveyed, even should he not altogether approve of the arrangement itself. The medical practitioner, especially him whose study it is to watch over the organ of sight, to preserve it, to assist its defects, and to cure its disorders we reckon to make especially our friend in the chapter on the physiological colors, in the appendix, relating to those that are more strictly pathological he will find himself quite in his own province. We are not without hopes of seeing the physiological phenomena hitherto neglected, and we may add most important branch of the theory of P.G. Roman 45, colors completely, investigated through the exertions of those individuals, who in our own times are treating this department with success. The investigator of nature should receive us cordially, since we enable him to exhibit the doctrine of colors in the series of other elementary phenomena, and at the same time, enable him to make use of a corresponding nomenclature, nay, almost the same words and designations, as under the other rubrics. It is true, we give him rather more trouble as a teacher, for the chapter of colors is not now to be dismissed as heretofore with a few paragraphs and experiments, nor will the scholar submit to be so scantily entertained as he has hitherto been, without murmuring. On the other hand, an advantage will afterwards arise out of this, for if the Newtonian doctrine was easily learnt, insurmountable difficulties presented themselves in its application. Our theory is perhaps more difficult to comprehend, but once known, all is accomplished, for it carries its application along with it. The chemist who looks upon colors as indications by which he may detect the more secret properties of material things has hitherto found much inconvenience in the denomination and description of colors. Nay, some have been induced, after closer and nicer examination, to look upon color as an uncertain and fallacious criterion. P.G. Roman 46 in chemical operations, yet we hope by means of our arrangement and the nomenclature before alluded to bring color again into credit, and to awaken the conviction that a progressive augmenting mutable quality, a quality which admits of alteration even to inversion, is not fallacious, but rather calculated to bring to light the most delicate operations of nature. In looking a little further round us, we're not without fears that we may fail to satisfy another class of scientific men. By an extraordinary combination of circumstances, the theory of colors has been drawn into the province, and before the tribunal of the mathematician, a tribunal to which it cannot be said to be amenable. This was owing to its affinity with the other laws of vision, which the mathematician was legitimately called upon to treat. It was owing again to another circumstance. A great mathematician had investigated the theory of colors, and having been mistaken in his observations as an experimentalist, he employed the whole force of his talent to give consistency to this mistake. Were both these circumstances considered, all misunderstanding would presently be removed, and the mathematician would willingly cooperate with us, especially in the physical department of the theory. To the practical man, to the dyer, on the other hand, our labor must be altogether acceptable. P.G. Roman 47, for it was precisely those who reflected on the facts resulting from the operations of dyeing who were the least satisfied with the old theory. They were the first who perceived the insufficiency of the Newtonian doctrine. The conclusions of men are very different according to the mode in which they approach a science or branch of knowledge, from which side, through which door they enter. The literally practical man, the manufacturer whose attention is constantly and forcibly called to the facts which occur under his eye, who experiences benefit or detriment from the application of his convictions, to whom loss of time and money is not indifferent, who is desirous of advancing, who aims at equaling or surpassing what others have accomplished. Such a person feels the unsoundness and erroneousness of a theory much sooner than the man of letters in whose eyes words consecrated by authority are at last equivalent to solid coin, than the mathematician, whose formula always remains infallible even although the foundation on which it is constructed may not square with it again. To carry on the figure before employed in entering this theory, from the side of painting, from the side of aesthetic to coloring generally, we shall be P.G. Roman 48, found to have accomplished a most thankworthy office. For the artist, in the sixth part, we have endeavored to define the effects of color as addressed at once to the eye and mind with a view to making them more available for the purposes of art, although much in this portion, and indeed throughout, has been suffered to remain as a sketch. It should be remembered that all theory can in strictness only point out leading principles under the guidance of which practice may proceed with vigor and be enabled to attain legitimate results. P.G. 1. Part Roman 1 Physiological colors. We naturally place these colors first because they belong altogether, or in a great degree, to the subject, one to the eye itself. They are the foundation of the whole doctrine, and open to our view the chromatic harmony on which so much difference of opinion has existed, they have been hitherto looked upon as extrinsic and casual as illusion and infirmity. Their appearances have been known from ancient date, but as they were too evanescent to be arrested, they were banished into the region of phantoms, and under this idea have been very variously described. Thus they are called colors adventitiae by Boyle, imaginarii, and fantastici by Rieste, by Buffon couleurs accidentelles, by Schurfer Scheinfarben apparent colors, ocular illusions and deceptions of sight pg2, by many, by Hamburger Vische fugitiva, by Darwin ocular spectra. We have called them physiological because they belong to the eye in a healthy state, because we consider them as the necessary conditions of vision, the lively alternating action of which with reference to external objects, and a principle within it, is thus plainly indicated. To these we subjoin the pathological colors, which, like all deviations from a constant law, afford a more complete insight into the nature of the physiological colors. Effects of light and darkness on the eye. The retina, after being acted upon by light or darkness, is found to be in two different states, which are entirely opposed to each other. If we keep the eyes open in a totally dark place, a certain sense of privation is experienced, the organ is abandoned to itself, it retires into itself, that stimulating and grateful contact is wanting by means of which it is connected with the external world, and becomes part of a whole. Pg 3. If we look on a white, strongly illumined surface, the eye is dazzled, and for a time is incapable of distinguishing objects moderately lighted. The whole of the retina is acted on in each of these extreme states, and thus we can only experience one of these effects at a time. In the one case 6, we found the organ in the utmost relaxation and susceptibility, in the other 7, in an overstrained state, and scarcely susceptible at all. If we pass suddenly from the one state to the other, even without supposing these to be the extremes, but only perhaps a change from bright to dusky, the difference is remarkable, and we find that the effects last for some time. In passing from bright daylight to a dusky place, we distinguish nothing at first. By degrees, the eye recovers its susceptibility. Strong eyes sooner than weak ones, the former in a minute, while the latter may require 7 or 8 minutes. The fact that the eye is not susceptible to faint Pg4 impressions of light, if we pass from light to comparative darkness, has led to curious mistakes in scientific observations. Thus an observer whose eyes required some time to recover their tone was long under the impression that rotten wood did not emit light at noonday, even in a dark room. The fact was he did not see the faint light, because he was in the habit of passing from bright sunshine to the dark room, and only subsequently remained so long there that the eye had time to recover itself. The same may have happened to Dr. Wall, who in the daytime, even in a dark room, could hardly perceive the electric light of amber. Our not seeing the stars by day, as well as the improved appearance of pictures, seen through a double tube, is also to be attributed to the same cause. If we pass from a totally dark place to one illumined by the sun, we are dazzled in coming from a lesser degree of darkness to light that is not dazzling. We perceive all objects clearer and better, hence eyes that have been in a state of repose are in all cases better able to perceive moderately distinct appearances. Prisoners who have been long confined in darkness acquire so great a susceptibility of the retina that even in the dark, probably a darkness Pg5 very slightly illumined, they can still distinguish objects. In the act which we call seeing, the retina is at one and the same time in different and even opposite states. The greatest brightness short of dazzling acts near the greatest darkness. In this state, we at once perceive all the intermediate gradations of chiaroscuro and all the varieties of hues. We will proceed in due order to consider and examine these elements of the visible world, as well as the relation in which the organ itself stands to them, and for this purpose, we take the simplest objects. Roman 2. Effects of black and white objects on the eye. In the same manner as the retina generally is affected by brightness and darkness, so it is affected by single bright or dark objects. If light and dark produce different results on the whole retina, so black and white objects seen at Pg6, the same time produce the same states together, which light and dark occasioned in succession. A dark object appears smaller than a bright one of the same size. Let a white disk be placed on a black ground, and a black disk on a white ground, both being exactly similar in size. Let them be seen together at some distance. and we shall pronounce the last to be about a fifth part smaller than the other, if the black circle be made larger by so much they will appear equal one. Thus Tycho de Brahe remarked that the moon in conjunction the darker state appears about a fifth part smaller than when in opposition the bright full state the first crescent appears to belong to a larger disk than the remaining dark portion, which can sometimes be distinguished at the period of the new moon. Black dresses make people appear smaller than light ones. Light seen behind an edge make an apparent notch in it. A ruler behind which the flame of a light just appears seems to us indented. The rising or setting sun appears to make a notch in the horizon. Plate 1's. Black as the equivalent of darkness leaves pg7 the organ in a state of repose. White as the representative of light excites it. We may perhaps conclude from the above experiment 16 that the unexcited retina, if left to itself, is drawn together and occupies a less space than in its active state produced by the excitement of light. Hence Kepler says very beautifully, cerdum est vel in retina causa pictor vel, in spiritibus causa, impressionis exister dilatationum, lucidorum paralip, in vitalianum p. 220 Schurfer, expresses a similar conjecture. Note A. However, this may be both impressions derived from such objects remain in the organ itself, and last for some time, even when the external cause is removed. In ordinary experience, we scarcely notice this, for objects are seldom presented to us, which are very strongly relieved from each other, and we avoid looking at those appearances that dazzle the sight. In glancing from one object to another, the succession of images appears to us distinct. We are not aware that some portion of the impression derived from the object first contemplated passes to that which is next looked at. If in the morning on waking, when the eye is very susceptible, we look intently at the bars pg8 of a window, relieved against the dawning sky, and then shut our eyes or look towards a totally dark place, we shall see a dark cross on a light ground before us for some time. Every image occupies a certain space on the retina, and of course a greater or less space in proportion, as the object is seen near or at a distance. If we shut the eyes immediately after looking at the sun, we shall be surprised to find how small the image it leaves appears. If, on the other hand, we turn the open eye towards the side of a room and consider the visionary image in relation to other objects, we shall always see it larger in proportion to the distance of the surface on which it is thrown. This is easily explained by the laws of perspective, according to which a small object near covers a great one at a distance. The duration of these visionary impressions varies with the powers or structure of the eye in different individuals, just as the time necessary for the recovery of the tone of the retina varies in passing from brightness to darkness. 10. It can be measured by minutes and seconds pg9, indeed much more exactly than it could formerly have been by causing a lighted linstock to revolve rapidly so as to appear a circle. Note B. But the force with which an impinging light impresses the eye is especially worthy of attention. The image of the sun lasts longest. Other objects of various degrees of brightness leave the traces of their appearance on the eye for a proportionate time. These images disappear by degrees and diminish at once in distinctness and in size. They are reduced from the contour inwards, and the impression on some persons has been that in square images the angles become gradually blunted, till at last a diminished round image floats before the eye. Such an image, when its impression is no more observable, can immediately after be again revived on the retina by opening and shutting the eye, thus alternately exciting and resting it. pg10. Images may remain on the retina in morbid affections of the eye for 14-17 minutes, or even longer. This indicates extreme weakness of the organ, its inability to recover itself, while visions of persons or things, which are the objects of love or aversion, indicate the connection between sense and thought. If while the image of the window bars before mentioned lasts, we look upon a light gray surface, the cross will then appear light, and the panes dark. In the first case 20, the image was like the original picture, so that the visionary impression also could continue unchanged. But in the present instance, our attention is excited by a contrary effect being produced. Various examples have been given by observers of nature. The scientific men who made observations in the Cordilleras saw a bright appearance round the shadows of their heads on some clouds. This example is a case in point, for while they fixed their eyes on the dark shadow, and at the same time moved from the spot. The compensatory light image appeared to float round the PG11 real dark one. If we look at a black disk on a light gray surface, we shall presently, by changing the direction of the eyes in the slightest degree, see a bright halo floating round the dark circle. A similar circumstance happened to myself, for while as I sat in the open air, I was talking to a man who stood at a little distance from me, relieved on a gray sky. It appeared to me, as I slightly altered the direction of my eyes after having for some time looked fixedly at him, that his head was encircled with a dazzling light. In the same way, probably, might be explained the circumstance that persons crossing dewy meadows at sunrise see a brightness round each other's heads too. The brightness in this case may be also iridescent, as the phenomena of refraction come into the account. Thus again, it has been asserted that the shadows of a balloon thrown on clouds were bordered with bright and somewhat variegated circles. Beccaria made use of a paper kite in some experiments on electricity. Round this kite appeared a small shining cloud, varying in size. The same brightness was even observed round part of the string. Sometimes it disappeared PG12, and if the kite moved faster, the light appeared to float to and fro for a few moments on the place before occupied. This appearance, which could not be explained by those who observed it at the time, was the image which the eye retained of the kite, relieved as a dark mass on a bright sky, that image being changed into a light mass on a comparatively dark background. In optical and especially in chromatic experiments, where the observer has to do with bright lights, whether colorless or colored, great care should be taken that the spectrum which the eye retains in consequence of a previous observation does not mix with the succeeding one, and thus affect the distinctness and purity of the impression. These appearances have been explained as follows. That portion of the retina on which the dark cross 29 was impressed is to be considered in a state of repose and susceptibility on this portion. Therefore, the moderately light surface acted in a more lively manner than on the rest of the retina, which had just been impressed with the light through the panes, and which, having thus been excited by a much stronger brightness, could only view the gray surface as a dark. PG13. This mode of explanation appears sufficient for the cases in question, but in the consideration of phenomena hereafter to be adduced, we are forced to trace the effects to higher sources. The eye after sleep exhibits its vital elasticity more especially by its tendency to alternate its impressions, which in the simplest form change from dark to light, and from light to dark. The eye cannot for a moment remain in a particular state, determined by the object it looks upon. On the contrary, it is forced to a sort of opposition, which in contrasting extreme with extreme, intermediate degree with intermediate degree at the same time, combines these opposite impressions, and thus ever tends to a whole, whether the impressions are successive or simultaneous, and confined to one image. Perhaps the peculiarly grateful sensation, which we experience in looking at the skillfully treated chiaroscuro of colorless pictures and similar works of art, arises chiefly from the simultaneous impression of a whole, which by the organ itself is sought rather than arrived at in succession, and which, whatever may be the result, can never be arrested. PG14. Roman 3. Gray surfaces and objects. A moderate light is essential to many chromatic experiments. This can be presently obtained by surfaces more or less gray, and thus we have at once to make ourselves acquainted with this simplest kind of middle tint, with regard to which it is hardly necessary to observe that in many cases a white surface in shadow or in a low light may be considered equivalent to a gray. Since a gray surface is intermediate between brightness and darkness, it admits of our illustrating a phenomenon before described 29 by an easy experiment. Let a black object be held before a gray surface, and let the spectator, after looking steadfastly at it, keep his eyes unmoved. While it is taken away, the space it occupied appears much lighter. Let a white object be held up in the same manner. On taking it away, the space it occupied will appear much darker than the PG15 rest of the surface. Let the spectator in both cases turn his eyes this way, and that on the surface, the visionary images will move in like manner. A gray object on a black ground appears much brighter than the same object on a white ground. If both comparisons are seen together, the spectator can hardly persuade himself that the two grays are identical. We believe this again to be a proof of the great excitability of the retina, and of the silent resistance which every vital principle is forced to exhibit when any definite or immutable state is presented to it. Thus inspiration already presupposes expiration. Thus every systole, its diastole, it is the universal formula of life, which manifests itself in this. As in all other cases, when darkness is presented to the eye it demands brightness, and vice versa, it shows its vital energy, its fitness, to receive the impression of the object precisely, by spontaneously tending to an opposite state. Pg 16. Roman 4. Dazzling colorless objects. If we look at a dazzling, altogether colorless object, it makes a strong lasting impression, and its aftervision is accompanied by an appearance of color. Let a room be made as dark as possible. Let there be a circular opening in the window shutter, about 3 inches in diameter, which may be closed, or not at pleasure, the sun being suffered to shine through this on a white surface. Let the spectator from some little distance fix his eyes on the bright circle, thus admitted, the whole being then closed. Let him look towards the darkest part of the room. A circular image will now be seen to float before him. The middle of this circle will appear bright colorless, or somewhat yellow, but the border will at the same moment appear red. After a time, this red increasing towards the center covers the whole circle, and at last the bright central point. No sooner, however, is the whole circle red than the edge begins to be blue, and the blue gradually encroaches inwards. Pg 17 on the red. When the whole is blue, the edge becomes dark and colorless. This darker edge again slowly encroaches on the blue till the whole circle appears colorless. The image then becomes gradually fainter, and at the same time diminishes in size. Here again, we see how the retina recovers itself by a succession of vibrations after the powerful external impression it received. 25-26. By several repetitions similar in result, I found the comparative duration of these appearances, in my own case, to be as follows. I looked on the bright circle 5 seconds, and then having closed the aperture saw the colored visionary circle floating before me after 13 seconds. It was altogether red. 29 seconds, next elapsed, till the whole was blue, and 48 seconds, till it appeared colorless by shutting and opening. The eye constantly revived the image, so that it did not quite disappear till 7 minutes had elapsed. Future observers may find these periods shorter or longer, as their eyes may be stronger or weaker. 23. But it would be very remarkable if, notwithstanding such variations, a corresponding proportion as to relative duration should be found to exist. Pg 18. But this remarkable phenomenon no sooner excites our attention than we observe a new modification of it. If we receive the impression of the bright circle as before, and then look on a light gray surface in a moderately lighted room, an image again floats before us. But in this instance, a dark one by degrees, it is encircled by a green border that gradually spreads inwards over the whole circle, as the red did in the former instance. As soon as this has taken place, a dingy yellow appears, and filling the space, as the blue did before, is finally lost in a negative shade. These two experiments may be combined by placing a black and a white plane surface next each other in a moderately lighted room, and then looking alternately on one and the other, as long as the impression of the light circle lasts. The spectator will then perceive at first a red and green image. Alternately, and afterwards the other changes. After a little practice, the two opposite colors may be perceived at once, by causing the floating image to fall on the junction of the two planes. This can be more conveniently done if the planes are at some distance, for the spectrum then appears larger. Pg 19. I happened to be in a forge towards evening at the moment when a glowing mass of iron was placed on the anvil. I had fixed my eyes steadfastly on it, and turning round, I looked accidentally into an open coal shed. A large red image now floated before my eyes, and as I turned them from the dark opening to the light boards of which the shed was constructed, the image appeared half green half red according as it had a lighter or darker ground behind it. I did not at that time take notice of the subsequent changes of this appearance. The aftervision occasioned by a total dazzling of the retina corresponds with that of a circumscribed bright object. The red color seen by persons who are dazzled with snow belongs to this class of phenomena, as well as the singularly beautiful green color, which dark objects seem to wear after looking long on white paper in the sun. The details of such experiments may be investigated hereafter by those whose young eyes are capable of enduring such trials further for the sake of science. With these examples we may also class the black letters, which in the evening light appear Pg 20 red. Perhaps we might insert under the same category the story that drops of blood appeared on the table, at which Henry Roman IV of France had seated himself with the Duc de Guise to play at dice. Roman 5 Colored objects. We have hitherto seen the physiological colors displayed in the aftervision of colorless bright objects, and also in the aftervision of general colorless brightness. We shall now find analogous appearances, if a given color be presented to the eye. In considering this, all that has been hitherto detailed must be present to our recollection. The impression of colored objects remains in the eye like that of colorless ones, but in this case, the energy of the retina stimulated, as it is to produce the opposite color, will be more apparent. Let a small piece of bright-colored paper or silk stuff be held before a moderately lighted white surface. Let the observer look steadfastly pg 21 on the small colored object, and let it be taken away after a time. While his eyes remain unmoved, the spectrum of another color will then be visible on the white plane. The colored paper may be also left in its place. While the eye is directed to another part of the white plane, the same spectrum will be visible there too, for it arises from an image which now belongs to the eye. In order at once to see what color will be evoked by this contrast, the chromatic circle, one may be referred to. The colors are here arranged in a general way, according to the natural order, and the arrangement will be found to be directly applicable in the present case, for the colors diametrically opposed to each other in this diagram are those which reciprocally evoke each other in the eye. Thus yellow demands purple, orange, blue, red, green, and vice versa. Thus again, all intermediate gradations reciprocally evoke each other, the simpler color demanding the compound, and vice versa. Note Roman 100. The cases here under consideration occur oftener than we are aware in ordinary life. Indeed, pg 22, an attentive observer sees these appearances everywhere, while on the other hand, the uninstructed, like our predecessors, consider them as temporary visual defects, sometimes even as symptoms of disorders in the eye, thus exciting serious apprehensions. A few remarkable instances may here be inserted. I had entered an inn towards evening, and as a well-favored girl with a brilliantly fair complexion, black hair, and a scarlet bodice came into the room, I looked attentively at her, as she stood before me at some distance in half shadow. As she presently afterwards turned away, I saw on the white wall, which was now before me, a black face, surrounded with a bright light, while the dress of the perfectly distinct figure appeared of a beautiful sea green. Among the materials for optical experiments, there are portraits with colors and shadows, exactly opposite to the appearance of nature. The spectator, after having looked at one of these for a time, will see the visionary figure tolerably true to nature. This is conformable to the same principles and consistent with experience, for in the former instance, a negress with a white headdress would have given me a white face, surrounded with black. In the case, pg 23 of the painted figures, however, which are commonly small, the parts are not distinguishable by every one in the afterimage. A phenomenon which has before excited attention among the observers of nature is to be attributed, I am persuaded, to the same cause. It has been stated that certain flowers towards evening in summer coruscate, become phosphorescent, or emit a momentary light. Some persons have described their observation of this minutely. I had often endeavored to witness it myself, and had even resorted to artificial contrivances to produce it. On the 19th of June, 1799, late in the evening, when the twilight was deepening into a clear night, as I was walking up and down the garden with a friend, we very distinctly observed a flame-like appearance near the oriental poppy, the flowers of which are remarkable for their powerful red color. We approached the place, and looked attentively at the flowers, but could perceive nothing further, till at last, by passing and repassing repeatedly, while we looked sideways on them, we succeeded in renewing the appearance as often as we pleased. It proved to be a physiological phenomenon, such as others we have described, and the apparent pg 24 coruscation was nothing but the spectrum of the flower in the compensatory blue-green color. In looking directly at a flower, the image is not produced, but it appears immediately as the direction of the eye is altered. Again, by looking sideways on the object, a double image is seen for a moment for the spectrum, then appears near and on the real object. The twilight accounts for the eye being in a perfect state of repose, and thus very susceptible, and the color of the poppy is sufficiently powerful in the summer twilight of the longest days to act with full effect, and produce a compensatory image. I have no doubt these appearances might be reduced to experiment, and the same effect produced by pieces of colored paper. Those who wish to take the most effectual means for observing the appearance in nature, suppose, in a garden should. Fix the eyes on the bright flowers selected for the purpose, and immediately after look on the gravel path. This will be seen studded with spots of the opposite color. The experiment is practicable on a cloudy day, and even in the brightest sunshine, for the sunlight, by enhancing the brilliancy of the flower, renders it fit to produce the compensatory color, sufficiently distinct to be perceptible even in a bright light. Thus peonies produce beautiful green marigolds, vivid blue spectra. Pg 25. As the opposite color is produced by a constant law in experiments with colored objects on portions of the retina, so the same effect takes place when the whole retina is impressed with a single color. We may convince ourselves of this by means of colored glasses. If we look long through a blue pane of glass, everything will afterwards appear in sunshine to the naked eye, even if the sky is gray, and the scene colorless. In like manner, in taking off green spectacles, we see all objects in a red light. Every decided color does a certain violence to the eye, and forces the organ to opposition. We have hitherto seen the opposite colors producing each other successively on the retina. It now remains to show by experiment that the same effects can exist simultaneously. If a colored object impinges on one part of the retina, the remaining portion at the same moment has a tendency to produce the compensatory color. To pursue a former experiment, if we look on a yellow piece of paper placed on a white surface, the remaining part of the organ has already a tendency to produce a purple hue on the colorless surface. In this case, the small portion of yellow is not powerful enough to produce Pg 26 this appearance distinctly, but if a white paper is placed on a yellow wall, we shall see the white tinged with a purple hue. Although this experiment may be made with any colors, yet red and green are particularly recommended for it, because these colors seem powerfully to evoke each other. Numerous instances occur in daily experience. If a green paper is seen through striped or flowered muslin, the stripes or flowers will appear reddish. A gray building scene through green palisades appears in like manner reddish. A modification of this tint in the agitated sea is also a compensatory color. The light side of the waves appears green in its own color, and the shadowed side is tinged with the opposite hue. The different direction of the waves with reference to the eye produces the same effect. Objects seen through an opening in a red or green curtain appear to wear the opposite hue. These appearances will present themselves to the attentive observer on all occasions, even to an unpleasant degree. Having made ourselves acquainted with the simultaneous exhibition of these effects in direct cases, we shall find that we can also observe them by indirect means. If we place a piece of Pg 27 paper of a bright orange color on the white surface, we shall, after looking intently at it, scarcely perceive the compensatory color on the rest of the surface. But when we take the orange paper away, and when the blue spectrum appears in its place immediately, as this spectrum becomes fully apparent, the rest of the surface will be overspread, as if by a flash, with a reddish-yellow light, thus exhibiting to the spectator, in a lively manner, the productive energy of the organ in constant conformity with the same law. As the compensatory colors easily appear where they do not exist in nature near and after the original opposite ones, so they are rendered more intense where they happen to mix with a similar real hue. In a court which was paved with gray limestone flags, between which grass had grown, the grass appeared of an extremely beautiful green, when the evening clouds threw a scarcely perceptible reddish light on the pavement. In an opposite case, we find in walking through meadows where we see scarcely anything but green the stems of trees, and the roads often gleam with a reddish hue. This tone is not uncommon in the works of landscape painters, especially those who practice in watercolors. They probably see it in Pg 28 nature, and thus unconsciously imitating it, their coloring is criticized as unnatural. These phenomena are of the greatest importance since they direct our attention to the laws of vision and are a necessary preparation for future observations on colors. They show that the eye especially demands completeness and seeks to eke out the colorific circle in itself. The purple or violet color suggested by yellow contains red and blue-orange, which responds to blue is composed of yellow and red-green uniting blue, and yellow demands red. And so through all gradations of the most complicated combinations, that we are compelled in this case to assume three leading colors, has been already remarked by other observers. When in this completeness, the elements of which it is composed are still appreciable by the eye, the result is justly called harmony. We shall subsequently endeavor to show how the theory of the harmony of colors may be deduced from these phenomena, and how simply through these qualities colors may be capable of being applied to aesthetic purposes. This will be shown when we have gone through the whole circle of our observations, returning to the point from which we started. pg 29. Roman 6 Colored Shadows. Before, however, we proceed further, we have yet to observe some very remarkable cases of the vivacity with which the suggested colors appear in the neighborhood of others. We allude to colored shadows to arrive at these. We first turn our attention to shadows that are colorless or negative. A shadow cast by the sun in its full brightness on a white surface gives us no impression of color, it appears black, or if a contrary light here assumed to differ only in degree can act upon it, it is only weaker half-lighted gray. Two conditions are necessary for the existence of colored shadows. First, that the principal light tinge the white surface with some hue. Secondly, that a contrary light illumine to a certain extent the cast shadow. Let a short lighted candle be placed at twilight on a sheet of white paper between it and the declining daylight. Let a pencil be placed pg 30 upright, so that its shadow thrown by the candle may be lighted, but not overcome by the weak daylight. The shadow will appear of the most beautiful blue. That this shadow is blue is immediately evident, but we can only persuade ourselves by some attention that the white paper acts as a reddish yellow, by means of which the complemental blue is excited in the I note Roman 500. In all colored shadows, therefore, we must presuppose a color excited or suggested by the hue of the surface on which the shadow is thrown. This may be easily found to be the case by attentive consideration, but we may convince ourselves at once by the following experiment. Place 2 candles at night opposite each other on a white surface, hold a thin rod between them upright, so that 2 shadows be cast by it. Take a colored glass, and hold it before one of the lights, so that the white paper appear colored at the same moment. The shadow cast by the colored light, and slightly illumined by the colorless one, will exhibit the complemental hue. pg 31. An important consideration suggests itself here, to which we shall frequently have occasion to return. Color itself is a degree of darkness, hence Kircher is perfectly right in calling it lumen oppicatum, as it is allied to shadow, so it combines readily with it. It appears to us readily in and by means of shadow. The moment a suggesting cause presents itself, we could not refrain from adverting at once to a fact which we propose to trace and develop hereafter. Note: select the moment in twilight when the light of the sky is still powerful enough to cast a shadow, which cannot be entirely effaced by the light of a candle. The candle may be so placed that a double shadow shall be visible, one from the candle towards the daylight, and another from the daylight towards the candle. If the former is blue, the latter will appear orange yellow. This orange yellow is in fact, however, only the yellowed light of the candle diffused over the whole paper, and which becomes visible in shadow. This is best exemplified by the former experiment with 2 candles and colored glasses. pg 32. The surprising readiness with which shadow assumes a color will again invite our attention in the further consideration of reflections and elsewhere. Thus the phenomena of colored shadows may be traced to their cause without difficulty henceforth. Let anyone who sees an instance of the kind observe only with what hue the light surface on which they are thrown is tinged. Nay, the color of the shadow may be considered as a chromatoscope of the illumined surface, for the spectator may always assume the color of the light to be the opposite of that of the shadow, and by an attentive examination may ascertain this to be the fact in every instance. These appearances have been a source of great perplexity to former observers, for as they were remarked chiefly in the open air, where they commonly appeared blue, they were attributed to a certain inherent blue, or blue coloring quality in the air. The inquirer can, however, convince himself by the experiment with the candle in a room that no kind of blue light or reflection is necessary to produce the effect in question. The experiment may be made on a cloudy day with white curtains drawn pg 33 before the light, and in a room where no trace of blue exists, and the blue shadow will be only so much the more beautiful. De Saussure, in the description of his ascent of Mont Blanc, says a second remark, which may not be uninteresting, relates to the color of the shadows. These notwithstanding the most attentive observation, we never found dark blue. Although this had been frequently the case in the plain, on the contrary, in 59 instances, we saw them once yellowish, 6 times pale bluish, 18 times colorless or black, and 34 times pale violet. Some natural philosophers suppose that these colors arise from accidental vapors diffused in the air, which communicate their own hues to the shadows. not that the colors of the shadows are occasioned by the reflection of any given sky color or interposition of any given air color. The above observations seem to favor this opinion. The instances given by de Saussure may be now explained and classed with analogous examples without difficulty. At a great elevation, the sky was generally free from vapors. The sun shone in full force on the snow, so that it appeared perfectly white to the eye. In this case, they saw the shadows quite colorless, if the air was charged with a pg-34 certain degree of vapor, in consequence of which the light snow would assume a yellowish tone. The shadows were violet-colored, and this effect, it appears, occurred oftenest. They saw also bluish shadows, but this happened less frequently, and that the blue and violet were pale was owing to the surrounding brightness, by which the strength of the shadows was mitigated. Once only they saw the shadow yellowish. In this case, as we have already seen 70, the shadow is cast by a colorless light, and slightly illumined by a colored one. In traveling over the Harz in winter, I happened to descend from the Brocken towards evening. The wide slopes, extending above and below me, the heath, every insulated tree, and projecting rock, and all masses of both were covered with snow or hoarfrost. The sun was sinking towards the Oder ponds. One, during the day, owing to the yellowish hue of the snow, shadows tending to violet had already been observable. These might now be pronounced to be decidedly blue, as the illumined parts exhibited a yellow deepening to orange. But as the sun at last was about to set, and its rays greatly mitigated by the thicker vapors, pg-35 began to diffuse a most beautiful red color over the whole scene around me. The shadow color changed to a green in lightness, to be compared to a sea green in beauty to the green of the emerald. The appearance became more and more vivid. One might have imagined oneself in a fairy world, for every object had clothed itself in the two vivid and so beautifully harmonizing colors, till at last, as the sun went down, the magnificent spectacle was lost in a gray twilight, and by degrees in a clear moon and starlight night. One of the most beautiful instances of colored shadows may be observed during the full moon. The candlelight and moonlight may be contrived to be exactly equal in force. Both shadows may be exhibited with equal strength and clearness, so that both colors balance each other perfectly. A white surface being placed opposite the full moon, and the candle being placed a little on one side at a due distance, an opaque body is held before the white plane. A double shadow will then be seen that, cast by the moon and illumined by the candlelight, will be a powerful red yellow, and, contrariwise, that cast by the candle and illumined by the moon, will appear of the most beautiful blue. The shadow, composed of the union of the two shadows, where pg-36 they cross each other, is black. The yellow shadow, 74, cannot perhaps be exhibited in a more striking manner. The immediate vicinity of the blue and the interposing black shadow make the appearance the more agreeable. It will even be found, if the eye dwells long on these colors, that they mutually evoke and enhance each other, the increasing red in the one still producing its contrast, viz. A kind of sea green. We are here led to remark that in this, and in all cases, a moment or two may perhaps be necessary to produce the complemental color. The retina must be first thoroughly impressed with the demanding hue before the responding one can be distinctly observable. When divers are under water, and the sunlight shines into the divingbell, everything is seen in a red light, the cause of which will be explained hereafter, while the shadows appear green. The very same phenomenon, which I observed on a high mountain 75, is presented to others in the depths of the sea, and thus nature throughout is in harmony with herself. Some observations and experiments, which equally illustrate what has been stated with regard pg-37 to colored objects and colored shadows, may be here added. Let a white paper blind be fastened inside the window on a winter evening. In this blind, let there be an opening through which the snow of some neighboring roof can be seen. Towards dusk, let a candle be brought into the room. The snow seen through the opening will then appear perfectly blue, because the paper is tinged with warm yellow by the candlelight. The snow seen through the aperture is here equivalent to a shadow illumined by a contrary light 76, and may also represent a gray disk on a colored surface 56. Another very interesting experiment may conclude these examples if we take a piece of green glass of some thickness and hold it so that the window bars be reflected in it. They will appear double owing to the thickness of the glass. The image which is reflected from the under surface of the glass will be green. The image which is reflected from the upper surface, and which should be colorless, will appear red. The experiment may be very satisfactorily made by pouring water into a vessel. The the inner surface of which can act as a mirror for both reflections may first be seen colorless, while the water is pure, and then by tinging it, they will exhibit two opposite hues. pg 38. Roman 7 faint lights. Light in its full force appears purely white, and it gives this impression also in its highest degree of dazzling splendor. Light, which is not so powerful, can also under various conditions remain colorless. Several naturalists and mathematicians have endeavored to measure its degrees. Lambert Bauger Rumford. Yet an appearance of color presently manifests itself in fainter lights, for in their relation to absolute light, they resemble the colored spectra of dazzling objects. 39. A light of any kind becomes weaker either when its own force from whatever cause is diminished, or when the eye is so circumstanced or placed that it cannot be sufficiently impressed by the action of the light. Those appearances, which may be called objective, come under the head of physical colors. We will only advert here to the transition from white to red heat in glowing iron. We may also observe pg 39 that the flames of lights at night appear redder in proportion to their distance from the eye. Note F. Candlelight at night acts as yellow. When seen near, we can perceive this by the effect it produces on other colors. At night, a pale yellow is hardly to be distinguished from white-blue approaches to green and rose color to orange. Candlelight at twilight acts powerfully as a yellow light. This is best proved by the purple-blue shadows, which under these circumstances are evoked by the eye. The retina may be so excited by a strong light that it cannot perceive fainter lights. 11. If it perceive these, they appear colored. Hence candlelight by day appears reddish, thus resembling in its relation to fuller light the spectrum of a dazzling object. Nay, if at night we look long and intently on the flame of a light, it appears to increase in redness. There are faint lights which, notwithstanding their moderate luster, give an impression of a pg 40 white, or at the most of a light yellow appearance on the retina, such as the moon in its full splendor. Rotten wood has even a kind of bluish light. All this will hereafter be the subject of further remarks. If at night we place a light near a white or grayish wall, so that the surface be illumined from this central point, to some extent, we find on observing the spreading light at some distance that the boundary of the illumined surface appears to be surrounded with a yellow circle which on the outside tends to red yellow. We thus observe that when light direct or reflected does not act in its full force, it gives an impression of yellow, of reddish. And lastly, even of red. Here, we find the transition to halos, which we are accustomed to see in some mode or other round luminous points. Roman 8 subjective halos. Halos may be divided into subjective and objective. The latter will be considered under the physical colors. The first only belong here. These are distinguished from the objective pg 41 halos by the circumstance of their vanishing when the point of light which produces them on the retina is covered. We have before noticed the impression of a luminous object on the retina, and seen that it appears larger, but the effect is not at an end here. It is not confined to the impression of the image. An expansive action also takes place spreading from the center. That a nimbus of this kind is produced round the luminous image in the eye may be best seen in a dark room, if we look towards a moderately large opening in the window shutter. In this case, the bright image is surrounded by a circular misty light. I saw such a halo bounded by a yellow and yellowed circle on opening my eyes at dawn, on an occasion when I passed several nights in a bed carriage. Halos appear most vivid when the eye is susceptible from having been in a state of repose. A dark background also heightens their appearance. Both causes account for our seeing them so strong. If a light is presented to the eyes pg 42 on waking at night, these conditions were combined when Descartes, after sleeping, as he sat in a ship, remarked such a vividly colored halo round the light. A light must shine moderately, not dazzle, in order to produce the impression of a halo in the eye. At all events, the halos of dazzling lights cannot be observed. We see a splendor of this kind round the image of the sun, reflected from the surface of water. A halo of this description, attentively observed, is found to be encircled towards its edge with a yellow border. But even here the expansive action before alluded to is not at an end, but appears still to extend in varied circles. Several cases seem to indicate a circular action of the retina, whether owing to the round form of the eye itself and its different parts, or to some other cause. If the eye is pressed only in a slight degree from the inner corner, darker or lighter circles, pg 43, appear at night even without pressure. we can sometimes perceive a succession of such circles emerging from or spreading over each other. We have already seen that a yellow border is apparent round the white space illumined by a light placed near it. This may be a kind of objective halo. 88. Subjective halos may be considered as the result of a conflict between the light and a living surface, from the conflict between the exciting principle and the excited and undulating motion arises, which may be illustrated by a comparison with the circles on water. The stone thrown in drives the water in all directions. The effect attains a maximum, it reacts, and being opposed continues under the surface. The effect goes on, culminates again, and thus the circles are repeated. If we have ever remarked the concentric rings which appear in a glass of water, on trying to produce a tone, by rubbing the edge, if we call to mind the intermitting pulsations in the reverberations of bells, we shall approach a conception of what may take place on the retina when the image of a luminous object impinges on it, not to mention pg 44, that as a living and elastic structure, it has already a circular principle in its organization. Note G. The bright circular space which appears round the shining object is yellow ending in red. Then follows a greenish circle, which is terminated by a red border. This appears to be the usual phenomenon, where the luminous body is somewhat considerable. In size, these halos become greater the more distant we are from the luminous object. Halos may, however, appear extremely small and numerous when the impinging image is minute yet powerful in its effect. The experiment is best made with a piece of gold leaf, placed on the ground, and illumined by the sun. In these cases, the halos appear in variegated rays. The iridescent appearance produced in the eye when the sun pierces through the leaves of trees seems also to belong to the same class of phenomena. pg 45. Pathological colors. Appendix. We are now sufficiently acquainted with the physiological colors to distinguish them from the pathological. We know what appearances belong to the eye in a healthy state, and are necessary to enable the organ to exert its complete vitality and activity. Morbid phenomena indicate in like manner the existence of organic and physical laws, for if a living being deviates from those rules with reference to which it is constructed, it still seeks to agree with the general vitality of nature in conformity with general laws, and throughout its whole course, still proves the constancy of those principles on which the universe has existed, and by which it is held together. We will here first advert to a very remarkable state, in which the vision of many persons is found to be, as it presents a deviation from the ordinary mode of seeing colors. It might be fairly classed under morbid impressions, but as it is consistent in itself, as it often occurs, pg 46 may extend to several members of a family, and probably does not admit of cure. We may consider it as bordering only on the nosological cases, and therefore place it first. I was acquainted with two individuals, not more than 20 years of age, who were thus affected. Both had bluish-gray eyes and acute sight for near and distant objects by daylight and candlelight, and their mode of seeing colors was in the main quite similar. They agreed with the rest of the world in denominating white black and gray in the usual manner. Both saw white untinged with any hue. One saw a somewhat brownish appearance in black, and in gray a somewhat reddish tinge. In general, they appeared to have a very delicate perception of the gradations of light and dark. They appeared to see yellow red yellow, and yellowed one like others. In the last case, they said they saw the yellow passing as it were over the red, as if glazed some thickly ground carmine, which had dried in a saucer they called red. pg 47. But now a striking difference presented itself. If the carmine was passed thinly over the white saucer, they would compare the light color thus produced to the color of the sky, and call it blue. If a rose was shown them beside it, they would in like manner call it blue, and in all the trials which were made, it appeared that they could not distinguish light blue from rose color. They confounded rose color blue and violet on all occasions. These colors only appeared to them to be distinguished from each other by delicate shades of lighter, darker, intenser, or fainter appearance. Again, they could not distinguish green from dark orange, nor more especially from a red-brown. If anyone accidentally conversing with these individuals happened to question them about surrounding objects, their answers occasioned the greatest perplexity, and the interrogator began to fancy his own wits were out of order. With some method we may, however, approach to a nearer knowledge of the law of this deviation from the general law. pg 48. These persons, as may be gathered from what has been stated, saw fewer colors than other people. Hence, arose the confusion of different colors they called the sky rose color, and the rose blue or vice versa. The question now is, did they see both blue or both rose color? Did they see green-orange or orange-green? This singular enigma appears to solve itself if we assume that they saw no blue, but instead of it, a light pure red or rose color. We can comprehend what would be the result of this by means of the chromatic diagram. If we take away blue from the chromatic circle, we shall miss violet, and green as well. Pure red occupies the place of blue and violet, and in again mixing with yellow, the red produces orange where green should be. Professing to be satisfied with this mode of explanation, we have named this remarkable deviation from ordinary vision a chianobulpsia 2. We have prepared some colored figures for pg 49 its further elucidation, and in explaining these, we shall add some further details. Among the examples will be found a landscape colored in the mode in which the individuals alluded to appeared to see nature, the sky rose color, and all that should be green varying from yellow to brown-red nearly, as foliage appears to us in autumn. 3 Note H. We now proceed to speak of morbid and other extraordinary affections of the retina, by which the eye may be susceptible of an appearance of light, without external light, reserving for a future occasion the consideration of galvanic light. If the eye receives a blow, sparks seem to spread from it in some states of body again, when the blood is heated, and the system much excited. If the eye is pressed first gently, and then more and more strongly, a dazzling and intolerable light may be excited. If those who have been recently couched experience pain and heat in the eye, they frequently pg 50 see fiery flashes and sparks. These symptoms last sometimes for a week or fortnight, or till the pain and heat diminish. A person suffering from earache saw sparks and balls of light in the eye during each attack, as long as the pain lasted. Persons suffering from worms often experience extraordinary appearances in the eye, sometimes sparks of fire, sometimes specters of light, sometimes frightful figures, which they cannot by an effort of the will cease to see. Sometimes these appearances are double. Hypochondriacs frequently see dark objects such as threads, hair, spiders, flies, wasps. These appearances also exhibit themselves in the incipient hard cataract. Many see semi-transparent small tubes forms like wings of insects, bubbles of water of various sizes, which fall slowly down if the eye is raised. Sometimes these congregate together, so as to resemble the spawn of frogs. Sometimes they appear as complete spheres, sometimes in the form of lenses. As light appeared in the former instances pg 51, without external light, so also these images appear without corresponding external objects. The images are sometimes transient, sometimes they last during the patient's life. Color again frequently accompanies these impressions. For hypochondriacs, often see yellowed stripes in the eye. These are generally more vivid and numerous in the morning, or when lasting. We have before seen that the impression of any object may remain for a time in the eye. This we have found to be a physiological phenomenon. 23. The excessive duration of such an impression, on the other hand, may be considered as morbid. The weaker the organ, the longer the impression of the image lasts. The retina does not so soon recover itself, and the effect may be considered as a kind of paralysis. 28. This is not to be wondered at in the case of dazzling lights. If anyone looks at the sun, he may retain the image in his eyes for several days. Boyle relates an instance of 10 years. The same takes place in a certain degree with pg 52, regard to objects that are not dazzling. Bush relates of himself that the image of an engraving complete in all its parts was impressed on his eye for 17 minutes. A person inclined to fullness of blood retained the image of a bright red calico with white spots many minutes in the eye, and saw it float before everything like a veil. It only disappeared by rubbing the eye for some time. Schurfer observes that the red color, which is the consequence of a powerful impression of light, may last for some hours. As we can produce an appearance of light on the retina by pressure on the eyeball, so by a gentle pressure, a red color appears, thus corresponding with the afterimage of an impression of light. Many sick persons on awaking see everything in the color of the morning sky, as if through a red veil. So if in the evening they doze and wake again, the same appearance presents itself. It remains for some minutes, and pg 53 always disappears. If the eye is rubbed, a little red stars and balls sometimes accompany the impression. This state may last for a considerable time. The aeronauts, particularly Zambicari and his companions, relate that they saw the moon blood red at the highest elevation, as they had ascended above the vapors of the earth, through which we see the moon and sun naturally of such a color, it may be suspected that this appearance may be classed with the pathological colors the senses, namely may be so influenced by an unusual state that the whole nervous system, and particularly the retina, may sink into a kind of inertness and inexcitability. Hence, it is not impossible that the moon might act as a very subdued light, and thus produce the impression of the red color. The sun even appeared blood red to the aeronauts of Hamburg. If those who are at some elevation in a balloon scarcely hear each other speak, may not this too be attributed to the inexcitable state of the nerves, as well as to the thinness of the air? Objects are often seen by sick persons in variegated colors. Boyle relates an instance pg 54 of a lady, who after a fall by which an eye was bruised saw all objects, but especially white objects glittering in colors, even to an intolerable degree. Physicians give the name of crupsia to an affection of the sight occurring in typhoid maladies. In these cases, the patients state that they see the boundaries of objects colored, where light and dark meet. A change probably takes place in the humors of the eye, through which their achromatism is affected. In cases of milky cataract, a very turbid crystalline lens causes the patient to see a red light. In a case of this kind, which was treated by the application of electricity, the red light changed by degrees to yellow, and at last to white when the patient again began to distinguish objects. These changes of themselves warranted the conclusion that the turbid state of the lens was gradually approaching the transparent state. We shall be enabled easily to trace this effect to its source as soon as we become better acquainted with the physical colors. If again it may be assumed that a jaundiced PG 55 patient sees, through an actually yellow-colored humor, we are at once referred to the department of chemical colors, and it is thus evident that we can only thoroughly investigate the chapter of pathological colors when we have made ourselves acquainted with the whole range of the remaining phenomena. What has been adduced may therefore suffice for the present, till we resume the further consideration of this portion of our subject. In conclusion, we may however at once advert to some peculiar states or dispositions of the organ. There are painters who, instead of rendering the colors of nature, diffuse a general tone, a warm or cold hue over the picture. In some again, a predilection for certain colors displays itself; in others, a want of feeling for harmony. Lastly, it is also worthy of remark that savage nations, uneducated people and children, have a great predilection for vivid colors, that animals are excited to rage by certain colors, that people of refinement avoid vivid colors in their dress and the objects that are about them, and seem inclined to banish them altogether from their presence. Note Roman 11. It has been found necessary to follow the author's nomenclature throughout pg 56. Part Roman 2. Physical colors. We give this designation to colors which are produced by certain material mediums. These mediums, however, have no color themselves, and may be either transparent, semi-transparent, yet transmitting light, or altogether opaque. The colors in question are thus produced in the eye through such external given causes, or are merely reflected to the eye when by whatever means they are already produced without us. Although we thus ascribe to them a certain objective character, their distinctive quality still consists in their being transient and not to be arrested. They are called by former investigators colors, apparens fluxi fugitivi fantastici falsi variants. They are also called speciosi and emphatici. On account of their striking splendor, they are immediately connected with the physiological colors, and appear to have but little more reality. For while in the production pg 57 of the physiological colors, the eye itself was chiefly efficient, and we could only perceive the phenomena thus evoked within ourselves but not without us, we have now to consider the fact that colors are produced in the eye by means of colorless objects, that we thus too have a colorless surface before us, which is acted upon as the retina itself is, and that we can perceive the appearance produced upon it without us in such a process. However, every observation will convince us that we have to do with colors in a progressive and mutable, but not in a final or complete state. Hence, in directing our attention to these physical colors, we find it quite possible to place an objective phenomenon beside a subjective one, and often by means of the union of the two, successfully, to penetrate farther into the nature of the appearance. Thus, in the observations by which we become acquainted with the physical colors, the eye is not to be considered as acting alone, nor is the light ever to be considered in immediate relation with the eye, but we direct our attention, especially to the various effects produced by mediums, those mediums being themselves colorless. Pg 58. Light under these circumstances may be affected by three conditions. First, when it flashes back from the surface of a medium, in considering which catoptrical experiments invite our attention. Secondly, when it passes by the edge of a medium, the phenomena thus produced were formerly called perioptical. We prefer the term paroptical. Thirdly, when it passes through either a merely light-transmitting or an actually transparent body, thus constituting a class of appearances on which dioptrical experiments are founded, we have called a fourth class of physical colors epoptical, as the phenomena exhibit themselves on the colorless surface of bodies under various conditions, without previous or actual dye. Note K. In examining these categories with reference to our three leading divisions, according to which we consider the phenomena of colors, in a physiological, physical, or chemical view, we find that the catoptrical colors are closely connected with the physiological. The paroptical are already somewhat more distinct and independent. The dioptrical exhibit themselves as entirely and strictly physical, and as having a decidedly objective character. The epoptical, although still only apparent, may be considered as the transition to the chemical colors. Pg 59. If we were desirous of prosecuting our investigations strictly in the order of nature, we ought to proceed according to the classification which has just been made. But in didactic treatises, it is not of so much consequence to connect as to duly distinguish the various divisions of a subject in order that at last, when every single class and case has been presented to the mind, the whole may be embraced in one comprehensive view. We therefore turn our attention forthwith to the dioptrical class, in order at once to give the reader the full impression of the physical colors, and to exhibit their characteristics the more strikingly. Roman 9. Dioptrical colors. Colors are called dioptrical when a colorless medium is necessary to produce them. The medium must be such that light and darkness can act through it either on the eye or on opposite surfaces. It is thus required that the medium should be transparent, or at least capable to a certain degree of transmitting light. Pg 60. According to these conditions, we divide the dioptrical phenomena into two classes, placing in the first those which are produced by means of imperfectly transparent yet light-transmitting mediums, and in the second, such as are exhibited when the medium is in the highest degree transparent. Roman 10. Dioptrical colors of the first class. Space, if we assume it to be empty, would have the quality of absolute transparency to our vision if this space is filled, so that the eye cannot perceive that it is so. There exists a more or less material transparent medium, which may be of the nature of air, and gas may be fluid or even solid. The pure and light-transmitting semi-transparent medium is only an accumulated form of the transparent medium. It may therefore be presented to us in three modes. Pg 61. The extreme degree of this accumulation is white, the simplest, brightest, first opaque occupation of space. Transparency itself, empirically considered, is already the first degree of the opposite state. The intermediate degrees from this point to opaque white are infinite. At whatever point short of opacity we arrest the thickening medium, it exhibits simple and remarkable phenomena when placed in relation with light and darkness. The highest degree of light, such as that of the sun of phosphorus burning in oxygen, is dazzling and colorless, so the light of the fixed stars is for the most part colorless. This light, however seen through a medium, but very slightly thickened, appears to us yellow if the density of such a medium be increased, or if its volume become greater. We shall see the light gradually assume a yellowed hue, which at last deepens to a rubby color. Note Roman 50. Pg 62. If on the other hand darkness is seen through a semi-transparent medium, which is itself illumined by a light striking on it, a blue color appears. This becomes lighter and paler as the density of the medium is increased, but on the contrary appears darker and deeper the more transparent the medium becomes in the least degree of dimness short of absolute transparency. Always supposing a perfectly colorless medium, this deep blue approaches the most beautiful violet. If this effect takes place in the eye as here described, and may thus be pronounced to be subjective, it remains further to convince ourselves of this by objective phenomena, for a light thus mitigated and subdued illumines all objects in like manner with a yellow, yellowed, or red hue, and although the effect of darkness through the non-transparent medium does not exhibit itself so powerfully, Yet the blue sky displays itself in the camera obscura very distinctly on white paper, as well as every other material color. In examining the cases in which this important PG63 leading phenomenon appears, we naturally mention the atmospheric colors. First, most of these may be here introduced in order. The sun seen through a certain degree of vapor appears with a yellow disk. The center is often dazzlingly yellow. When the edges are already red, the orb seen through a thick yellow mist appears rubbered. As was the case in 1794, even in the north, the same appearance is still more decided owing to the state of the atmosphere. When the sirocco prevails in southern climates, the clouds generally surrounding the sun, in the latter case, are of the same color, which is reflected again on all objects. The red hues of morning and evening are owing to the same cause. The sun is announced by a red light. In shining through a greater mass of vapors, the higher he rises, the yellower and brighter the light becomes. If the darkness of infinite space is seen through atmospheric vapors illumined by the daylight, the blue color appears on high mountains. The sky appears by day intensely blue owing to the few thin vapors that float before the endless dark space. As soon as we descend in the PG64 valleys, the blue becomes lighter till at last in certain regions, and in consequence of increasing vapors, it altogether changes to a very pale blue. The mountains in like manner appear to us blue, for as we see them at so great a distance that we no longer distinguish the local tints, and as no light reflected from their surface acts on our vision, they are equivalent to mere dark objects, which owing to the interposed vapors appear blue. So we find the shadowed parts of nearer objects are blue when the air is charged with thin vapors. The snow mountains, on the other hand, at a great distance, still appear white or approaching to a yellowish hue, because they act on our eyes as brightness seen through atmospheric vapor. The blue appearance at the lower part of the flame of a candle belongs to the same class of phenomena. If the flame be held before a white ground, no blue will be seen. But this color will immediately appear if the flame is opposed PG65 to a black ground. This phenomenon may be exhibited most strikingly with a spoonful of lighted spirits of wine. We may thus consider the lower part of the flame as equivalent to the vapor, which, although infinitely thin, is still apparent before the dark surface. It is so thin that one may easily see to read through it. On the other hand, the point of the flame, which conceals objects from our sight, is to be considered as a self-illuminating body. Lastly, smoke is also to be considered as a semi-transparent medium, which appears to us yellow or reddish before a light ground, but blue before a dark one. If we now turn our attention to fluid mediums, we find that water, deprived in a very slight degree of its transparency, produces the same effects. The infusion of the lignum nephriticum Gillandina, which formerly excited so much attention, is only a semi-transparent liquor, which in dark wooden cups must appear blue, but held towards the sun in a transparent glass, must exhibit a yellow appearance. PG66. A drop of scented water of spirit varnish of several metallic solutions may be employed to give various degrees of opacity to water. For such experiments, spirit of soap perhaps answers best. The bottom of the sea appears to divers of a red color in bright sunshine. In this case, the water, owing to its depth, acts as a semi-transparent medium. Under these circumstances, they find the shadows green, which is the complemental color. Among solid mediums, the opal attracts our attention. First, its colors are at least partly to be explained by the circumstance that it is in fact a semi-transparent medium, through which sometimes light, sometimes dark substrata are visible. For these experiments, however, the opal glass vitrum asteroids Durasol is the most desirable material. It is prepared in various ways, and its semi-opacity is produced by metallic oxides. The same effect is produced also by melting pulverized and calcined bones, together PG67, with the glass, on which account it is also known by the name of beingless. But prepared in this mode, it easily becomes too opaque. This glass may be adapted for experiments in various ways. It may either be made in a very slight degree non-transparent, in which case the light seen through various layers, placed one upon the other, may be deepened from the lightest yellow to the deepest red, or if made originally more opaque, it may be employed in thinner or thicker lamin. The experiments may be successfully made in both ways. In order, however, to see the bright blue color, the glass should neither be too opaque nor too thick, for, as it is quite natural that darkness must act weakly through the semi-transparent medium, so this medium, if too thick, soon approaches whiteness. Panes of glass throw a yellow light on objects through those parts where they happen to be semi-opaque, and these same parts appear blue if we look at a dark object through them. Smoked glass may be also mentioned here, and is in like manner to be considered as a semi-opaque medium. It exhibits the sun more Pg68 or less ruby-colored. And although this appearance may be attributed to the black-brown color of the soot, we may still convince ourselves that a semi-transparent medium here acts, if we hold such a glass moderately smoked and lit by the sun on the unsmoked side before a dark object, for we shall then perceive a bluish appearance. A striking experiment may be made in a dark room with sheets of parchment. If we fasten a piece of parchment before the opening in the window shutter, when the sun shines, it will appear nearly white. By adding a second, a yellowish color appears which still increases as more leaves are added, till at last it changes to red. A similar effect, owing to the state of the crystalline lens in milky cataract, has been already adverted to 131. Having now in tracing these phenomena arrived at the effect of a degree of opacity, scarcely capable of transmitting light, we may here mention a singular appearance, which was owing to a momentary state of this kind. Pg 69. A portrait of a celebrated theologian had been painted some years before the circumstance to which we allude by an artist, who was known to have considerable skill in the management of his materials. The very reverend individual was represented in a rich velvet dress, which was not a little admired and which attracted the eye of the spectator, almost more than the face. The picture, however, from the effect of the smoke of lamps and dust, had lost much of its original vivacity. It was therefore placed in the hands of a painter who was to clean it and give it a fresh coat of varnish. This person began his operations by carefully washing the picture with a sponge. No sooner, however, had he gone over the surface once or twice and wiped away the first dirt than, to his amazement, the black velvet dress changed suddenly to a light blue plush, which gave the ecclesiastic a very secular though somewhat old-fashioned appearance. The painter did not venture to go on with his washing. He could not comprehend how a light blue should be the ground of the deepest black still, less how he could so suddenly have removed a glazing color, capable of converting the one tint to the other. At all events, he was not a little disconcerted at having spoilt the picture to such an extent. Nothing to characterize the ecclesiastic remained. Pg 70. But the richly curled round wig, which made the exchange of a faded plush for a handsome new velvet dress far from desirable. Meanwhile, the mischief appeared irreparable, and the good artist, having turned the picture to the wall, retired to rest with a mind ill at ease. But what was his joy the next morning when, on examining the picture, he beheld the black velvet dress again in its full splendor. He could not refrain from again wetting a corner upon which the blue color again appeared, and after a time vanished. On hearing of this phenomenon, I went at once to see the miraculous picture. A wet sponge was passed over it in my presence, and the change quickly took place. I saw a somewhat faded, but decidedly light blue plush dress, the folds under the arm being indicated by some brown strokes. I explained this appearance to myself by the doctrine of the semi-opaque medium. The painter, in order to give additional depth to his black, may have passed some particular varnish over it. On being washed, this varnish imbibed some moisture, and hence became semi-opaque, in consequence of which the black underneath immediately appeared blue. Perhaps those who are practically acquainted with the effect of varnishes may, through accident or contrivance, arrive at some means of exhibiting this singular appearance. As an experiment to those Pg 71 who are fond of investigating natural phenomena, notwithstanding many attempts, I could not myself succeed in reproducing it. Having now traced the most splendid instances of atmospheric appearances, as well as other less striking, yet sufficiently remarkable cases, to the leading examples of semi-transparent mediums, we have no doubt that attentive observers of nature will carry such researches further and accustom themselves to trace and explain the various appearances which present themselves in everyday experience on the same principle. We may also hope that such investigators will provide themselves with an adequate apparatus in order to place remarkable facts before the eyes of others who may be desirous of information. We venture once for all to call the leading appearance in question, as generally described in the foregoing pages, a primordial and elementary phenomenon, and we may here be permitted at once to state what we understand by the term. The circumstances which come under our notice in ordinary observation are for the most part insulated cases, which with some attention admit pg 72 of being classed under general leading facts. These again range themselves under theoretical rubrics, which are more comprehensive, and through which we become better acquainted with certain indispensable conditions of appearances in detail. From henceforth everything is gradually arranged under higher rules and laws, which however are not to be made intelligible by words and hypotheses to the understanding, merely, but at the same time by real phenomena to the senses. We call these primordial phenomena because nothing appreciable by the senses lies beyond them. On the contrary, they are perfectly fit to be considered as a fixed point to which we first ascended step by step, and from which we may in like manner descend to the commonest case of everyday experience. Such an original phenomenon is that which has lately engaged our attention. We see on the one side light brightness, on the other darkness obscurity. We bring the semi-transparent medium between the two, and from these contrasts, and this medium, the colors develop themselves contrasted in like manner, but soon through a reciprocal relation, directly tending again to a point of union. 1. pg 73. With this conviction, we look upon the mistake that has been committed in the investigation of this subject to be a very serious one, inasmuch as a secondary phenomenon has been thus placed higher in order. The primordial phenomenon has been degraded to an inferior place. Nay, secondary phenomenon has been placed at the head. A compound effect has been treated as simple, a simple appearance as compound. Owing to this contradiction, the most capricious complication and perplexity have been introduced into physical inquiries, the effects of which are still apparent. But when even such a primordial phenomenon is arrived at, the evil still is that we refuse to recognize it as such, that we still aim at something beyond, although it would become us to confess that we are arrived at the limits of experimental knowledge. Let the observer of nature suffer the primordial phenomenon to remain undisturbed in its beauty. Let the philosopher admit it into his department, and he will find that important elementary facts are a worthier basis for further operations than insulated cases, opinions, and hypotheses. Note Roman 10,001. That is according to the author's statement, 150-151. Both tend to red, the yellow deepening to orange, as the comparatively dark medium is thickened before brightness, the blue deepening to violet, as the light medium is thinned before darkness. pg 74. Roman 11. Dioptrical colors of the second class. Refraction. Dioptrical colors of both classes are closely connected, as will presently appear on a little examination. Those of the first class appeared through semi-transparent mediums. Those of the second class will now appear through transparent mediums. But since every substance, however transparent, may be already considered to partake of the opposite quality, as every accumulation of a medium called transparent proves, so the near affinity of the two classes is sufficiently manifest. We will, however, first consider transparent mediums abstractedly as such as entirely free from any degree of opacity, and direct our whole attention to a phenomenon which here presents itself, and which is known by the name of refraction. In treating of the physiological colors, we have already had occasion to vindicate what pg 75 were formerly called illusions of sight as the active energies of the healthy and duly efficient eye too, and we are now again invited to consider similar instances, confirming the constancy of the laws of vision. Throughout nature as presented to the senses, everything depends on the relation which things bear to each other, but especially on the relation which man, the most important of these, bears to the rest. Hence, the world divides itself into two parts, and the human being as subject stands opposed to the object. Thus the practical man exhausts himself in the accumulation of facts, the thinker in speculation, each being called upon to sustain a conflict which admits of no peace and no decision. But still, the main point always is whether the relations are truly seen, as our senses, if healthy, are the surest witnesses of external relations, so we may be convinced that in all instances where they appear to contradict reality, they lay the greater and surer stress on true relations. Thus a distant object appears to us smaller, and precisely by this means we are aware of distance. We produced colored appearances on colorless objects through colorless mediums, and at the same moment our pg 76 attention was called to the degree of opacity in the medium. Thus the different degrees of opacity in so-called transparent mediums, nay even other physical and chemical properties belonging to them, are known to our vision by means of refraction, and invite us to make further trials in order to penetrate more completely by physical and chemical means, into those secrets, which are already open to our view on one side. Objects seen through mediums more or less transparent do not appear to us in the place which they should occupy according to the laws of perspective. On this fact, the dioptrical colors of the second class depend. Those laws of vision which admit of being expressed in mathematical formula are based on the principle that as light proceeds in straight lines, it must be possible to draw a straight line from the eye to any given object in order that it be seen. If therefore case arises in which the light arrives to us in a bent or broken line, that we see the object by means of a bent or broken line, we are at once informed that the Pg77 medium between the eye and the object is denser, or that it has assumed this or that foreign nature. This deviation from the law of right-line vision is known by the general term of refraction, and although we may take it for granted that our readers are sufficiently acquainted with its effects, yet we will here once more briefly exhibit it in its objective and subjective point of view. Let the sun shine diagonally into an empty cubical vessel, so that the opposite side be illumined, but not the bottom. Let water be then poured into this vessel, and the direction of the light will be immediately altered, for a part of the bottom is shone upon at the point where the light enters the thicker medium. It deviates from its rectilinear direction, and appears broken, hence the phenomenon is called the breaking Brechung, or refraction. Thus much of the objective experiment. We arrive at the subjective fact in the following mode. Let the eye be substituted for the sun, let the sight be directed in like manner Pg78, diagonally, over one side, so that the opposite inner side be entirely seen. While no part of the bottom is visible on pouring in water, the eye will perceive a part of the bottom, and this takes place without our being aware that we do not see in a straight line, for the bottom appears to us raised, and hence we give the term elevation Hebung to the subjective phenomenon. Some points, which are particularly remarkable with reference to this, will be adverted to hereafter. Were we now to express this phenomenon generally, we might here repeat in conformity with the view lately taken that the relation of the objects is changed or deranged. But as it is our intention at present to separate the objective from the subjective appearances, we first express the phenomenon in a subjective form and say a derangement, or displacement of the object seen, or to be seen takes place. But that which is seen without a limiting outline may be thus affected without our perceiving the change. On the other hand, if what we look at has a visible termination, we have an evident indication that a displacement occurs. If therefore Pg79, we wish to ascertain the relation or degree of such a displacement, we must chiefly confine ourselves to the alteration of surfaces with visible boundaries, in other words, to the displacement of circumscribed objects. The general effect may take place through parallel mediums, for every parallel medium displaces the object by bringing it perpendicularly towards the eye. The apparent change of position is, however, more observable through mediums that are not parallel. These latter may be perfectly spherical, or may be employed in the form of convex or concave lenses. We shall make use of all these as occasion may require in our experiments, but as they not only displace the object from its position, but alter it in various ways, we shall in most cases prefer employing mediums with surfaces not indeed parallel with reference to each other, but still altogether plane, namely prisms. These have a triangle for their base, and may, it is true, be considered as portions of a lens, but they are particularly available for our experiments inasmuch as they very perceptibly displace the object from its position without producing a remarkable distortion. Pg80. And now, in order to conduct our observations with as much exactness as possible, and to avoid all confusion and ambiguity, we confine ourselves at first to subjective experiments, in which namely the object is seen by the observer through a refracting medium. As soon as we have treated these in due series, the objective experiments will follow in similar order. Roman 12. Refraction, without the appearance of color. Refraction can visibly take place without our perceiving an appearance of color, to whatever extent a colorless or uniformly colored surface may be altered as to its position by refraction. No color consequent upon refraction appears within it, provided it has no outline or boundary. We may convince ourselves of this in various ways. Pg81. Place a glass cube on any larger surface, and look through the glass perpendicularly or obliquely. The unbroken surface opposite the eye appears altogether raised, but no color exhibits itself if we look at a pure gray or blue sky, or a uniformly white or colored wall. Through a prism, the portion of the surface which the eye thus embraces will be altogether changed as to its position without our therefore observing the smallest appearance of color. Roman 13 Conditions of the appearance of color. Although in the foregoing experiments, we have found all unbroken surfaces, large or small, colorless, yet at the outlines or boundaries, where the surface is relieved upon a darker or lighter object, we observe a colored appearance. Outline as well as surface is necessary to constitute a figure or circumscribed object. We therefore express the leading fact, thus circumscribed objects must be displaced by refraction in order to the exhibition of an appearance of color. Pg 82. We place before us the simplest object, a light disk on a dark ground. A1 A displacement occurs with regard to this object. If we apparently extend its outline from the center, by magnifying it, this may be done with any convex glass, and in this case, we see a blue edge B. We can to appearance contract the circumference of the same light disk towards the center. By diminishing the object, the edge will then appear yellow C. This may be done with a concave glass, which however should not be ground thin like common eyeglasses, but must have some substance in order however to make this experiment at once. With the convex glass, let a smaller black disk be inserted within the light disk on a black ground. If we magnify the black disk on a white ground with a convex glass, the same result takes place as if we diminish the white disk, for we extend the black outline upon the white, and we thus perceive the yellow edge together with the blue edge. These two appearances, the blue and yellow, exhibit themselves in and upon the white. They Pg 83. Both assume a reddish hue in proportion as they mingle with the black too. Plate 2. In this short statement, we have described the primordial phenomena of all appearance of color occasioned by refraction. These undoubtedly may be repeated, varied, and rendered more striking, may be combined, complicated, confused, but after all may be still restored to their original simplicity. In examining the process of the experiment, just given, we find that in the one case we have to appearance extended the white edge upon the dark surface, in the other, we have extended the dark edge upon the white surface. Supplanting one by the other, pushing one over the other, we will now endeavor step by step to analyze these and similar cases. If we cause the white disk to move in appearance entirely from its place, which can be done Pg 84 effectually by prisms, it will be colored according to the direction in which it apparently moves in conformity with the above laws. If we look at the disk A3 through a prism, so that it appear moved to be, the outer edge will appear blue and bluered according to the law of the figure B, Fig 1, the other edge being yellow and yellowed according to the law of the figure C, Fig 1. For in the first case the white figure is as it were extended over the dark boundary, and in the other case the dark boundary is passed over the white figure. The same happens if the disk is to appearance moved from A to C, from A to D, and so throughout the circle. As it is with the simple effect, so it is with more complicated appearances. If we look through a horizontal prism, a B4, at a white disk, placed at some distance behind it at E, the disk will be raised to F and colored according to the above law. If we remove this prism and look through a vertical 1C, D at the same disk, it will appear at H and colored according to the same law. If we place the two prisms one upon the other, the disk will appear displaced diagonally in conformity with a general law of nature, and will be colored as Pg 85 before that is according to its movement in the direction. For example, if we attentively examine these opposite colored edges, we find that they only appear in the direction of the apparent change of place. A round figure leaves us in some degree uncertain. As to this, a quadrangular figure removes all doubt. The quadrangular figure A6 moved in the direction a B or a D exhibits no color on the sides which are parallel with the direction in which it moves. On the other hand, if moved in the direction a C parallel with its diagonal, all the edges of the figure appear colored 7. Thus a former position 203 is here confirmed, viz., to produce color an object must be so displaced that the light edges be apparently carried over a dark surface, the dark edges over a light surface, the figure over its boundary, the boundary over the figure. But Pg 86, if the rectilinear boundaries of a figure could be indefinitely extended by refraction, so that figure and background might only pursue their course next, but not over each other, no color would appear, not even if they were prolonged to infinity. Roman 14 conditions, under which the appearance of color increases. We have seen in the foregoing experiments that all appearance of color occasioned by refraction depends on the condition that the boundary or edge be moved in upon the object itself, or the object itself over the ground, that the figure should be as it were carried over itself or over the ground, and we shall now find that by increased displacement of the object the appearance of color exhibits itself in a greater degree. This takes place in subjective experiments, to which for the present we confine ourselves under the following conditions. First, if in looking through parallel mediums, the eye is directed more obliquely. Secondly, if the surfaces of the medium are no longer parallel, but form a more or less acute angle. Pg 87. Thirdly, owing to the increased proportion of the medium, whether parallel mediums be increased in size, or whether the angle be increased provided it does not attain a right angle. Fourthly, owing to the distance of the eye armed with a refracting medium from the object to be displaced. Fifthly, owing to a chemical property that may be communicated to the glass, and which may be afterwards increased in effect. The greatest change of place, short of considerable distortion of the object, is produced by means of prisms, and this is the reason why the appearance of color can be exhibited most powerfully through glasses of this form, yet we will not in employing them suffer ourselves to be dazzled by the splendid appearances they exhibit, but keep the above well-established simple principles calmly in view. The color which is outside or foremost in the apparent change of an object by refraction is always the broader, and we will henceforth call this a border. The color that remains next the outline is the narrower, and this we will call an edge. Pg 88. If we move a dark boundary towards a light surface, the yellow broader border is foremost, and the narrower yellowed edge follows close to the outline. If we move a light boundary towards a dark surface, the broader violet border is foremost, and the narrower blue edge follows. If the object is large, its center remains uncolored. Its inner surface is then to be considered as unlimited 195. It is displaced, but not otherwise altered. But if the object is so narrow that under the above conditions the yellow border can reach the blue edge, the space between the outlines will be entirely covered with color. If we make this experiment with a white stripe on a black ground, 1. The two extremes will presently meet, and thus produce green. We shall then see the following series of colors: yellowed, yellow, green, blue, bluard. If we place a black band or stripe on white paper too, the violet border will spread till it meets Pg 89, the yellowed edge. In this case, the intermediate black is effaced, as the intermediate white was in the last experiment, and in its stead, a splendid pure red will appear. 3. The series of colors will now be as follows: blue, bluard, red, yellowed, yellow. The yellow and blue in the first case 214 can by degrees meet so fully that the two colors blend entirely in green, and the order will then be yellowed, green, bluard. In the second case, 215, under similar circumstances, we see only blue, red, yellow. This appearance is best exhibited by refracting the bars of a window when they are relieved on a gray sky. 4. Pg 90. In all this, we are never to forget that this appearance is not to be considered as a complete or final state, but always as a progressive increasing, and in many senses controllable appearance. Thus we find that by the negation of the above 5 conditions it gradually decreases, and at last disappears altogether. Roman 15 explanation of the foregoing phenomena. Before we proceed further, it is incumbent on us to explain the first tolerably simple phenomenon, and to show its connection with the principles first laid down in order that the observer of nature may be enabled clearly to comprehend the more complicated appearances that follow. In the first place, it is necessary to remember that we have to do with circumscribed objects. In the act of seeing generally, it is the circumscribed visible which chiefly invites our observation. And in the present instance, in speaking of the appearance of color, as occasioned by refraction, the circumscribed visible, the detached object, solely occupies our attention. Pg 91. For our chromatic exhibitions, we can however divide objects generally into primary and secondary. The expressions of themselves denote what we understand by them, but our meaning will be rendered still more plain by what follows. Primary objects may be considered firstly as original as images, which are impressed on the eye by things before it, and which assure us of their reality to these. The secondary images may be opposed as derived images, which remain in the organ when the object itself is taken away, those apparent afterimages, which have been circumstantially treated of in the doctrine of physiological colors. The primary images, again, may be considered as direct images, which, like the original impressions, are conveyed immediately from the object to the eye in contradistinction to these. The secondary images may be considered as indirect, being only conveyed to us, as it were at second hand from a reflecting surface. These are the mirrored or catoptrical images, which in certain cases can also become double images. When namely the reflecting body is transparent pg 92 and has two parallel surfaces one behind the other, in such a case, an image may be reflected to the eye from both surfaces, and thus arise double images inasmuch as the upper image does not quite cover the under one. This may take place in various ways. Let a playing card be held before a mirror. We shall at first see the distinct image of the card, but the edge of the whole card, as well as that of every spot upon it, will be bounded on one side with a border which is the beginning of the second reflection. This effect varies in different mirrors, according to the different thickness of the glass and the accidents of polishing. If a person wearing a white waistcoat with the remaining part of his dress dark stands before certain mirrors, the border appears very distinctly, and in like manner, the metal buttons on dark cloth exhibit the double reflection very evidently. The reader who has made himself acquainted with our former descriptions of experiments 80 will the more readily follow the present statement. The window bars reflected by plates of glass appear double, and by increased thickness of the glass, and a due adaptation of the angle of reflection, the two reflections may be entirely separated from each other. So, vase full of pg 93 water with a plain mirror-like bottom reflects any object twice, the two reflections being more or less separated under the same conditions. In these cases, it is to be observed that where the two reflections cover each other, the perfect vivid image is reflected, but where they are separated, they exhibit only weak transparent and shadowy images. If we wish to know which is the under and which the upper image, we have only to take a colored medium, for then a light object reflected from the under surface is of the color of the medium, while that reflected from the upper surface presents the complemental color. With dark objects it is the reverse, hence black and white surfaces may be here also conveniently employed. How easily the double images assume and evoke colors will here again be striking. Thirdly, the primary images may be considered as principal images, while the secondary can be, as it were, annexed to these as accessory images. Such an accessory image produces a sort of double form, except that it does not separate itself from the principal object, although it may be said to be always endeavoring to do so. It is pg 94 with secondary images of this last description that we have to do in prismatic appearances. A surface without a boundary exhibits no appearance of color. When refracted 195, whatever is seen must be circumscribed by an outline to produce this effect. In other words, a figure and object is required. This object undergoes an apparent change of place by refraction. The change is, however, not complete, not clean, not sharp, but incomplete inasmuch as an accessory image only is produced. In examining every appearance of nature, but especially in examining an important and striking one, we should not remain in one spot. We should not confine ourselves to the insulated fact nor dwell on it exclusively, but look round through all nature to see where something similar, something that has affinity to it, appears. For it is only by combining analogies that we gradually arrive at a whole which speaks for itself and requires no further explanation. Thus we here call to mind that in certain cases refraction unquestionably produces double images, as is the case in Iceland's spar. Similar pg 95 double images are also apparent in cases of refraction through large rock crystals, and in other instances phenomena which have not hitherto been sufficiently observed. But since in the case under consideration 227, the question relates not to double, but to accessory images, we refer to a phenomenon already adverted to, but not yet thoroughly investigated. We allude to an earlier experiment in which it appeared that a sort of conflict took place in regard to the retina between a light object and its dark ground, and between a dark object and its light ground 16, The light object in this case appeared larger, the dark one smaller. By a more exact observation of this phenomenon, we may remark that the forms are not sharply distinguished from the ground, but that they appear with a kind of gray in some degree colored edge, in short with an accessory image. If then objects seen only with the naked eye produce such effects, what may not take place when a dense medium is interposed, it is not that alone which presents itself to us, pg 96, in obvious operation, which produces and suffers effects, but likewise all principles that have a mutual relation only of some sort are efficient accordingly, and indeed often in a very high degree. Thus, when refraction produces its effect on an object, there appears an accessory image. Next, the object itself, the real form thus refracted, seems even to linger behind, as if resisting the change of place, but the accessory image seems to advance and extends itself more or less in the mode already shown 212,216. We also remarked 224 that in double images the fainter appear only half substantial, having a kind of transparent evanescent character, just as the fainter shades of double shadows must always appear as half shadows. These latter assume colors easily and produce them readily. 69. The former also 80, and the same takes place in the instance of accessory images, which it is true do not altogether quit the real object, but still advance or extend from it, as half-substantial images, and hence can appear colored so quickly and so powerfully. That the prismatic appearance is in fact an pg 97 accessory image, we may convince ourselves in more than one mode. It corresponds exactly with the form of the object itself, whether the object be bounded by a straight line, or a curve indented, or waving. The form of the accessory image corresponds throughout exactly with the form of the object too. Again, not only the form but other qualities of the object are communicated to the accessory image. If the object is sharply relieved from its ground, like white on black, the colored accessory image in like manner appears in its greatest force. It is vivid, distinct, and powerful, but it is most especially powerful when a luminous object is shown on a dark ground, which may be contrived in various ways. But if the object is but faintly distinguished from the ground, like gray objects on black or white, or even on each other, the accessory image is also faint, and when the original difference of tint or force is slight, becomes hardly discernible. pg 98. The appearances which are observable when colored objects are relieved on light, dark, or colored grounds are moreover well worthy of attention in this case. A union takes place between the apparent color of the accessory image and the real color of the object. A compound color is the result which is either assisted and enhanced by the accordance or neutralized by the opposition of its ingredients. But the common and general characteristic, both of the double and accessory image, is semitransparence, the tendency of a transparent medium to become only half transparent or merely light transmitting, has been before adverted to 147-140. 8. Let the reader assume that he sees within, or through such a medium, a visionary image, and he will at once pronounce this latter to be a semi-transparent image. Thus the colors produced by refraction may be fitly explained by the doctrine of the semi-transparent mediums, for where dark passes over light, as the border of the semi-transparent accessory image advances, yellow appears, and on the other hand, where a light outline passes over the dark background, blue appears. 150-151. pg 99. The advancing foremost color is always the broader, thus the yellow spreads over the light with a broad border, but the yellowed appears as a narrower stripe, and is next the dark according to the doctrine of augmentation, as an effect of shade 3. On the opposite side, the condensed blue is next the edge, while the advancing border spreading as a thinner veil over the black produces the violet color, precisely on the principles before explained in treating of semi-transparent mediums principles, which will hereafter be found equally efficient in many other cases. Since an analysis like the present requires to be confirmed by ocular demonstration, we beg every reader to make himself acquainted with the experiments hitherto adduced, not in a superficial manner, but fairly and thoroughly. We have not placed arbitrary signs before him. Instead of the appearances themselves, no modes of expression are here proposed for his pg 100 adoption, which may be repeated forever without the exercise of thought, and without leading anyone to think, but we invite him to examine intelligible appearances, which must be present to the eye, and mind in order to enable him clearly to trace these appearances to their origin, and to explain them to himself and to others. Roman 16 Decrease of the appearance of color. We need only take the 5 conditions 210, under which the appearance of color increases in the contrary order, to produce the contrary or decreasing state. It may be as well, however, briefly to describe and review the corresponding modifications, which are presented to the eye. At the highest point of complete junction of the opposite edges, the colors appear as follows: 216. Yellowed blue, green red, blued yellow. pg 101. Where the junction is less complete, the appearance is as follows: 214, 215. Yellowed blue, yellow blued, green red, blue yellowed, blued yellow. Here therefore the surface still appears completely colored, but neither series is to be considered as an elementary series always developing itself in the same manner, and in the same degrees. On the contrary, they can and should be resolved into their elements, and in doing this, we become better acquainted with their nature and character. These elements, then, are 199, 200, 201. Yellowed blue, yellow blued, white black, blue yellowed, blued yellow. Here the surface itself, the original object which has been hitherto completely covered, and as it were lost again, appears in the center of the colors, asserts its right, and enables us pg 102 fully to recognize the secondary nature of the accessory images, which exhibit themselves as edges and borders. Note n. We can make these edges and borders as narrow as we please, nay, we can still have refraction in reserve, after having done away with all appearance of color at the boundary of the object. Having now sufficiently investigated the exhibition of color in this phenomenon, we repeat that we cannot admit it to be an elementary phenomenon. On the contrary, we have traced it to an antecedent, and a simpler one we have derived it, in connection with the theory of secondary images from the primordial phenomenon of light and darkness, as affected or acted upon by semi-transparent mediums. Thus prepared, we proceed to describe the appearances which refraction produces on gray and colored objects, and this will complete the section of subjective phenomena. pg 103. Roman 17 Gray objects displaced by refraction. Hitherto, we have confined our attention to black and white objects, relieved on respectively opposite grounds as seen through the prism. Because the colored edges and borders are most clearly displayed in such cases, we now repeat these experiments with gray objects, and again find similar results. As we called black the equivalent of darkness, and white the representative of light 18, so we now venture to say that gray represents half-shadow which partakes more or less of light and darkness, and thus stands between the two. We invite the reader to call to mind the following facts, as bearing on our present view. Gray objects appear lighter on a black than on a white ground. 33. They appear as a light on a black ground, and larger as a dark on the white ground, and smaller. 16. pg 104. The darker the gray, the more it appears as a faint light on black, as a strong dark on white, and vice versa. Hence, the accessory images of dark gray on black are faint on white strong, so the accessory images of light gray on white are faint on black strong. Gray on black seen through the prism will exhibit the same appearances as white on black. The edges are colored according to the same law, only the borders appear fainter. If we relieve gray on white, we have the same edges and borders which would be produced if we saw black on white through the prism. Note O. Various shades of gray placed next each other in gradation will exhibit at their edges either blue and violet only, or red and yellow only, according as the darker gray is placed over or under. A series of such shades of gray placed horizontally next each other will be colored conformably to the same law according as the whole series is relieved on a black or white ground above or below. pg 105. The observer may see the phenomena exhibited by the prism at one glance by enlarging the plate intended to illustrate this section 1. It is of great importance duly to examine and consider another experiment in which a gray object is placed partly on a black and partly on a white surface, so that the line of division passes vertically through the object. The colors will appear on this gray object in conformity with the usual law, but according to the opposite relation of the light to the dark, and will be contrasted in a line, for as the gray is as a light to the black, so it exhibits the red and yellow above the blue and violet below again. As the gray is as a dark to the white, the blue and violet appear above the red and yellow below. This experiment will be found of great importance with reference to the next chapter. Pg 106. Roman 18 colored objects displaced by refraction. An unlimited colored surface exhibits no prismatic color, in addition to its own hue, thus not at all differing from a black, white, or gray surface. To produce the appearance of color, light and dark boundaries must act on it either accidentally or by contrivance. Hence experiments and observations on colored surfaces, as seen through the prism, can only be made when such surfaces are separated by an outline from another differently tinted surface. In short, when circumscribed objects are colored. All colors, whatever they may be, correspond so far with gray that they appear darker than white and lighter than black. This shade-like quality of color has been already alluded to 69, and will become more and more evident if then we begin by placing colored objects on black and white surfaces, and examine them through the prism. We shall again have all that we have seen exhibited with gray surfaces. Plate 3. Pg 107. If we displace a colored object by refraction, there appears, as in the case of colorless objects, and according to the same laws, an accessory image. This accessory image retains, as far as color is concerned, its usual nature, and acts on one side as a blue and bluerd, on the opposite side as a yellow and yellowed. Hence, the apparent color of the edge and border will be either homogeneous with the real color of the object or not so. In the first case, the apparent image identifies itself with the real one and appears to increase it, while in the second case the real image may be vitiated, rendered indistinct, and reduced in size by the apparent image. We proceed to review the cases in which these effects are most strikingly exhibited. If we take a colored drawing enlarged from the plate, which illustrates this experiment 1, and examine the red and blue squares, placed next each other on a black ground through the prism, as usual we shall find that as both colors are lighter than the ground, similarly colored edges and borders will appear above and below Pg 108 at the outlines of both only. They will not appear equally distinct to the eye. Red is proportionally much lighter on black than blue, the colors of the edges will therefore appear stronger on the red than on the blue, which here acts as a dark gray, but little different from black. 251. The extreme red edge will identify itself with the vermilion color of the square, which will thus appear a little elongated in this direction, while the yellow border immediately underneath it only gives the red surface a more brilliant appearance, and is not distinguished without attentive observation. On the other hand, the red edge and yellow border are heterogeneous with the blue square. A dull red appears at the edge, and a dull green mingles with the figure, and thus the blue square seems at a hasty glance to be comparatively diminished on this side. At the lower outline of the two squares, a blue edge and a violet border will appear, and will Pg 109 produce the contrary effect, for the blue edge, which is heterogeneous with the warm red surface, will vitiate it, and produce a neutral color, so that the red on this side appears comparatively reduced and driven upwards, and the violet border on the black is scarcely perceptible. On the other hand, the blue apparent edge will identify itself with the blue square, and not only not reduce, but extend it, the blue edge, and even the violet border next it have the apparent effect of increasing the surface and elongating it in that direction. The effect of homogeneous and heterogeneous edges, as I have now minutely described it, is so powerful and singular that the two squares at the first glance seem pushed out of their relative horizontal position and moved in opposite directions, the red upwards, the blue downwards. But no one who is accustomed to observe experiments in a certain succession, and respectively to connect and trace them, will suffer himself to be deceived by such an unreal effect. A just impression with regard to this important Pg 110 phenomenon will, however, much depend on some nice and even troublesome conditions, which are necessary to produce the illusion in question. Paper should be tinged with vermilion or the best minium for the red square, and with deep indigo for the blue square. The blue and red prismatic edges will then unite imperceptibly with the real surfaces, where they are respectively homogeneous. Where they are not, they vitiate the colors of the squares without producing a very distinct middle tint. The real red should not incline too much to yellow, otherwise the apparent deep red edge above will be too distinct. At the same time, it should be somewhat yellow, otherwise the transition to the yellow border will be too observable, the blue must not be light otherwise the red edge will be visible. And the yellow border will produce a too decided green, while the violet border underneath would not give us the impression of being part of an elongated light blue square. All this will be treated more circumstantially hereafter, when we speak of the apparatus, intended to facilitate the experiments connected with this part of our subject. 2. Every inquirer pg 111 should prepare the figures himself in order fairly to exhibit this specimen of ocular deception, and at the same time to convince himself that the colored edges, even in this case, cannot escape accurate examination. Meanwhile, various other combinations, as exhibited in the plate, are fully calculated to remove all doubt on this point in the mind of every attentive observer. If, for instance, we look at a white square next the blue one on a black ground, the prismatic hues of the opposite edges of the white, which here occupies the place of the red in the former experiment, will exhibit themselves in their utmost force. The red edge extends itself above the level of the blue, almost in a greater degree than was the case with the red square itself in the former experiment. The lower blue edge again is visible in its full force next the white, while on the other hand it cannot be distinguished next the blue square. The violet border underneath is also much more apparent on the white than on the blue. If the observer now compares these double PG 112 squares, carefully prepared, and arranged one above the other, the red with the white, the two blue squares together, the blue with the red, the blue with the white, he will clearly perceive the relations of these surfaces to their colored edges and borders. The edges and their relations to the colored surfaces appear still more striking if we look at the colored squares and a black square on a white ground, for in this case, the illusion before mentioned ceases altogether, and the effect of the edges is as visible as in any case that has come under our observation. Let the blue and red squares be first examined through the prism. In both, the blue edge now appears above this edge homogeneous with the blue surface unites with it, and appears to extend it upwards. Only the blue edge, owing to its lightness, is somewhat too distinct in its upper portion, the violet border underneath. It is also sufficiently evident on the blue. The apparent blue edge is on the other hand heterogeneous with the red square. It is neutralized by contrast, and is scarcely visible. Meanwhile, the violet border, uniting with the real red, produces a hue resembling that of the peach blossom. If thus, owing to the above causes, the upper PG 113 outlines of these squares do not appear level with each other, the correspondence of the under outlines is the more observable, for since both colors, the red and the blue, are darks compared with the white, as in the former case they were light compared with the black, the red edge with its yellow border appears very distinctly under both. It exhibits itself under the warm red surface in its full force, and under the dark blue nearly as it appears under the black, as may be seen if we compare the edges and borders of the figures placed one above the other on the white ground. In order to present these experiments with the greatest variety and perspicuity, squares of various colors are so arranged 3 that the boundary of the black and white passes through them vertically according to the laws now known to us, especially in their application to colored objects. We shall find the squares as usual doubly colored. At each edge each square will appear to be split in two, and to be elongated upwards or downwards. We may here call to mind the experiment with the gray figure seen in like manner on the line of division between black and white 2574. PG 114. A phenomenon was before exhibited even to illusion in the instance of a red and blue square on a black ground. In the present experiment, the elongation upwards and downwards of two differently colored figures is apparent in the two halves of one and the same figure of one and the same color. Thus we are still referred to the colored edges and borders, and to the effects of their homogeneous and heterogeneous relations with respect to the real colors of the objects. I leave it to observers themselves to compare the various gradations of colored squares placed half on black, half on white, only inviting their attention to the apparent alteration, which takes place in contrary directions. For red and yellow appear elongated upwards, if on a black ground downwards, if on a white blue downwards, if on a black ground upwards, if on a white, all which however is quite in accordance with the diffusely detailed examples above given. Let the observer now turn the figures so that the beforementioned squares placed on the line of division between black and white may be in a horizontal series, the black above the white, underneath. On looking at these squares, PG 115, through the prism he will observe that the red square gains by the addition of two red edges. On more accurate examination, he will observe the yellow border on the red figure, and the lower yellow border upon the white will be perfectly apparent. The upper red edge on the blue square is, on the other hand, hardly visible the yellow border. Next, it produces a dull green by mingling with the figure. The lower red edge and the yellow border are displayed in lively colors. After observing that the red figure in these cases appears to gain by an addition on both sides, while the dark blue on one side at least loses, something we shall see the contrary effect produced by turning the same figures upside down, so that the white ground be above the black below. For as the homogeneous edges and borders now appear above and below the blue square, this appears elongated, and a portion of the surface itself seems even more brilliantly colored. It is only by attentive observation that we can distinguish the edges and borders from the color of the figure itself. Pg 116. The yellow and red squares, on the other hand, are comparatively reduced by the heterogeneous edges in this position of the figures, and their colors are to a certain extent vitiated. The blue edge in both is almost invisible. The violet border appears as a beautiful peach blossom hue on the red, as a very pale color of the same kind on the yellow. Both the lower edges are green dull on the red, vivid on the yellow. The violet border is but faintly perceptible under the red, but is more apparent under the yellow. Every inquirer should make it a point to be thoroughly acquainted with all the appearances here adduced, and not consider it irksome to follow out a single phenomenon through so many modifying circumstances. These experiments, it is true, may be multiplied to infinity by differently colored figures, upon and between differently colored grounds. Under all such circumstances, however, it will be evident to every attentive observer that colored squares only appear relatively altered, or elongated, or reduced by the prism, because an addition of homogeneous or heterogeneous edges produces an illusion. The inquirer will now be enabled to do away with this illusion, if he has the Pg 117 patience, to go through the experiments one after the other, always comparing the effects together, and satisfying himself of their correspondence. Experiments with colored objects might have been contrived in various ways, why they have been exhibited precisely in the above mode, and with so much minuteness will be seen hereafter. The phenomena, although formerly not unknown, were much misunderstood, and it was necessary to investigate them thoroughly to render some portions of our intended historical view clearer. In conclusion, we will mention a contrivance by means of which our scientific readers may be enabled to see these appearances distinctly at one view, and even in their greatest splendor. Cut in a piece of pasteboard 5 perfectly similar square openings of about an inch next each other exactly in a horizontal line. Behind these openings place 5 colored glasses in the natural order orange, yellow, green, blue, violet. Let the series thus adjusted be fastened in an opening of the camera obscura, so that the bright sky may be seen through the squares, or that the sun may shine on them. They will thus appear very powerfully colored. Let the spectator now examine them through the prism, and observe the appearances, already Pg 118 familiar, by the foregoing experiments with colored objects, namely the partly assisting, partly neutralizing effects of the edges and borders, and the consequent apparent elongation or reduction of the colored squares with reference to the horizontal line. The results witnessed by the observer in this case entirely correspond with those in the cases before analyzed. We do not therefore go through them again in detail, especially as we shall find frequent occasions hereafter to return to the subject. Note P. Roman 19. Achromatism and hyperchromatism. Formerly, when much that is regular and constant in nature was considered as mere aberration and accident, the colors arising from refraction were but little attended to, and were looked upon as an appearance attributable to particular local circumstances. But after it had been assumed that this appearance of color accompanies refraction at all times, it was natural that it should be considered as intimately and exclusively connected with that phenomenon. The belief obtaining that the Pg 119 measure of the colored appearance was in proportion to the measure of the refraction, and that they must advance pari passu with each other. If again philosophers ascribed the phenomenon of a stronger or weaker refraction, not indeed wholly, but in some degree to the different density of the medium, as purer atmospheric air, charged with vapors, water, glass, according to their increasing density, increased the so-called refraction or displacement of the object, so they could hardly doubt that the appearance of color must increase in the same proportion, and hence took it for granted in combining different mediums, which were to counteract refraction, that as long as refraction existed, the appearance of color must take place, and that as soon as the color disappeared, the refraction also must cease. Afterwards, it was however discovered that this relation, which was assumed to correspond, was in fact dissimilar, that two mediums can refract an object with equal power, and yet produce very dissimilar colored borders. It was found that in addition to the physical principle to which refraction was ascribed, a pg 120 chemical one was also to be taken into the account. We propose to pursue this subject hereafter in the chemical division of our inquiry, and we shall have to describe the particulars of this important discovery in our history of the doctrine of colors. What follows may suffice for the present. In mediums of similar or nearly similar refracting power, we find the remarkable circumstance that a greater and lesser appearance of color can be produced by a chemical treatment. The greater effect is owing namely to acids, the lesser to alkalis. If metallic oxides are introduced into a common mass of glass, the colored appearance through such glasses becomes greatly increased, without any perceptible change of refracting power. That the lesser effect again is produced by alkalis may be easily supposed. Those kinds of glass which were first employed after the discovery are called flint and crown glass. The first produces the stronger, the second, the fainter appearance of color. We shall make use of both these denominations as technical terms in our present statement pg 121, and assume that the refractive power of both is the same, but that flint glass produces the colored appearance more strongly by 1/3 than the crown glass. The diagram plate 3 fig 2 may serve in illustration. A black surface is here divided into compartments for more convenient demonstration. Let the spectator imagine 5 white squares between the parallel lines a B and C Roman 500. The square No 1 is presented to the naked eye unmoved from its place. But let the square No 2 seen through a crownglass prism, G, be supposed to be displaced by refraction 3 compartments, exhibiting the colored borders to a certain extent again. Let the square No 3 seen through a flint glass prism H in like manner be moved downwards 3 compartments, when it will exhibit the colored borders by about 1/3 wider than No 2. Again, let us suppose that the square No 4 has like No 2 been moved downwards 3 compartments by a prism of crown glass, and that then, by an oppositely placed prism H of pg 122 flint glass, it has been again raised to its former situation where it now stands. Here it is true the refraction is done away with by the opposition of the two, but as the prism H in displacing the square by refraction through 3 compartments produces colored borders wider by 1/3 than those produced by the prism G, so notwithstanding the refraction is neutralized, there must be an excess of colored border, remaining the position of this color as usual depends on the direction of the apparent motion 204 communicated to the square by the prism H, and consequently, it is the reverse of the appearance in the two squares 2 and 3, which have been moved in an opposite direction. This excess of color we have called hyperchromatism, and from this, the achromatic state may be immediately arrived at. For assuming that it was the square No 5, which was removed 3 compartments from its first supposed place, like No 2 by a prism of crownglass G, it would only be necessary to reduce the angle of a prism of flint glass H, and to connect it reverse to the prism G, in order to raise the square No 5 2 degrees, or compartments, by which means the hyperchromatism pg 123 of the first case would cease. The figure would not quite return to its first position, and yet be already colorless. The prolonged lines of the united prisms under No 5 show that a single complete prism remains again. We have only to suppose the lines curved, and an object glass presents itself. Such is the principle of the achromatic telescopes. For these experiments, a small prism composed of 3 different prisms, as prepared in England, is extremely well adapted. It is to be hoped our own opticians will in future enable every friend of science to provide himself with this necessary instrument. Roman 20. Advantages of subjective experiments. Transition to the objective. We have presented the appearances of color as exhibited by refraction, first by means of subjective experiments, and we have so far arrived at a definite result that we have been enabled to deduce the phenomena in question pg 124 from the doctrine of semi-transparent mediums and double images. In statements which have reference to nature, everything depends on ocular inspection, and these experiments are the more satisfactory as they may be easily and conveniently made. Every amateur can procure his apparatus without much trouble or cost, and if he is a tolerable adept in pasteboard contrivances, he may even prepare a great part of his machinery himself. A few plain surfaces on which black, white, gray, and colored objects may be exhibited alternately on a light and dark ground are all that is necessary. The spectator fixes them before him, examines the appearances at the edge of the figures conveniently, and as long as he pleases he retires to a greater distance, again approaches, and accurately observes the progressive states of the phenomena. Besides this, the appearances may be observed with sufficient exactness through small prisms, which need not be of the purest glass. The other desirable requisites in these glass instruments will however be pointed out in the section which treats of the apparatus 1. Pg 125. A great advantage in these experiments, again, is that they can be made at any hour of the day, in any room, whatever aspect it may have. We have no need to wait for sunshine, which in general is not very propitious to northern observers. Objective experiments. The objective experiments, on the contrary, necessarily require the sunlight, which even when it is to be had may not always have the most desirable relation with the apparatus placed opposite to it. Sometimes the sun is too high, sometimes too low, and withal only a short time in the meridian of the best situated room, it changes its direction during the observation. The observer is forced to alter his own position and that of his apparatus, in consequence of which the experiments in many cases become uncertain. If the sun shines through the prism, it exhibits all inequalities, lines, and bubbles in the glass, and thus the appearance is rendered confused, dim, and discolored. Yet both kinds of experiments must be investigated with equal accuracy. They appear to Pg 126 be opposed to each other, and yet are always parallel. What one order of experiments exhibits, the other exhibits likewise, and yet each has its peculiar capabilities, by means of which certain effects of nature are made known to us in more than one way. In the next place, there are important phenomena which may be exhibited by the union of subjective and objective experiments. The latter experiments, again, have this advantage, that we can in most cases represent them by diagrams, and present to view the component relations of the phenomena. In proceeding, therefore, to describe the objective experiments, we shall so arrange them that they may always correspond with the analogous subjective examples. For this reason, too, we annex to the number of each paragraph the number of the former corresponding 1, but we set out by observing generally that the reader must consult the plates, that the scientific investigator must be familiar with the apparatus, in order that the twin phenomena in one mode or the other may be placed before them. Pg 127. Roman 21. Refraction without the appearance of color. 306, 195, 196. That refraction may exhibit its effects without producing an appearance of color is not to be demonstrated so perfectly in objective as in subjective experiments. We have it as true unlimited spaces, which we can look at through the prism, and thus convince ourselves that no color appears where there is no boundary, but we have no unlimited source of light, which we can cause to act through the prism. Our light comes to us from circumscribed bodies, and the sun, which chiefly produces our prismatic appearances, is itself only a small circumscribed luminous object. We may, however, consider every larger opening through which the sun shines, every larger medium through which the sunlight is transmitted and made to deviate from its course, as so far unlimited that we can confine our attention to the center of the surface without considering its boundaries. 308, 197. If we place a large water prism in the sun, a Pg 128 large bright space is refracted upwards by it on the plane intended to receive the image, and the middle of this illumined space will be colorless. The same effect may be produced if we make the experiment with glass prisms having angles a few degrees. The appearance may be produced even through glass prisms whose refracting angle is 60 degrees, provided we place the recipient surface near enough. Roman 22. Conditions of the appearance of color. 309, 198. Although then the illumined space before mentioned appears indeed refracted and moved from its place, but not colored, yet on the horizontal edges of this space we observe a colored appearance, that here again the color is solely owing to the displacement of a circumscribed object, may require to be more fully proved. The luminous body which here acts is circumscribed. The sun, while it shines and diffuses light, is still an insulated object, however small the opening in the lid of a camera obscura be made still the whole image of the sun, will pg 129 penetrate it. The light which streams from all parts of the sun's disk will cross itself in the smallest opening and form the angle which corresponds with the sun's apparent diameter on the outside. We have a cone narrowing to the orifice within this apex, spreads again, producing on an opposite surface a round image, which still increases in size in proportion to the distance of the recipient surface from the apex. This image, together with all other objects of the external landscape, appears reversed on the white surface in question in a dark room. How little, therefore, we have here to do with single sunrays bundles, or fasces of rays, cylinders of rays, pencils, or whatever else of the kind may be imagined, is strikingly evident for the convenience of certain diagrams. The sunlight may be assumed to arrive in parallel lines, but it is known that this is only a fiction quite allowable, where the difference between the assumption and the true appearance is unimportant. But we should take care not to suffer such a postulate to be equivalent to a fact, and proceed to further operations on such a fictitious basis. Let the aperture in the window shutter be now enlarged at pleasure, let it be made round pg 130 or square, nay, let the whole shutter be opened, and let the sun shine into the room through the whole window. The space which the sun illumines will always be larger according to the angle which its diameter makes, and thus even the whole space illumined by the sun through the largest window is only the image of the sun, plus the size of the opening. We shall hereafter have occasion to return to this. 312, 199. If we transmit the image of the sun through convex glasses, we contract it towards the focus in this case, according to the laws before explained. A yellow border and a yellowed edge must appear when the spectrum is thrown on white paper. But as this experiment is dazzling and inconvenient, it may be made more agreeably with the image of the full moon. On contracting this orb by means of a convex glass, the colored edge appears in the greatest splendor, for the moon transmits a mitigated light in the first instance, and can thus the more readily produce color which, to a certain extent, accompanies the subduing of light at the same time. The eye of the observer is only gently and agreeably excited. 313, 200. If we transmit a luminous image through concave pg 131 glasses, it is dilated. Here the image appears edged with blue. The two opposite appearances may be produced by a convex glass simultaneously, or in succession simultaneously, by fastening an opaque disc in the center of the convex glass, and then transmitting the sun's image, in this case the luminous image, and the black disc within it, are both contracted, and consequently the opposite colors must appear again. We can present this contrast in succession by first contracting the luminous image towards the focus, and then suffering it to expand again beyond the focus, when it will immediately exhibit a blue edge. 315, 201. Here too what was observed in the subjective experiments is again to be remarked, namely, that blue and yellow appear in and upon the white, and that both assume a reddish appearance in proportion as they mingle with the black. 316, 202, 203. These elementary phenomena occur in all subsequent objective experiments, as they constituted the groundwork of the subjective ones. pg 132. The process, too, which takes place, is the same. A light boundary is carried over a dark surface. A dark surface is carried over a light boundary. The edges must advance, and as it were push over each other in these experiments as in the former ones. 317, 204. If we admit the sun's image through a larger or smaller opening into the dark room, if we transmit it through a prism, so placed that its refracting angle as usual is underneath the luminous image, instead of proceeding in a straight line to the floor, is refracted upwards on a vertical surface, placed to receive it. This is the moment to take notice of the opposite modes, in which the subjective and objective refractions of the object appear. If we look through a prism held with its refracting angle underneath at an object above us, the object is moved downwards, whereas a luminous image refracted through the same prism is moved upwards. This, which we here merely mention as a matter of fact for the sake of brevity, is easily explained by the laws of refraction and elevation. pg 133. The luminous object being moved from its place in this manner, the colored borders appear in the order, and according to the laws before explained, the violet border is always foremost, and thus, in objective cases, proceeds upwards, in subjective cases downwards. 320-205. The observer may convince himself in like manner of the mode, in which the appearance of color takes place in the diagonal direction, when the displacement is effected by means of two prisms, as has been plainly enough shown in the subjective example for this experiment. However, prisms should be procured of few degrees, say about 15. 321-206-207. That the coloring of the image takes place here too according to the direction in which it moves will be apparent if we make a square opening of moderate size in a shutter, and cause the luminous image to pass through a water prism, the spectrum being moved first in the horizontal and vertical directions. Then diagonally, the colored edges will change their position accordingly. pg 134. 322-208. Whence it is again evident that to produce color the boundaries must be carried over each other, not merely move side by side. Roman 23, Conditions of the increase of color. 323-209. Here too, an increased displacement of the object produces a greater appearance of color. 324-210. This increased displacement occurs by a more oblique direction of the impinging luminous object through mediums with parallel surfaces, by changing the parallel form for one more or less acute angled, by increased proportion of the medium, whether parallel or acute angled partly, because the object is by this means more powerfully displaced partly, because an effect depending on the mere mass cooperates, by the distance of the recipient surface from the refracting medium, so that the colored pg 135 spectrum emerging from the prism may be said to have a longer way to travel. When a chemical property produces its effects under all these circumstances, this we have already entered into more fully under the head of achromatism and hyperchromatism. 325-211. The objective experiments have this advantage that the progressive states of the phenomenon may be arrested and clearly represented by diagrams, which is not the case with the subjective experiments. We can observe the luminous image after it has emerged from the prism step by step, and mark its increasing color by receiving it on a plane at different distances, thus exhibiting before our eyes various sections of this cone. With an elliptical base, again the phenomenon may at once be rendered beautifully visible throughout its whole course. In the following manner, let a cloud of fine white dust be excited along the line in which the image passes through the dark space. The cloud is best produced by fine, perfectly dry hair powder. The more or less colored appearance will now be painted on the white atoms, and presented in pg 136 its whole length and breadth to the eye of the spectator. By this means, we have prepared some diagrams which will be found among the plates in these. The appearance is exhibited from its first origin, and by these the spectator can clearly comprehend why the luminous image is so much more powerfully colored through prisms than through parallel mediums. 328-212. At the two opposite outlines of the image, an opposite appearance presents itself beginning from an acute angle. The appearance spreads, as it proceeds further in space, according to this angle on one side in the direction in which the luminous image is moved. A violet border advances on the dark, a narrower blue edge remains next the outline of the image on the opposite side, a yellow border advances into the light of the image itself, and a yellowed edge remains at the outline. 329-213. Here therefore the movement of the dark against the light against the dark may be clearly observed. Plate 4's pg 137. 330-214. The center of a large object remains long uncolored, especially with mediums of less density and smaller angles, but at last the opposite borders and edges touch each other, upon which a green appears in the center of the luminous image. 330-215. Objective experiments have been usually made with the sun's image. An objective experiment with a dark object has hitherto scarcely been thought of. We have, however, prepared a convenient contrivance for this also. Let the large water prism before alluded to be placed in the sun, and let a round pasteboard disc be fastened either inside or outside. The colored appearance will again take place at the outline beginning according to the usual law. The edges will appear, they will spread in the same proportion, and when they meet red will appear in the center too, An intercepting square may be added near the round disc, and placed in any direction ad libitum, and the spectator can again convince himself of what has been before so often described. 330 to 216. If we take away these dark objects from the PG 138 prism, in which case, however, the glass is to be carefully cleaned, and hold a rod or a large pencil before the center of the horizontal prism, we shall then accomplish the complete immixture of the violet border and the yellowed edge, and see only the three colors, the external blue and yellow, and the central red. If again we cut a long horizontal opening in the middle of a piece of pasteboard fastened on the prism, and then cause the sunlight to pass through it, we shall accomplish the complete union of the yellow border with the blue edge upon the light, and only see yellowed green and violet. The details of this are further entered into in the description of the plates. 334-217. The prismatic appearance is thus by no means complete and final when the luminous image emerges from the prism. It is then only that we perceive its elements in contrast, for as it increases, these contrasting elements unite, and are at last intimately joined. The section of this phenomenon arrested on a plane surface is different at every degree of distance from the prism, so that the notion of an immutable series of colors, or of a pervading similar proportion between them, cannot be a question for a moment. PG 139. Roman 24. Explanation of the foregoing phenomena. 330-218. As we have already entered into this analysis circumstantially, while treating of the subjective experiments as all that was of force, there is equally valid here, it will require no long details, in addition to show that the phenomena which are entirely parallel in the two cases may also be traced precisely to the same sources. 336-219. That in objective experiments also we have to do with circumscribed images has been already demonstrated at large. The sun may shine through the smallest opening, yet the image of the whole disk penetrates beyond the largest prism, may be placed in the open sunlight, yet it is still the sun's image that is bounded by the edges of the refracting surfaces, and produces the accessory images of this boundary. We may fasten pasteboard with many openings cut in it before the water prism, yet we still merely see multiplied images, which after having been moved from their place by refraction exhibit colored edges and borders, and in these mere accessory images. PG 140. 330-235. In subjective experiments, we have seen that objects strongly relieved from each other produce a very lively appearance of color, and this will be the case in objective experiments in a much more vivid and splendid degree. The sun's image is the most powerful brightness we know, hence its accessory image will be energetic in proportion, and notwithstanding its really secondary dimmed and darkened character, must be still very brilliant. The colors thrown by the sunlight through the prism on any object carry a powerful light with them, for they have the highest and most intense source of light as it were for their ground. That we are warranted in calling even these accessory images semi-transparent, thus deducing the appearances from the doctrine of the semi-transparent mediums, will be clear to everyone who has followed us thus far, but particularly to those who have supplied themselves with the necessary apparatus, so as to be enabled at all times to witness the precision and vivacity with which semi-transparent mediums act. PG 141. Roman 25. Decrease of the appearance of color. 339-243. If we could afford to be concise in the description of the decreasing colored appearance in subjective cases, we may here be permitted to proceed with still greater brevity, while we refer to the former distinct statement. One circumstance, only on account of its great importance, may be here recommended to the reader's especial attention, as a leading point of our whole thesis. 340-244-247. The decline of the prismatic appearance must be preceded by its separation by its resolution into its elements, at a due distance from the prism, the image of the sun being entirely colored. The blue and yellow at length mix completely, and we see only yellowed green and bluard. If we bring the recipient surface nearer to the refracting medium, yellow and blue appear again, and we see the five colors with their gradations at a still shorter distance, the yellow and blue separate from each other entirely. The green vanishes, and the image itself appears colorless between the colored edges and borders. The nearer we bring the recipient surface to the prism, the PG 142, narrower the edges and borders become, till at last when in contact with the prism they are reduced to nothing. Roman 26 Gray objects. 340, 1-218. We have exhibited gray objects as very important to our inquiry in the subjective experiments. They show, by the faintness of the accessory images, that these same images are in all cases derived from the principal object. If we wish here too to carry on the objective experiments parallel with the others, we may conveniently do this by placing a more or less dull ground glass before the opening through which the sun's image enters. By this means, a subdued image would be produced, which on being refracted would exhibit much duller colors on the recipient plane than those immediately derived from the sun's disk. And thus even from the intense unimage, only a faint accessory image would appear proportioned to the mitigation of the light. By the glass this experiment, it is true, will only again and again confirm what is already sufficiently familiar to us. Pg 143. Roman 27 Colored objects. 340-260. There are various modes of producing colored images in objective experiments. In the first place, we can fix colored glass before the opening, by which means a colored image is at once produced. Secondly, we can fill the water prism with colored fluids. Thirdly, we can cause the colors already produced in their full vivacity by the prism to pass through proportionate small openings in a tin plate, and thus prepare small circumscribed colors for a second operation. This last mode is the most difficult, for owing to the continual progress of the sun, the image cannot be arrested in any direction at will. The second method has also its inconveniences, since not all colored liquids can be prepared perfectly bright and clear on these accounts. The first is to be preferred, and deserves the more to be adopted, because natural philosophers have hitherto chosen to consider the colors produced from the sunlight through the prism, those produced through liquids and glasses, and those which are already fixed on paper or cloth, as exhibiting effects equally to be depended on and equally available in demonstration. As it is thus merely necessary that the image Pg 144 should be colored, so the large water prism before alluded to affords us the best means of effecting this. A pasteboard screen may be contrived to slide before the large surfaces of the prism, through which, in the first instance, the light passes. Uncolored in this screen, openings of various forms may be cut in order to produce different images, and consequently different accessory images. This being done, we need only fix colored glasses before the openings, in order to observe what effect refraction produces on colored images in an objective sense. A series of glasses may be prepared in a mode similar to that before described. 284. These should be accurately contrived to slide in the grooves of the large water prism. Let the sun then shine through them, and the colored images refracted upwards will appear bordered and edged, and will vary accordingly, for these borders and edges will be exhibited quite distinctly on some images, and on others will be mixed with the specific color of the glass, which they will either enhance or neutralize. Every observer will be enabled to convince himself here again that we have only to do with the same simple phenomenon, so circumstantially described subjectively and objectively. Pg 145. Roman 28 Achromatism and hyperchromatism. 340, 5-280, 5-290. It is possible to make the hyperchromatic and achromatic experiments objectively as well as subjectively. After what has been already stated, a short description of the method will suffice, especially as we take it for granted that the compound prism before mentioned is in the hands of the observer. Let the sun's image pass through an acute-angled prism of few degrees, prepared from crownglass, so that the spectrum be refracted upwards on an opposite surface. The edges will appear colored according to the constant law, namely the violet and blue above and outside, the yellow and yellowed below, and within the image, as the refracting angle of this prism is undermost, let another proportionate prism of flintglass be placed against it with its refracting angle uppermost. The sun's image will, by this means, be again moved to its place, where, owing to the excess of the coloring power of the prism of flintglass, it will still appear a little colored, and in consequence of the direction in which it has been moved, the blue and violet Pg 146 will now appear underneath and outside the yellow and yellowed above and inside. If the whole image be now moved a little upwards by a proportionate prism of crownglass, the hyperchromatism will disappear. The sun's image will be moved from its place, and yet will appear colorless. With an achromatic object glass composed of 3 glasses, this experiment may be made step by step, if we do not mind taking out the glasses from their setting, the 2 convex glasses of crown glass, in contracting the sun's image towards the focus, the concave glass of flint glass, in dilating the image beyond it exhibit at the edges the usual colors. A convex glass united with a concave one exhibits the colors according to the law of the latter. If all 3 glasses are placed together, whether we contract the sun's image towards the focus, or suffer it to dilate beyond the focus, colored edges never appear, and the achromatic effect intended by the optician is in this case again attained. But as the crown glass has always a greenish tint, and as a tendency to this, hue may be more pg 147 decided in large and strong object glasses, and under certain circumstances, produce the compensatory red, which however in repeated experiments with several instruments of this kind, did not occur to us philosophers have resorted to the most extraordinary modes of explaining such a result, and having been compelled in support of their system, theoretically, to prove the impossibility of achromatic telescopes, have felt a kind of satisfaction in having some apparent ground for denying so great an improvement of this. However, we can only treat circumstantially in our historical account of these discoveries. Roman 29 Combination of subjective and objective experiments. Having shown above 318 that refraction considered objectively and subjectively must act in opposite directions, it will follow that if we combine the experiments the effects will reciprocally destroy each other. Let the sun's image be thrown upwards on a pg 148 vertical plane through a horizontally placed prism. If the prism is long enough to admit of the spectator also looking through it, he will see the image elevated by the objective refraction again depressed, and in the same place in which it appeared without refraction. Here a remarkable case presents itself, but at the same time, a natural result of a general law, for since as often before stated the objective sun's image thrown on the vertical plane is not an ultimate or unchangeable state of the phenomenon, so in the above operation, the image is not only depressed when seen through the prism, but its edges and borders are entirely robbed of their hues, and the spectrum is reduced to a colorless circular form. By employing 2 perfectly similar prisms, placed next each other for this experiment, we can transmit the sun's image through one and look through the other. If the spectator advances nearer with the prism through which he looks, the image is again elevated, and by degrees becomes colored according to the law of the first prism. If he pg 149 again retires, till he has brought the image to the neutralized point, and then retires still farther away, the image which had become round and colorless moves still more downwards, and becomes colored in the opposite sense, so that if we look through the prism, and upon the refracted spectrum at the same time, we see the same image colored according to subjective and objective laws. The modes in which this experiment may be varied are obvious. If the refracting angle of the prism through which the sun's image was objectively elevated is greater than that of the prism through which the observer looks, he must retire to a much greater distance in order to depress the colored image so low on the vertical plane that it shall appear colorless, and vice versa. It will be easily seen that we may exhibit achromatic and hyperchromatic effects in a similar manner, and we leave it to the amateur to follow out such researches, more fully other complicated experiments in which prisms and lenses are employed. Together others again, in which objective and subjective experiments are variously intermixed, we reserve for a future pg 150 occasion, when it will be our object to trace such effects to the simple phenomena with which we are now sufficiently familiar. Roman 30 Transition. In looking back on the description and analysis of dioptrical colors, we do not repent either that we have treated them so circumstantially, or that we have taken them into consideration before the other physical colors out of the order we ourselves laid down. Yet before we quit this branch of our inquiry, it may be as well to state the reasons that have weighed with us. If some apology is necessary for having treated the theory of the dioptrical colors, particularly those of the second class, so diffusely, we should observe that the exposition of any branch of knowledge is to be considered partly with reference to the intrinsic importance of the subject, and partly with reference to the particular necessities of the time in which the pg 151 inquiry is undertaken. In our own case, we were forced to keep both these considerations constantly in view In the first place, we had to state a mass of experiments, with our consequent convictions. Next, it was our especial aim to exhibit certain phenomena known, it is true, but misunderstood, and above all exhibited in false connection, in that natural and progressive development, which is strictly and truly conformable to observation, in order that hereafter in our polemical or historical investigations, we might be enabled to bring a complete preparatory analysis, to bear on and elucidate our general view. The details we have entered into were on this account unavoidable, they may be considered as a reluctant consequence of the occasion hereafter when philosophers will look upon a simple principle as simple a combined effect as combined when they will acknowledge the first elementary and the second complicated states for what they are then, indeed. All this statement may be abridged to a narrower form, a labor, which should we ourselves not be able to accomplish it, we bequeath to the active interest of contemporaries and posterity. With respect to the order of the chapters, it should be remembered that natural phenomena pg 152, which are even allied to each other, are not connected in any particular sequence or constant series. Their efficient causes act in a narrow circle, so that it is in some sort indifferent what phenomenon is first or last. Considered, the main point is that all should be as far as possible present to us in order that we may embrace them at last from one point of view, partly according to their nature, partly according to generally received methods. Yet in the present particular instance, it may be asserted that the dioptrical colors are justly placed at the head of the physical colors, not only on account of their striking splendor and their importance in other respects, but because in tracing these to their source much was necessarily entered into, which will assist our subsequent inquiries. For hitherto light has been considered as a kind of abstract principle existing and acting independently, to a certain extent self-modified, and on the slightest cause producing colors out of itself, to divert the votaries of physical science from this mode of viewing the subject, to make them attentive to the fact that in prismatic and other appearances, we have not to do pg 153 with light as an uncircumscribed and modifying principle, but as circumscribed and modified that we have to do with a luminous image with images or circumscribed objects. Generally, whether light or dark, this was the purpose we had in view, and such is the problem to be solved. All that takes place in dioptrical case, especially those of the second class, which are connected with the phenomena of refraction, is now sufficiently familiar to us, and will serve as an introduction to what follows. Catoptrical appearances remind us of the physiological phenomena, but as we ascribe a more objective character to the former, we thought ourselves justified in classing them with the physical examples. It is of importance, however, to remember that here again, it is not light in an abstract sense, but a luminous image that we have to consider. In proceeding onwards to the paroptrical class, the reader, if duly acquainted with the foregoing facts, will be pleased to find himself once more in the region of circumscribed forms, the shadows of bodies, especially as secondary pg 154 images, so exactly accompanying the object, will serve greatly to elucidate analogous appearances. We will not, however, anticipate these statements, but proceed as heretofore in what we consider the regular course. Roman 30. 1. Catoptrical colors. Catoptrical colors are such as appear in consequence of a mirror-like reflection. We assume in the first place that the light itself, as well as the surface from which it is reflected, is perfectly colorless. In this sense, the appearances in question come under the head of physical colors. They arise in consequence of reflection, as we found the dioptrical colors of the second class appear by means of refraction. Without further general definitions, we turn our attention at once to particular cases, and to the conditions which are essential to the exhibition of these phenomena. pg 155. If we unroll a coil of bright steel wire, and after suffering it to spring confusedly together again, place it at a window in the light, we shall see the prominent parts of the circles and convolutions illumined, but neither resplendent nor iridescent. But if the sun shines on the wire, this light will be condensed into a point, and we perceive a small, resplendent image of the sun, which when seen near exhibits no color. On retiring a little, however, and fixing the eyes on this refulgent appearance, we discern several small mirrored suns colored in the most varied manner. And although the impression is that green and red predominate, yet, on a more accurate inspection, we find that the other colors are also present. If we take an eyeglass and examine the appearance through it, we find the colors have vanished as well as the radiating splendor in which they were seen, and we perceive only the small luminous points, the repeated images of the sun. We thus find that the impression is subjective in its nature, and that the appearance is allied to those which we have adverted to under the name of radiating halos 100. pg 156. We can, however, exhibit this phenomenon objectively. Let a piece of white paper be fastened beneath a small aperture in the lid of a camera obscura, and when the sun shines through this aperture, let the confusedly rolled steel wire be held in the light, so that it be opposite to the paper. The sunlight will impinge on and in the circles of the wire, and will not as in the concentrating lens of the eye display itself in a point, but as the paper can receive the reflection of the light in every part of its surface, will be seen in hair-like lines, which are also iridescent. This experiment is purely catoptrical, for, as we cannot imagine that the light penetrates the surface of the steel, and thus undergoes a change, we are soon convinced that we have here a mere reflection, which in its subjective character is connected with the theory of faintly acting lights, and the afterimage of dazzling lights, and as far as it can be considered objective announces, even in the minutest appearances, a real effect independent of the action and reaction of the eye. We have seen that to produce these effects pg 157, not merely light, but a powerful light is necessary, that this powerful light again is not an abstract and general quality, but a circumscribed light, a luminous image. We can convince ourselves still further of this by analogous cases. A polished surface of silver placed in the sun reflects a dazzling light, but in this case no color is seen. If, however, we slightly scratch the surface, an iridescent appearance in which green and red are conspicuous will be exhibited at a certain angle in chased and carved metals. The effect is striking, yet it may be remarked throughout that in order to its appearance, some alternation of light and dark, must cooperate with the reflection. Thus a window bar, the stem of a tree, an accidentally or purposely interposed object, produces a perceptible effect. This appearance, too, may be exhibited objectively in the camera obscura. If we cause a polished plated surface to be so acted on by aqua fortis that the copper within is touched, and the surface itself thus rendered rough, and if the sun's image be then reflected from it, the splendor will be reverberated from every minutest prominence, and the surface will appear iridescent. So if we hold a sheet of pg 158 black unglazed paper in the sun, and look at it attentively, it will be seen to glisten in its minutest points with the most vivid colors. All these examples are referable to the same conditions. In the first case, the luminous image is reflected from a thin line; in the second, probably from sharp edges; in the third, from very small points. In all, a very powerful and circumscribed light is requisite for all these appearances of color. Again, it is necessary that the eye should be at a due distance from the reflecting points. If these observations are made with the microscope, the appearance will be greatly increased in force and splendor, for we then see the smallest portion of the surfaces, lit by the sun, glittering in these colors of reflection, which, allied to the hues of refraction, now attain their highest degree of brilliancy. In such cases, we may observe a vermiform iridescence on the surface of organic bodies, the further description of which will be given hereafter. Lastly, the colors which are chiefly exhibited pg 159 in reflection are red and green, whence we may infer that the linear appearance especially consists of a thin line of red bounded by blue on one side and yellow on the other. If these triple lines approach very near together, the intermediate space must appear green, a phenomenon which will often occur to us as we proceed. We frequently meet with these colors in nature. The colors of the spider's web might be considered exactly of the same class with those reflected from the steel wire, except that the non-translucent quality of the former is not so certain, as in the case of steel, on which account some have been inclined to class the colors of the spider's web with the phenomena of refraction. In mother of pearl, we perceive infinitely fine organic fibers, and lamel in juxtaposition, from which, as from the scratched silver before alluded to, varied colors, but especially red and green, may arise. The changing colors of the plumage of birds may also be mentioned here, although in all organic pg 160 instances a chemical principle and an adaptation of the color to the structure may be assumed, considerations to which we shall return in treating of chemical colors. That the appearances of objective halos also approximate catoptrical phenomena will be readily admitted, while we again do not deny that refraction as well may here come into the account for the present, we restrict ourselves to one or two observations. Hereafter, we may be enabled to make a fuller application of general principles to particular examples. We first call to mind the yellow and red circles produced on a white or gray wall by a light placed near it. 88 light, when reflected, appears subdued, and a subdued light excites the impression of yellow and subsequently of red. Let the wall be illumined by a candle placed quite close to it. The farther the light is diffused, the fainter it becomes. But it is still the effect of the flame, the continuation of its action, the dilated effect of its image. We might therefore very fairly call these circles pg 161 reiterated images, because they constitute the successive boundaries of the action of the light, and yet at the same time only present an extended image of the flame. If the sky is white and luminous round the sun owing to the atmosphere being filled with light vapors, if mists or clouds pass before the moon, the reflection of the disk mirrors itself in them. The halos we then perceive are single or double, smaller or greater, sometimes very large, often colorless, sometimes colored. I witnessed a very beautiful halo round the moon the 15th of November 1799. When the barometer stood high, the sky was cloudy and vapory. The halo was completely colored, and the circles were concentric round the light, as in subjective halos. That this halo was objective, I was presently convinced by covering the moon's disk, when the same circles were nevertheless perfectly visible. The different extent of the halos appears to have a relation with the proximity or distance of the vapor from the eye of the observer. pg 162. As windowpanes lightly breathed upon increase the brilliancy of subjective halos, and in some degree give them an objective character, so perhaps with a simple contrivance in winter, during a quickly freezing temperature, a more exact definition of this might be arrived at. How much reason we have in considering these circles to insist on the image, and its effects is apparent in the phenomenon of the so-called double suns. Similar double images always occur in certain points of halos and circles, and only present in a circumscribed form. What takes place in a more general way in the whole circle. All this will be more conveniently treated in connection with the appearance of the rainbow note Q. In conclusion, it is only necessary to point out the affinity between the catoptrical and paroptical colors. We call those paroptical colors, which appear when the light passes by the edge of an opaque colorless body. How nearly these are allied to the dioptrical colors of the second class will be easily seen by those who are convinced with us that the colors of refraction pg 163 take place only at the edges of objects. The affinity again between the catoptrical and paroptical colors will be evident in the following chapter. Roman 32 Paroptical colors. The paroptical colors have been hitherto called perioptical, because a peculiar effect of light was supposed to take place as it were round the object, and was ascribed to a certain flexibility of the light to and from the object. These colors again may be divided into subjective and objective, because they appear partly without us, as it were painted on surfaces, and partly within us immediately on the retina. In this chapter, we shall find it more to our purpose to take the objective cases first, since the subjective are so closely connected with other appearances already known to us, that it is hardly possible to separate them. The paroptical colors then are so called because pg 164, the light must pass by an outline or edge to produce them. They do not, however, always appear in this case to produce the effect. Very particular conditions are necessary besides. It is also to be observed that in this instance again light does not act as an abstract diffusion. 361. The sun shines towards an edge, the volume of light poured from the sunimage passes by the edge of a substance, and occasions shadows. Within these shadows, we shall presently find colors appear. But above all, we should make the experiments and observations that bear upon our present inquiry in the fullest light. We therefore place the observer in the open air, before we conduct him to the limits of a dark room. A person walking in sunshine in a garden, or on any level path, may observe that his shadow only appears sharply defined next the foot, on which he rests farther from this point, especially round the head. It melts away into the bright ground for, as the sunlight proceeds not only from the middle of the sun, but also acts crosswise from the two extremes of every pg 165 diameter, an objective parallax takes place, which produces a half-shadow on both sides of the object. If the person walking raises and spreads his hand, he distinctly sees in the shadow of each finger the diverging separation of the two half-shadows outwards, and the diminution of the principal shadow, inwards, both being effects of the cross-action of the light. This experiment may be repeated and varied before a smooth wall with rods of different thicknesses, and again with balls. We shall always find that the farther the object is removed from the surface of the wall, the more the weak double shadow spreads, and the more the forcible main shadow diminishes, till at last the main shadow appears quite effaced, and even the double shadows become so faint that they almost disappear at a still greater distance. They are in fact imperceptible. That this is caused by the cross-action of the light, we may easily convince ourselves, for the shadow of a pointed object plainly exhibits 2 points. We must thus never lose sight of the pg 166 fact that in this case, the whole synimage axe produces shadows, changes them to double shadows, and finally obliterates them. Instead of solid bodies, let us now take openings cut of various given sizes next each other, and let the sun shine through them on a plane surface at some little distance. We shall find that the bright image produced by the sun on the surface is larger than the opening. This is because one edge of the sun shines towards the opposite edge of the opening, while the other edge of the disk is excluded on that side. Hence, the bright image is more weakly lighted towards the edges. If we take square openings of any size we please, we shall find that the bright image on a surface 9 feet from the opening is on every side about an inch larger than the opening, thus nearly corresponding with the angle of the apparent diameter of the sun. That the brightness should gradually diminish towards the edges of the image is quite natural, for at last only a minimum of the light can act crosswise from the sun's circumference through the edge of the aperture. Pg 167. Thus, we here again see how much reason we have in actual observation to guard against the assumption of parallel rays bundles and fasces of rays, and the like hypothetical notions. We might rather consider the splendor of the sun, or of any light, as an infinite specular multiplication of the circumscribed luminous image, whence it may be explained that all square openings through which the sun shines at certain distances, according as the apertures are greater or smaller, must give a round image of light. The above experiments may be repeated through openings of various shapes and sizes, and the same effect will always take place at proportionate distances. In all these cases, however, we may still observe that in a full light, and while the sun merely shines past an edge, no color is apparent. We therefore proceed to experiments with a subdued light, which is essential to the appearance of color. Let a small opening be made in the window shutter of a dark room. Let the pg 168 crossing sunlight, which enters, be received on a surface of white paper, and we shall find that the smaller the opening is, the dimmer the light image will be. This is quite obvious, because the paper does not receive light from the whole sun, but partially from single points of its disk. If we look attentively at this dim image of the sun, we find it still dimmer towards the outlines where a yellow border is perceptible. The color is still more apparent if a vapor or a transparent cloud passes before the sun, thus subduing and dimming its brightness. The halo on the wall, the effect of the decreasing brightness of a light placed near it, is here forced on our recollection. 88. If we examine the image more accurately, we perceive that this yellow border is not the only appearance of color. We can see besides a bluish circle, if not even a halo-like repetition of the colored border. If the room is quite dark, we discern that the sky next the sun also has its effect. We see the blue sky, nay, even the whole landscape on the paper, and are thus again convinced that as far as regards the sun, we have here only to do with a luminous image. Pg 169. If we take a somewhat larger square opening, so large that the image of the sun shining through it does not immediately become round, we may distinctly observe the half-shadows of every edge or side, the junction of these in the corners, and their colors, just as in the above-mentioned appearance with the round opening. We have now subdued a parallactic light by causing it to shine through small apertures, but we have not taken from it its parallactic character, so that it can produce double shadows of bodies, although with diminished power. These double shadows, which we have hitherto been describing, follow each other in light and dark-colored and colorless circles, and produce repeated, nay, almost innumerable halos. These effects have been often represented in drawings and engravings by placing needles, hairs, and other small bodies in the subdued light. The numerous halo-like double shadows may be increased. Thus observed, they have been ascribed to an alternating flexile action of the light, and the same assumption has been employed to explain the obliteration of the central shadow and the appearance of a light in the place of the dark. Pg 170. For ourselves, we maintain that these again are parallactic double shadows, which appear edged with colored borders and halos. After having seen and investigated the foregoing phenomena, we can proceed to the experiments with knife blades, one exhibiting effects, which may be referred to the contact and parallactic mutual intersection of the half-shadows and halos already familiar to us. Lastly, the observer may follow out the experiments with hare's needles and wires in the half-light produced, as before described by the sun as well as in that derived from the blue sky, and indicated on the white paper. He will thus make himself still better acquainted with the true nature of this phenomenon. But since in these experiments everything depends on our being persuaded of the parallactic action of the light, we can make this more evident by means of two sources of light, the two shadows from which intersect each other, and may be altogether separated by day. This may be contrived with two small Pg 171 openings in a window shutter by night with two candles. There are even accidental effects in interiors on opening and closing shutters by means of which we can better observe these appearances than with the most careful apparatus. But still all in each of these may be reduced to experiment by preparing a box which the observer can look into from above and gradually diminishing the openings after having caused a double light to shine in this case. As might be expected, the colored shadow considered under the physiological colors appears very easily. It is necessary to remember generally what has been before stated with regard to the nature of double shadows half-lights, and the like experiments also should especially be made with different shades of gray placed next each other, where every stripe will appear light by a darker, and dark by a lighter stripe next it. If at night with three or more lights we produce shadows which cross each other successively, we can observe this phenomenon very distinctly, and we shall be convinced that the physiological case before more fully treated here comes into the account. 38. To what extent the appearances that accompany Pg 172, the paroptical colors, may be derived from the doctrine of subdued lights, from half-shadows, and from the physiological disposition of the retina, or whether we shall be forced to take refuge in certain intrinsic qualities of light as has hitherto been done, time may teach. Suffice it here to have pointed out the conditions under which the paroptical colors appear, and we may hope that our allusion to their connection with the facts before adduced by us will not remain unnoticed by the observers of nature. The affinity of the paroptical colors with the dioptrical of the second class will also be readily seen and followed up by every reflecting investigator here as in those instances we have to do with edges or boundaries, here as in those instances with a light which appears at the outline. How natural, therefore, it is to conclude that the paroptical effects may be heightened, strengthened, and enriched by the dioptrical. Since, however, the luminous image actually shines through the medium, we can here only have to do with objective cases of refraction. It is these which are strictly allied to the paroptical cases. The subjective cases of refraction, where we see objects through the medium, are quite distinct from the paroptical. Pg 173. We have already recommended them on account of their clearness and simplicity. The connection between the paroptical colors and the catoptrical may be already inferred from what has been said, for, as the catoptrical colors only appear on scratches, points, steel wire, and delicate threads, so it is nearly the same case as if the light shone past an edge. The light must always be reflected from an edge in order to produce color. Here again, as before pointed out, the partial action of the luminous image and the subduing of the light are both to be taken into the account. We add but few observations on the subjective paroptical colors, because these may be classed partly with the physiological colors, partly with the dioptrical of the second order. The greater part hardly seem to belong here, but when attentively considered, they still diffuse a satisfactory light over the whole doctrine and establish its connection. If we hold a ruler before the eyes, so that the flame of a light just appears above it, we see the ruler as it were indented and notched at the Pg 174 place, where the light appears. This seems deducible from the expansive power of light acting on the retina. 18. The same phenomenon on a large scale is exhibited at sunrise, for when the orb appears distinctly, but not too powerfully, so that we can still look at it, it always makes a sharp indentation in the horizon. If when the sky is gray, we approach a window, so that the dark cross of the window bars be relieved on the sky, If after fixing the eyes on the horizontal bar, we bend the head a little forward on half closing the eyes, as we look up, we shall presently perceive a bright yellowed border under the bar and a bright light blue one above it, the duller and more monotonous the gray of the sky, the more dusky the room. And consequently, the more previously unexcited the eye, the livelier the appearance will be, but it may be seen by an attentive observer, even in bright daylight. If we move the head backwards, while half closing the eyes, so that the horizontal bar be seen below, the phenomenon will appear reversed. Pg 175. The upper edge will appear yellow, the under edge blue. Such observations are best made in a dark room if white paper is spread before the opening where the solar microscope is commonly fastened. The lower edge of the circle will appear blue, the upper yellow, even while the eyes are quite open, or only by half closing them, so far that a halo no longer appears round the white. If the head is moved backwards, the colors are reversed. These phenomena seem to prove that the humors of the eye are in fact only really achromatic in the center where vision takes place, but that towards the circumference, and in unusual motions of the eyes, as in looking horizontally when the head is bent backwards or forwards, a chromatic tendency remains, especially when distinctly relieved objects are thus looked at. Hence, such phenomena may be considered as allied to the dioptrical colors of the second class. Similar colors appear if we look on black and white objects through a pinhole in a card. Pg 176. Instead of a white object, we may take the minute light aperture in the tin plate of a camera obscura as prepared for paroptical experiments. If we look through a tube the farther end of which is contracted or variously indented, the same colors appear. The following phenomena appear to me to be more nearly allied to the paroptical appearances. If we hold up a needle near the eye, the point appears double. A particularly remarkable effect again is produced if we look towards a gray sky through the blades of knives. Prepared for paroptical experiments, we seem to look through a gauze. A multitude of threads appear to the eye. These are in fact only the reiterated images of the sharp edges, each of which is successively modified by the next, or perhaps modified in a parallactic sense, by the oppositely acting one, the whole mass being thus changed to a thread-like appearance. Lastly, it is to be remarked that if we look through the blades towards a minute light, in Pg 177, the window shutter colored stripes and halos appear on the retina, as on the paper. The present chapter may be here terminated the less reluctantly, as a friend has undertaken to investigate this subject by further experiments in our recapitulation, in the description of the plates and apparatus. We hope hereafter to give an account of his observations too. Roman 33. Epoptical colors. We have hitherto had to do with colors which appear with vivacity, but which immediately vanish again when certain conditions cease. We have now to become acquainted with others which, it is true, are still to be considered as transient, but which under certain circumstances become so fixed that even after the conditions which first occasion their appearance cease, they still remain, and thus constitute. Pg 178. The link between the physical and the chemical colors. They appear from various causes on the surface of a colorless body, originally without communication, dye, or immersion, and we now proceed to trace them from their faintest indication to their most permanent state through the different conditions of their appearance, which for easier survey we here at once summarily state. First condition: the contact of two smooth surfaces of hard transparent bodies. First case: if masses or plates of glass, or if lenses are pressed against each other. Second case: if a crack takes place in a solid mass of glass, crystal, or ice. Third case: if lamel of transparent stones become separated. Second condition: if a surface of glass or a polished stone is breathed. Third condition: the combination of the two, last first breathing on the glass, then placing another plate of glass upon it, thus exciting the colors by pressure, then removing the upper glass, upon which the colors begin to fade and vanish with the breath. Pg 179. Fourth condition: bubbles of various liquids, soap, chocolate, beer, wine, fine glass bubbles. Fifth condition: very fine pellicles and lamel produced by the decomposition of minerals and metals, the pellicles of lime, the surface of stagnant water, especially if impregnated with iron, and again, pellicles of oil on water, especially of varnish on aquafortis. Sixth condition: if metals are heated, the operation of imparting tints to steel and other metals. Seventh condition: if the surface of glass is beginning to decompose. First condition, first case, if two convex glasses, or a convex and plane glass, or best of all a convex and concave glass, come in contact concentric colored circles, appear the phenomenon exhibits itself immediately on the slightest pressure, and may then be gradually carried through various successive states. We will describe the complete appearance at once, as we shall then be better enabled to follow the different states through which it passes. The center is colorless, where the glasses are so to speak united in one by the strongest pressure. A dark gray point appears with a silver PG 180 white space round. It then follow in decreasing distances various insulated rings, all consisting of three colors, which are in immediate contact with each other. Each of these rings, of which perhaps 3 or 4 might be counted, is yellow on the inner side, blue on the outer, and red in the center between two rings. There appears a silver-white interval. The rings which are farthest from the center are always nearer together. They are composed of red and green, without a perceptible white space between them. We will now observe the appearances in their gradual formation, beginning from the slightest pressure. On the slightest pressure, the center itself appears of a green color, then follow as far as the concentric circles extend red and green rings. They are wide accordingly, and no trace of a silver-white space is to be seen between them. The green is produced by the blue of an imperfectly developed circle mixing with the yellow of the first circle. All the remaining circles are in this slight contact, broad their yellow and blue edges mixed together, thus producing a beautiful green. The red, however, of PG 181, each circle remains pure and untouched, hence the whole series is composed of these two colors. A somewhat stronger pressure separates the first circle by a slight interval from the imperfectly developed one. It is thus detached, and may be said to appear in a complete state. The center is now a blue point, for the yellow of the first circle is now separated from this central point by a silver-white space. From the center of the blue, a red appears, which is thus in all cases bounded on the outside by its blue edge. The second and third rings from the center are quite detached. Where deviations from this order present themselves, the observer will be enabled to account for them from what has been or remains to be stated. On a stronger pressure, the center becomes yellow. This yellow is surrounded by a red and blue edge. At last, the yellow also retires from the center. The innermost circle is formed and is bounded with yellow. The whole center itself now appears silver-white, till at last on the strongest pressure the dark point appears, and the phenomenon as described at first is complete. PG 182. The relative size of the concentric circles and their intervals depends on the form of the glasses, which are pressed together. We remarked above that the colored center is in fact an undeveloped circle. It is, however, often found on the slightest pressure that several undeveloped circles exist there, as it were in the germ. These can be successively developed before the eye of the observer. The regularity of these rings is owing to the form of the convex glasses, and the diameter of the colored appearance depends on the greater or lesser section of a circle on which a lens is polished. We easily conclude from this that by pressing plain glasses together, irregular appearances only will be produced. The colors in fact undulate like watered silks and spread from the point of pressure in all directions. Yet the phenomenon as thus exhibited is much more splendid than in the former instance, and cannot fail to strike every spectator. If we make the experiment in this mode, we shall distinctly see, as in the other case, that on a slight pressure, the green and red waves appear on a stronger stripes of blue, red, and yellow, become detached. PG 183. At first the outer sides of these stripes touch on increased pressure. They are separated by a silver-white space. Before we proceed to a further description of this phenomenon, we may point out the most convenient mode of exhibiting it. Place a large convex glass on a table near the window. Upon this glass, lay a plate of well-polished mirror glass about the size of a playing card, and the mere weight of the plate will press sufficiently to produce one or other of the phenomena above described. So also, by the different weight of plates of glass, by other accidental circumstances, for instance, by slipping the plate on the side of the convex glass, where the pressure cannot be so strong as in the center, all the gradations above described can be produced in succession. In order to observe the phenomenon, it is necessary to look obliquely on the surface where it appears, but above all it is to be remarked that by stooping still more, and looking at the appearance under a more acute angle, the circles not only grow larger, but other circles are developed from the center of which no trace is to be discovered. when we look perpendicularly even through the strongest magnifiers. Pg 184. In order to exhibit the phenomenon in its greatest beauty, the utmost attention should be paid to the cleanness of the glasses. If the experiment is made with plate glass adapted for mirrors, the glass should be handled with gloves. The inner surfaces, which must come in contact with the utmost nicety, may be most conveniently cleaned before the experiment, and the outer surfaces should be kept clean while the pressure is increased. From what has been said, it will be seen that an exact contact of two smooth surfaces is necessary. Polished glasses are best adapted for the purpose. Plates of glass exhibit the most brilliant colors when they fit closely together, and for this reason the phenomenon will increase in beauty if exhibited under an air pump by exhausting the air. The appearance of the colored rings may be produced in the greatest perfection by placing a convex and concave glass together, which have been ground on similar segments of circles. I have never seen the effect more brilliant than with the object glass of an achromatic telescope, Pg 185, in which the crown glass and flint glass were necessarily in the closest contact. A remarkable appearance takes place when dissimilar surfaces are pressed together, for example a polished crystal and a plate of glass. The appearance does not at all exhibit itself in large flowing waves, as in the combination of glass with glass, but it is small and angular, and as it were disjointed. Thus it appears that the surface of the polished crystal, which consists of infinitely small sections of lamel, does not come so uninterruptedly in contact with the glass as another glass plate would. The appearance of color vanishes on the strongest pressure, which so intimately unites the two surfaces that they appear to make but one substance. It is this which occasions the dark center, because the pressed lens no longer reflects any light from this point, for the very same point, when seen against the light, is perfectly clear and transparent. On relaxing the pressure, the colors in like manner gradually diminish and disappear entirely when the surfaces are separated. Pg 186. These same appearances occur in two similar cases. If entirely transparent masses become partially separated, the surfaces of their parts being still sufficiently in contact, we see the same circles and waves more or less. They may be produced in great beauty by plunging a hot mass of glass in water, the different fissures and cracks, enabling us to observe the colors in various forms. Nature often exhibits the same phenomena in split rock crystals. This appearance again frequently displays itself in the mineral world in those kinds of stone which by nature have a tendency to exfoliate these original lamel. Art is true so intimately united that stones of this kind appear altogether transparent and colorless, yet the internal layers become separated from various accidental causes, without altogether destroying the contact. Thus the appearance which is now familiar to us by the foregoing description often occurs in nature, particularly in calcareous spars, the specularis adularia, and other minerals of similar structure. Hence, it shows an ignorance of the proximate causes of an appearance, so often accidentally produced, to consider it so important in mineralogy, and to attach a special value to the specimens exhibiting it. Pg 187. We have yet to speak of the very remarkable inversion of this appearance as related by men of science, if namely instead of looking at the colors by a reflected light, we examine them by a transmitted light, the opposite colors are said to appear, and in a mode corresponding with that which we have before described as physiological, the colors evoking each other. Instead of blue, we should thus see red yellow, instead of red green Roman 100, and vice versa. We reserve experiments in detail the rather, as we have ourselves still some doubts on this point. If we were now called upon to give some general explanation of these epoptical colors, as they appear under the first condition, and to show their connection with the previously detailed physical phenomena, we might proceed to do so as follows. The glasses employed for the experiments are to be regarded as the utmost possible practical approach to transparence by the intimate contact, however, occasioned by the pressure applied to them. Their surfaces, we are persuaded, immediately become, in a very slight degree, dimmed within. This semi-transparence, Pg 188, the colors immediately appear, and every circle comprehends the whole scale, for when the two opposites, yellow and blue, are united by their red extremities, pure red, appears the green on the other hand, as in prismatic experiments when yellow and blue touch. We have already repeatedly found that where color exists at all, the whole scale is soon called into existence. A similar principle may be said to lurk in the nature of every physical phenomenon, it already follows from the idea of polar opposition, from which an elementary unity or completeness results. The fact that a color exhibited by transmitted light is different from that displayed by reflected light reminds us of those dioptrical colors of the first class which we found were produced precisely in the same way through semiopacity, that here too a diminution of transparency exists. There can scarcely be a doubt for the adhesion of the perfectly smooth plates of glass. An adhesion so strong that they remain hanging to each other produces a degree of union, which deprives each of the two surfaces in some degree of its smoothness and transparence. The fullest proof may, however, pg 189, be found in the fact that in the center where the lens is most strongly pressed on the other glass, and where a perfect union is accomplished, a complete transparence takes place, in which we no longer perceive any color. All this may be hereafter confirmed in a recapitulation of the whole. Second condition: if, after breathing on a plate of glass, the breath is merely wiped away with the finger, and if we then again immediately breathe on the glass, we see very vivid colors gliding through each other. These, as the moisture evaporates, change their place, and at last vanish altogether. If this operation is repeated, the colors are more vivid and beautiful and remain longer than they did the first time. Quickly as this appearance passes and confused as it appears to be, I have yet remarked the following effects. At first, all the principal colors appear with their combinations on breathing more strongly. The appearance may be perceived in some order in this succession. It may be remarked that when the breath in evaporating becomes contracted from all sides pg 190, towards the center the blue color vanishes last. The phenomenon appears most readily between the minute lines, which the action of passing the fingers leaves on the clear surface. A somewhat rough state of the surface of the glass is otherwise requisite on some glass. The appearance may be produced by merely breathing. In other cases, the wiping with the fingers is necessary. I have even met with polished mirror glasses, one side of which immediately showed the colors vividly, the other not to judge from some remaining pieces. The former was originally the front of the glass, the latter the side, which was covered with quicksilver. These experiments may be best made in cold weather, because the glass may be more quickly and distinctly breathed upon, and the breath evaporates more suddenly. In severe frost, the phenomenon may be observed on a large scale, while traveling in a carriage. The glasses being well cleaned and all closed, the breath of the persons within is very gently diffused over the glass, and immediately produces the most vivid play of colors. How far they may present a regular succession, I have not been able to remark pg 191, but they appear particularly vivid when they have a dark object as a background. This alternation of colors does not, however, last long, for as soon as the breath gathers in drops or freezes to points of ice, the appearance is at once at an end. Third condition: the two foregoing experiments of the pressure and breathing may be united, namely by breathing on a plate of glass, and immediately after pressing the other upon it. The colors then appear as in the case of two glasses, unbreathed upon, with this difference, that the moisture occasions here and there an interruption of the undulations. On pushing one glass away from the other, the moisture appears iridescent as it evaporates. It might, however, be asserted that this combined experiment exhibits no more than each single experiment, for it appears the colors excited by pressure disappear in proportion as the glasses are less in contact, and the moisture then evaporates with its own colors. Fourth condition: iridescent appearances are observable in almost all bubbles. Soap bubbles pg 192 are the most commonly known, and the effect in question is thus exhibited in the easiest mode. But it may be observed in wine, beer, in pure spirit, and again, especially in the froth of chocolate. As in the above cases, we required an infinitely narrow space between two surfaces which are in contact, so we can consider the pellicle of the soap bubble as an infinitely thin lamina between two elastic bodies, for the appearance in fact takes place between the air within which distends the bubble and the atmospheric air. The bubble when first produced is colorless, then colored stripes like those in marble paper begin to appear. These at length spread over the whole surface, or rather are driven round it as it is distended. In a single bubble suffered to hang from the straw or tube, the appearance of color is difficult to observe, for the quick rotation prevents any accurate observation, and all the colors seem to mix together, yet we can perceive that the colors begin at the orifice of the tube. The solution itself may, however, be blown into carefully pg 193, so that only one bubble shall appear. This remains white colorless if not much agitated, but if the solution is not, two watery circles appear round the perpendicular axis of the bubble, these being near each other, are commonly composed alternately of green and red. Lastly, several bubbles may be produced together by the same means. In this case, the colors appear on the sides, where two bubbles have pressed each other flat. The bubbles of chocolate froth may perhaps be even more conveniently observed than those of soap, though smaller they remain longer in these owing to the heat. An impulse, a movement is produced and sustained which appears necessary to the development and succession of the appearances. If the bubble is small or shut in between others, colored lines chase each other over the surface resembling marbled paper. All the colors of the scale are seen to pass through each other, the pure, the augmented, the combined, all distinctly clear and beautiful in small bubbles. The appearance lasts for a considerable time. Pg 194. If the bubble is larger, or if it becomes by degrees detached, owing to the bursting of others, near we perceive that this impulsion and attraction of the colors has as it were an end in view, for on the highest point of the bubble we see a small circle appear which is yellow in the center. The other remaining colored lines move constantly round this with a vermicular action. In a short time, the circle enlarges and sinks downwards on all sides. In the center the yellow remains below, and on the outside it becomes red, and soon blue. Below this again appears a new circle of the same series of colors. If they approximate sufficiently, a green is produced by the union of the border colors. When I could count 3 such leading circles, the center was colorless, and this space became by degrees larger as the circles sank lower till at last the bubble burst. Fifth condition, very delicate pellicles may be formed in various ways. On these films, we discover a very lively play of colors, either in the usual order, or more confusedly passing through each other. The water, in which lime Pg 195 has been slaked, soon skims over. With a colored pellicle, the same happens on the surface of stagnant water, especially if impregnated with iron. The lamel of the fine tartar, which adheres to bottles especially in red French wine, exhibit the most brilliant colors on being exposed to the light. If carefully detached drops of oil on water, brandy, and other fluids produce also similar circles and brilliant effects. But the most beautiful experiment that can be made is the following. Let aqua fortis not too strong be poured into a flat saucer, and then with a brush drop on it some of the varnish used by engravers to cover certain portions. During the process of biting their plates after quick commotion, there presently appears a film which spreads itself out in circles and immediately produces the most vivid appearances of color. Sixth condition, when metals are heated, colors, rapidly succeeding each other, appear on the surface. These colors can, however, be arrested at will. If a piece of polished steel is heated, it will at a certain degree of warmth be overspread with yellow. If taken suddenly away from the fire, this yellow remains. Pg 196. As the steel becomes hotter, the yellow appears darker, intenser, and presently passes into red. This is difficult to arrest, for it hastens very quickly to bright blue. This beautiful blue is to be arrested if the steel is suddenly taken out of the heat and buried in ashes. The blue steel works are produced in this way. If again the steel is held longer over the fire, it soon becomes a light blue, and so it remains. These colors pass like a breath over the plate of steel. Each seems to fly before the other, but in reality, each successive hue is constantly developed from the preceding one. If we hold a penknife in the flame of a light, a colored stripe will appear across the blade. The portion of the stripe which was nearest to the flame is light blue. This melts into bluard. The red is in the center, then follow yellowed and yellow. This phenomenon is deducible from the preceding Pg 197 ones. For the portion of the blade, next the handle is less heated than the end which is in the flame, and thus all the colors which in other cases exhibited themselves in succession must here appear at once, and may thus be permanently preserved. Robert Boyle gives this succession of colors as follows: a florido flavo, ad flavum saturum, et rubescentum quem artifices sanguineum vocant, inde ad languidum postea, ad saturarum cyaneum. This would be quite correct if the words languidus and saturare were to change places. How far the observation is correct that the different colors have a relation to the degree of temper which the metal afterwards acquires, we leave to others to decide. The colors are here only indications of the different degrees of heat. Note R. When lead is calcined, the surface is first grayish. This grayish powder with greater heat becomes yellow. And then orange silver too exhibits colors. When heated, the fracture of silver, in the process of refining, belongs to the same class of examples. When metallic glasses melt, colors in like manner appear on the surface. Pg 198. Seventh condition: when the surface of glass becomes decomposed, the accidental opacity blindwardden of glass has been already noticed. The term blindwardden is employed to denote that the surface of the glass is so affected as to appear dim to us. White glass becomes blind soonest cast, and afterwards polished glass is also liable to be so affected, the bluish less the green least. Of the two sides of a plate of glass, one is called the mirror side. It is that which in the oven lies uppermost, on which one may observe roundish elevations. It is smoother than the other, which is undermost in the oven, and on which scratches may be sometimes observed. On this account, the mirror side is placed facing the interior of rooms, because it is less affected by the moisture adhering to it from within than the other would be, and the glass is thus less liable to become blind. This half opacity or dimness of the glass assumes by degrees an appearance of color, which may become very vivid, and in which Pg 199 perhaps a certain succession or otherwise regular order might be discovered. Having thus traced the physical colors from their simplest effects to the present instances where these fleeting appearances are found to be fixed in bodies, we are in fact arrived at the point where the chemical colors begin, nay, we have in some sort already passed those limits, circumstance which may excite a favorable prejudice for the consistency of our statement. By way of conclusion to this part of our inquiry, we subjoin a general observation, which may not be without its bearing on the common connecting principle of the phenomena that have been adduced. The coloring of steel and the appearances analogous to it might perhaps be easily deduced from the doctrine of the semi-opaque mediums. Polished steel reflects light powerfully. We may consider the color produced by the heat as a slight degree of dimness. Hence, a bright yellow must immediately appear. This, as the dimness increases, must still appear deeper, more condensed, and redder, and at last pure and rubbered. The color has now reached the extreme point of depth, and if we suppose the same degree Pg 200 of semi-opacity still to continue, the dimness would now spread itself over a dark ground, first producing a violet, then a dark blue, and at last a light blue, and thus complete the series of the appearances. We will not assert that this mode of explanation will suffice in all cases. Our object is rather to point out the road by which the all-comprehensive formula, the very key of the enigma, may be at last discovered. Note S. Pg 201. Part Roman 3. Chemical colors. We give this denomination to colors which we can produce, and more or less fix in certain bodies, which we can render more intense, which we can again take away and communicate to other bodies, and to which therefore we ascribe a certain permanency. Duration is their prevailing characteristic. In this view, the chemical colors were formerly distinguished with various epithets. They were called colors proprii corporae, materials, vari permanens fixi. In the preceding chapter, we observed how the fluctuating and transient nature of the physical colors becomes gradually fixed, thus forming the natural transition to our present subject. Color becomes fixed in bodies more or less, permanently, superficially, or thoroughly. All bodies are susceptible of color. It can Pg 202 either be excited, rendered intense, and gradually fixed in them, or at least communicated to them. Roman 30. 4. Chemical contrast. In the examination of colored appearances, we had occasion everywhere to take notice of a principle of contrast. So again, in approaching the precincts of chemistry, we find a chemical contrast of a remarkable nature. We speak here with reference to our present purpose only of that which is comprehended under the general names of acid and alkali. We characterize the chromatic contrast, in conformity with all other physical contrasts, as a more and less, ascribing the plus to the yellow side, the minus to the blue. And we now find that these two divisions correspond with the chemical contrasts. The yellow and yellowed affect the acids, the blue and bluerd the alkalis. Thus the phenomena of chemical colors, although still necessarily mixed up with Pg 203 other considerations, admit of being traced with sufficient simplicity. The principal phenomena in chemical colors are produced by the oxidation of metals, and it will be seen how important this consideration is at the outset. Other facts which come into the account, and which are worthy of attention, will be examined under separate heads. In doing this, We, however, expressly state that we only propose to offer some preparatory suggestions to the chemist in a very general way, without entering into the nicer chemical problems and questions, or presuming to decide on them. Our object is only to give a sketch of the mode in which, according to our conviction, the chemical theory of colors may be connected with general physics. Roman 35 White. In treating of the dioptrical colors of the first class 155, we have already in some degree anticipated this subject. Transparent substances, pg 204, may be said to be in the highest class of inorganic matter. With these, colorless semitransparence is closely connected, and white may be considered the last opaque degree of this. Pure water crystallized to snow appears white for the transparence of the separate parts, makes no transparent whole. Various crystallized salts, when deprived to a certain extent of moisture, appear as a white powder. The accidentally opaque state of a pure transparent substance might be called white. Thus, pounded glass appears as a white powder. The cessation of a combining power and the exhibition of the atomic quality of the substance might at the same time be taken into the account. The known undecomposed earths are in their pure state all white. They pass to a state of transparence by natural crystallization. Silex becomes rock crystal. Argil, mica, magnesia, talc, calcareous earth, and barytes appear transparent in various spars. Note T. As in the coloring of mineral bodies, the Pg 205 metallic oxides will often invite our attention. We observe in conclusion that metals, when slightly oxidated at first, appear white as lead is converted to white lead by vegetable acid. Roman 36 Black. Black is not exhibited in so elementary a state as white. We meet with it in the vegetable kingdom in semicombustion, and charcoal, a substance especially worthy of attention on other accounts, exhibits a black color again. If woods, for example, boards, owing to the action of light, air, and moisture, are deprived in part of their combustibility, there appears first the gray, then the black color. So again, we can convert even portions of animal substance to charcoal by semicombustion. In the same manner, we often find that a suboxidation takes place in metals when the black color is to be produced. Various metals, particularly iron, become black by slight oxidation, Pg 206, by vinegar, by mild acid fermentations, for example, a decoction of rice. Roman 100. Again, it may be inferred that a deoxidation may produce black. This occurs in the preparation of ink, which becomes yellow by the solution of iron in strong sulfuric acid, but when partly deoxidized by the infusion of gallnuts, appears black. Roman 37. First excitation of color. In the division of physical colors, where semi-transparent mediums were considered, we saw colors antecedently to white and black. In the present case, we assume a white and black already produced and fixed, and the question is how color can be excited in them. Here too we can say white that becomes darkened or dimmed inclines to yellow-black, as it becomes lighter inclines to blue. Note U. Pg 207. Yellow appears on the active plus side immediately in the light. The bright, the white, all white surfaces easily assume a yellow tinge. Paper, linen, wool, silk, wax, transparent fluids again, which have a tendency to combustion, easily become yellow. In other words, they easily pass into a very slight state of semitransparence. So again, the excitement on the passive side, the tendency to obscure dark black, is immediately accompanied with blue, or rather, with a reddish-blue iron dissolved in sulfuric acid, and much diluted with water if held to the light in a glass, exhibits a beautiful violet color. As soon as a few drops only of the infusion of gallnuts are added, this color presents the peculiar hues of the dark topaz, the orphnanon of a burntid, as the ancients expressed it. Whether any color can be excited in the pure earths by the chemical operations of nature and art without the admixture of metallic oxides is an important question. Generally indeed answered in the negative, it is perhaps connected with the question to what extent Pg 208 changes may be produced in the earths through oxidation. Undoubtedly, the negation of the above question is confirmed by the circumstance that wherever mineral colors are found, some trace of metal, especially of iron, shows itself. We are thus naturally led to consider how easily iron becomes oxidized, how easily the oxide of iron assumes different colors, how infinitely divisible it is, and how quickly it communicates its color. It were to be wished, notwithstanding, that new experiments could be made in regard to the above point, so as either to confirm or remove any doubt. However, this may be the susceptibility of the Earths with regard to colors already existing, is very great a luminous Earth, is thus particularly distinguished. In proceeding to consider the metals which in the inorganic world have the almost exclusive prerogative of appearing colored, we find that in their pure independent natural state, they are already distinguished from the Pg 209 pure Earths by a tendency to some one color or other. While silver approximates most to pure whiteness, really represents pure white heightened by metallic splendor steel tin lead, and so forth inclined towards pale blue-gray gold on the other hand deepens to pure yellow copper, approaches a red hue, which under certain circumstances increases almost to bright red, but which again returns to a yellow-golden color when combined with zinc. But if metals in their pure state have so specific a determination towards this or that exhibition of color, they are through the effect of oxidation in some degree reduced to a common character, for the elementary colors now come forth in their purity, and although this or that metal appears to have a particular tendency to this or that color, we find some that can go through the whole circle of hues, others that are capable of exhibiting more than one color. Tin, however, is distinguished by its comparative inaptitude to become colored. We propose to give a table hereafter showing how far the different metals can be more or less made to exhibit the different colors. Pg 210. When the clean, smooth surface of a pure metal on being heated becomes overspread with a mantling color, which passes through a series of appearances, as the heat increases, this, we are persuaded, indicates the aptitude of the metal to pass through the whole range of colors. We find this phenomenon most beautifully exhibited in polished steel, but silver, copper, brass, lead, and tin easily present similar appearances. A superficial oxidation is probably here taking place, as may be inferred from the effects of the operation, when continued especially in the more easily oxidizable metals. The same conclusion may be drawn from the fact that iron is more easily oxidizable by acid liquids, when it is red hot, for in this case, the two effects concur with each other. We observe again that steel accordingly, as it is hardened in different stages of its colorification, may exhibit a difference of elasticity. This is quite natural, for the various appearances of color indicate various degrees of heat. 1. If we look beyond this superficial mantling Pg 211, this pellicle of color, we observe that as metals are oxidized throughout their masses, white or black appears with the first degree of heat, as may be seen in white lead, iron, and quicksilver. If we examine further and look for the actual exhibition of color, we find it most frequently on the plus side. The mantling, so often mentioned of smooth metallic surfaces, begins with yellow iron, passes presently into yellow ochre lead from white lead, to massicot quicksilver from thiops to yellow turbith. The solutions of gold and platinum in acids are yellow. The exhibitions on the minus side are less frequent. Copper, slightly oxidized, appears blue in the preparation of Prussian blue alkalis are employed. Generally, however, these appearances of color are of so mutable a nature that chemists look upon them as deceptive tests, at least in the nicer gradations for ourselves, as we can only treat of these matters in a general way. We merely observe that the appearances of color in metals may be classed according to their Pg 212 origin, manifold appearance, and cessation, as various results of oxidation, hyperoxidation, aboxidation, and deoxidation. 2. Roman 38. Augmentation of color. 1. The augmentation of color exhibits itself as a condensation, a fullness, a darkening of the hue. We have before seen in treating of colorless mediums, that by increasing the degree of opacity in the medium, we can deepen a bright object from the lightest yellow to the intensest rubbered blue. On the other hand, increases to the most beautiful violet if we rarefy and diminish a semi-opaque medium itself lighted, but through which we see darkness. 150-151. If the color is positive, a similar color appears in the intenser state. Thus, if we fill a white porcelain cup with a pure yellow liquor, the fluid will appear to become gradually redder Pg 213 towards the bottom, and at last appears orange. If we pour a pure blue solution into another cup, the upper portion will exhibit a sky blue, that towards the bottom a beautiful violet. If the cup is placed in the sun, the shadowed side even of the upper portion is already violet. If we throw a shadow with the hand or any other substance over the illumined portion, the shadow in like manner appears reddish. This is one of the most important appearances connected with the doctrine of colors, for we here manifestly find that a difference of quantity produces a corresponding qualified impression on our senses. In speaking of the last class of apoptical colors, 452-485, we stated our conjecture that the coloring of steel might perhaps be traced to the doctrine of the semi-transparent mediums, and we would here again recall this to the reader's recollection. All chemical augmentation of color again is the immediate consequence of continued excitation. The augmentation advances constantly and unremittingly, and it is to be observed that the increase of intenseness is most common on the plus side. Yellow iron ochre increases as well by fire as by other operations to a very pg 214 strong red massicot, is increased to red lead turbith to vermilion, which last attains a very high degree of the yellowed, an intimate saturation of the metal by the acid, and its separation to infinity take place together with the above effects. The augmentation on the minus side is less frequent, but we observe that the more pure and condensed the Prussian blue or cobalt glass is prepared, the more readily it assumes a reddish hue and inclines to the violet. The French have a happy expression for the less perceptible tendency of yellow and blue towards red. They say the color has un il de rouge, which we might perhaps express by a reddish glance, einen rothlichen Blick. Roman 39 Culmination 1. This is the consequence of still progressing augmentation, red, in which neither yellow nor pg 215 blue is to be detected here, constitutes the acme. If we wish to select a striking example of a culmination on the plus side, we again find it in the colored steel, which attains the bright red acme and can be arrested at this point. Were we here to employ the terminology before proposed, we should say that the first oxidation produces yellow, the hyperoxidation yellowed, that here a kind of maximum exists, and that then an aboxidation, and lastly a deoxidation takes place. High degrees of oxidation produce a bright red gold in solution, precipitated by a solution of tin, appears bright red oxide of arsenic in combination with sulfur, produces a ruby color. How far, however, a kind of suboxidation may cooperate in some culminations is matter for inquiry, for an influence of alkalis on pg 216 yellowed also appears to produce the culmination, the color reaching the acme, by being forced towards the minus side. The Dutch prepare a color known by the name of vermilion from the best Hungarian cinnabar, which exhibits the brightest yellowed. This vermilion is still only a cinnabar which however approximates the pure red, and it may be conjectured that alkalis are used to bring it nearer to the culminating point. Vegetable juices treated in this way offer very striking examples of the above, affects the coloring matter of turmeric annatto dyers, saffron too, and other vegetables being extracted with spirits of wine, exhibits tints of yellowed, and hyacinthed. These, by the admixture of alkalis, pass to the culminating point, and even beyond it to bluard. No instance of a culmination on the minus side has come to my knowledge in the mineral and vegetable kingdoms. In the animal kingdom, the juice of the murex is remarkable of its augmentation, and culmination on the minus side we shall hereafter have occasion to speak. pg 217. Roman 40 Fluctuation. The mutability of color is so great that even those pigments which may have been considered to be defined and arrested still admit of slight variations on one side or the other. This mutability is most remarkable near the culminating point, and is affected in a very striking manner by the alternate employment of acids and alkalis. To express this appearance, in dyeing the French make use of the word virer to turn from one side to the other. They thus very adroitly convey an idea which others attempt to express by terms indicating the component hues. The effect produced with litmus is one of the most known and striking of this kind. This coloring substance is tendered red-blue. By means of alkalis, the red-blue is very readily changed to red yellow by means of acids and again returns to its first state by again employing alkalis. The question whether a culminating point is to be discovered and arrested by pg 218 nice experiments is left to those who are practiced in these operations. Dyeing, especially scarlet dyeing, might afford a variety of examples of this fluctuation. Roman 40, one passage through the whole scale. The first excitation and gradual increase of color take place more on the plus than on the minus side, so also in passing through the whole scale color exhibits itself most on the plus side. A passage of this kind, regular and evident to the senses from yellow through red to blue, is apparent in the coloring of steel. The metals may be arrested at various points of the colorific circle by various degrees and kinds of oxidation. As they also appear green, a question arises whether chemists know any instance in the PG 219 mineral kingdom of a constant transition from yellow through green to blue, and vice versa. Oxide of iron melted with glass produces first a green, and with a more powerful heat, a blue color. We may here observe of green generally that it appears especially in an atomic sense, and certainly in a pure state when we mix blue and yellow. But again, an impure and dirty yellow soon gives us the impression of green. Yellow and black already produce green. This, however, is owing to the affinity between black and blue. An imperfect yellow, such as that of sulfur, gives us the impression of a greenish hue. Thus again, an imperfect blue appears green. The green of wine bottles arises. It appears from an imperfect union of the oxide of iron with the glass. If we produce a more complete union, by greater heat, a beautiful blue glass is the result. From all this, it appears that a certain chasm exists in nature between yellow and blue, the opposite characters of which, it is true, may be done away atomically by due immixture, and thus combined to green, but the true reconciliation between yellow and blue, it seems, only takes place by means of red. PG 220. The process, however, which appears unattainable in inorganic substances, we shall find to be possible when we turn our attention to organic productions, for in these the passage through the whole circle from yellow through green and blue to red really takes place. Roman 42. Inversion. Again, an immediate inversion or change to the totally opposite hue is a very remarkable appearance, which sometimes occurs at present. We are merely enabled to adduce what follows. The mineral chameleon, a name which has been given to an oxide of manganese, may be considered in its perfectly dry state as a green powder. If we strew it in water, the green color displays itself very beautifully in the first moment of solution, but it changes presently to the bright red opposite to green without any apparent intermediate state. PG 221. The same occurs with the sympathetic ink, which may be considered a reddish liquid, but which when dried by warmth appears as a green color on paper. In fact, this phenomenon appears to be owing to the conflict between a dry and moist state, as has been already observed. If we are not mistaken by the chemists, we may look to the improvements of time to point out what may further be deduced from these phenomena, and to show what other facts they may be connected with. Roman 43. Fixation. Mutable as we have hitherto found color to be even as a substance, yet under certain circumstances, it may at last be fixed. There are bodies capable of being entirely converted into coloring matter. Here it may be said that the color fixes itself in its own substance. PG 222 stops at a certain point, and as there defined, such coloring substances are found throughout nature. The vegetable world affords a great quantity of examples, among which some are particularly distinguished, and may be considered as the representatives of the rest, such as on the active side matter, on the passive side indigo. In order to make these materials available in use, it is necessary that the coloring quality in them should be intimately condensed, and the tinging substance refined, practically speaking, to an infinite divisibility. This is accomplished in various ways, and particularly by the well-known means of fermentation and decomposition. These coloring substances now attach themselves again to other bodies. Thus in the mineral kingdom, they adhere to earths and metallic oxides. They unite in melting with glasses, and in this case, as the light is transmitted through them, they appear in the greatest beauty, while an eternal duration may be ascribed to them. They fasten on vegetable and animal bodies with more or less power, and remain more or less PG 223, permanently, partly owing to their nature as yellow, for instance, is more evanescent than blue, or owing to the nature of the substance on which they appear. They last less in vegetable than in animal substances. And even within this latter kingdom, there are again varieties. Hemp or cotton, thread, silk, or wool exhibit very different relations to coloring substances. Here comes into the account the important operation of employing mordants, which may be considered as the intermediate agents between the color and the recipient substance. Various works on dyeing speak of this circumstantially. Suffice it to have alluded to processes by means of which the color retains a permanency, only to be destroyed with the substance, and which may even increase in brightness and beauty by use. Roman 44. Intermixture real. Every intermixture presupposes a specific state of color, and thus when we speak of intermixture, we here understand it, in an atomic PG 224 sense, we must first have before us certain bodies arrested at any given point of the colorific circle before we can produce gradations by their union. Yellow, blue, and red may be assumed as pure elementary colors already existing from these violet, orange, and green, are the simplest combined results. Some persons have taken much pains to define these intermixtures more accurately by relations of number, measure, and weight, but nothing very profitable has been thus accomplished. Painting consists strictly speaking in the intermixture of such specific coloring bodies and their infinite possible combinations, which can only be appreciated by the nicest, most practiced eye, and only accomplished under its influence. The intimate combination of these ingredients is effected in the first instance through the most perfect comminution of the material, by means of grinding, washing Roman 100, as well as by vehicles PG 225, or liquid mediums, which hold together the pulverized substance, and combine organically, as it were the unorganic. Such are the oils, resins Roman 100. Note Roman 5. If all the colors are mixed together, they retain their general character, as they are no longer seen next each other, no completeness, no harmony is experienced. The result is gray, which, like apparent color, always appears somewhat darker than white and somewhat lighter than black. This gray may be produced in various ways by mixing yellow and blue to an emerald green, and then adding pure red till all three neutralize each other, or by placing the primitive and intermediate colors next each other in a certain proportion and afterwards mixing them. That all the colors mixed together produce white is an absurdity which people have credulously been accustomed to repeat for a century, in opposition to the evidence of their senses. Colors, when mixed together, retain their PG 226 original darkness. The darker the colors, the darker will be the gray resulting from their union, till at last this gray approaches black. The lighter the colors, the lighter will be the gray which at last approaches white. Roman 45. Intermixture apparent. The intermixture which is only apparent naturally invites our attention. In connection with the foregoing, it is in many respects important, and indeed the intermixture which we have distinguished as real might be considered as merely apparent, for the elements of which the combined color consists are only too small to be considered as distinct parts. Yellow and blue powders mingled together appear green to the naked eye, but through a magnifying glass we can still perceive yellow and blue distinct from each other. Thus yellow and blue stripes, seen at a distance, present a green mass. The same observation is applicable with regard to the intermixture of other specific colors. In the description of our apparatus, we shall PG 227 have occasion to mention the wheel, by means of which the apparent intermixture is produced by rapid movement. Various colors are arranged near each other round the edge of a disc, which is made to revolve with velocity, and thus by having several such discs ready, every possible intermixture can be presented to the eye, as well as the mixture of all colors to gray, darker or lighter, according to the depth of the tints, as above explained. Physiological colors admit in like manner of being mixed with others. If, for example, we produce the blue shadow 65 on a light yellow paper, the surface will appear green. The same happens with regard to the other colors, if the necessary preparations are attended to. If, when the eye is impressed with visionary images that last for a while, we look on colored surfaces, an intermixture also takes place. The spectrum is determined to a new color, which is composed of the two. Physical colors also admit of combination. Here might be adduced the experiments in PG 228, which many-colored images are seen through the prism, as we have before shown in detail 250, 284. Those who have prosecuted these inquiries have, however, paid most attention to the appearances which take place when the prismatic colors are thrown on colored surfaces. What is seen under these circumstances is quite simple. In the first place, it must be remembered that the prismatic colors are much more vivid than the colors of the surface on which they are thrown. Secondly, we have to consider that the prismatic colors may be either homogeneous or heterogeneous with the recipient surface. In the former case, the surface deepens and enhances them, and is itself enhanced in return, as a colored stone is displayed by a similarly colored foil. In the opposite case, each vitiates, disturbs, and destroys the other. These experiments may be repeated with colored glasses, by causing the sunlight to shine through them on colored surfaces. In every instance, similar results will appear. Pg 229. The same effect takes place when we look on colored objects through colored glasses, the colors being thus, according to the same conditions, enhanced, subdued, or neutralized. If the prismatic colors are suffered to pass through colored glasses, the appearances that take place are perfectly analogous in these cases, more or less force, more or less light, and dark. The clearness and cleanness of the glass are all to be allowed for, as they produce many delicate varieties of effect. These will not escape the notice of every accurate observer who takes sufficient interest in the inquiry to go through the experiments. It is scarcely necessary to mention that several colored glasses, as well as oiled or transparent papers, placed over each other, may be made to produce and exhibit every kind of intermixture at pleasure. Lastly, the operation of glazing in painting belongs to this kind of intermixture. By this means, a much more refined union may be produced than that arising from the mechanical atomic mixture, which is commonly employed. Pg 230. Roman 46. Communication actual. Having now provided the coloring materials as before shown, a further question arises how to communicate these to colorless substances. The answer is of the greatest importance, from the connection of the object with the ordinary wants of men with useful purposes, and with commercial and technical interests. Here again, the dark quality of every color again comes into the account, from a yellow that is very near to white through orange, and the hue of minium to pure red and carmine, through all gradations of violet to the deepest blue, which is almost identified with black color, still increases in darkness. Blue, once defined, admits of being diluted, made light united with yellow, and then as green it approaches the light side of the scale, but this is by no means according to its own nature. In the physiological colors, we have already seen that they are less than the light, inasmuch Pg 231, as they are a repetition of an impression of light. Nay, at last, they leave this impression quite as a dark. In physical experiments, the employment of semi-transparent mediums, the effect of semi-transparent accessory images, taught us that in such cases we have to do with a subdued light, with a transition to darkness. In treating of the chemical origin of pigments, we found that the same effect was produced on the very first excitement. The yellow tinge, which mantles over the steel, already darkens the shining surface. In changing white lead to massicate it, is evident that the yellow is darker than white. This process is in the highest degree delicate. The growing intenseness, as it still increases, tinges the substance more and more intimately and powerfully, and thus indicates the extreme fineness and the infinite divisibility of the colored atoms. The colors which approach the dark side, and consequently blue in particular, can be made to approximate to black. In fact, a very perfect Prussian blue, or an indigo acted on by vitriolic acid, appears almost as a black. Pg 232. A remarkable appearance may be here adverted to pigments in their deepest and most condensed state, especially those produced from the vegetable kingdom, such as the indigo just mentioned, or madder, carried to its intensest hue, no longer show their own color. On the contrary, a decided metallic shine is seen on their surface, in which the physiological compensatory color appears. All good indigo exhibits a copper color in its fracture, a circumstance attended to as a known characteristic in trade. Again, the indigo, which has been acted on by sulfuric acid, if thickly laid on or suffered to dry, so that neither white paper nor the porcelain can appear through, exhibits a color approaching to orange. The bright red Spanish rouge, probably prepared from madder, exhibits on its surface a perfectly green metallic shine. If this color, or the blue before mentioned, is washed with a pencil on porcelain or paper, it is seen in its real state owing to the bright ground shining through. Colored liquids appear black when no light. Pg 233 is transmitted through them, as we may easily see in cubic tin vessels with glass bottoms. In these, every transparent colored infusion will appear black and colorless if we place a black surface under them. If we contrive that the image of a flame be reflected from the bottom, the image will appear colored. If we lift up the vessel and suffer the transmitted light to fall on white paper under it, the color of the liquid appears on the paper. Every light ground seen through such a colored medium exhibits the color of the medium. Thus every color, in order to be seen, must have a light within or behind it. Hence, the lighter and brighter the grounds are, the more brilliant the colors appear. If we pass lac varnish over a shining white metal surface, as the so-called foils are prepared, the splendor of the color is displayed by this internally reflected light as powerfully as in any prismatic experiment. Nay, the force of the physical colors is owing principally to the circumstance that light is always acting with and behind them. Lichtenberg, who of necessity followed the pg 234, received theory owing to the time and circumstances in which he lived, was yet too good an observer, and too acute not to explain and classify after his fashion what was evident to his senses. He says in the preface to De Laval, "It appears to me also on other grounds probable, that our organ, in order to be impressed by a color, must at the same time be impressed by all light white. To procure white as a ground is the chief business of the dyer. Every color may be easily communicated to colorless earths, especially to alum, but the dyer has especially to do with animal and vegetable products as the ground of his operations. Everything living tends to colordo local specific color, to effect to oppositivating the minutest atoms. Everything in which life is extinct approximates to white 494 to the abstract, the general state to clearness 1 to transparence. How this is put in practice in technical operations remains to be adverted to in the chapter on the privation of color. With regard to the pg 235 communication of color, we have especially to bear in mind that animals and vegetables in a living state produce colors, and hence their substances, if deprived of colors, can the more readily reassume them. Roman 47 Communication apparent. The communication of colors, real as well as apparent, corresponds, as may easily be seen with their intermixture. We need not therefore repeat what has been already sufficiently entered into. Yet we may here point out more circumstantially the importance of an apparent communication, which takes place by means of reflection. This phenomenon is well known, but still it is pregnant with inferences, and is of the greatest importance, both to the investigator of nature and to the painter. Let a surface colored with any one of the positive colors be placed in the sun, and let its pg 236 reflection be thrown on other colorless objects. This reflection is a kind of subdued light, a half-light, a half-shadow which in a subdued state reflects the colors in question. If this reflection acts on light surfaces, it is so far overpowered that we can scarcely perceive the color which accompanies it. But if it acts on shadowed portions, a sort of magical union takes place with the shadow, is the proper element of color. And in this case, a subdued color approaches it, lighting up, tinging, and enlivening it, and thus arises an appearance as powerful as agreeable, which may render the most pleasing service to the painter, who knows how to make use of it. These are the types of the so-called reflexes, which were only noticed late in the history of art, and which have been too seldom employed in their full variety. The schoolmen called these colors notionals and intentionals, and the history of the doctrine of colors will generally show that the old inquirers already observed the phenomena well enough and knew how to distinguish them properly, although the whole method of treating such subjects is very different from ours. pg 237. Roman 48 Extraction. Color may be extracted from substances, whether they possess it naturally or by communication in various ways. We have thus the power to remove it intentionally for a useful purpose, but on the other hand, it often flies contrary to our wish. Not only are the elementary earths in their natural state white, but vegetable and animal substances can be reduced to a white state, without disturbing their texture. A pure white is very desirable for various uses, as in the instance of our preferring to use linen and cotton stuffs uncolored. In like manner some silk stuffs, paper, and other substances are. The more agreeable the whiter they can be. Again, the chief basis of all dyeing consists in white grounds. For these reasons, manufacturers, aided by accident and contrivance, have devoted themselves assiduously to discover means of extracting color. Infinite experiments have been made in connection with this object, and many important facts have been arrived at. pg 238. It is in accomplishing this entire extraction of color that the operation of bleaching consists, which is very generally practiced empirically or methodically. We will here shortly state the leading principles. Light is considered as one of the first means of extracting color from substances, and not only the sunlight but the mere powerless daylight, for as both lights, direct light of the sun as well as the derived light of the Skycandle Bologna phosphorus, so both act on colored surfaces, whether the light attacks the color allied to it, and as it were kindles and consumes it, thus reducing the definite quality to a general state, or whether some other operation unknown to us takes place. It is clear that light exercises a great power on colored surfaces, and bleaches them more or less here. However, the different colors exhibit a different degree of durability. Yellow, especially if prepared from certain materials, is in this case the first to fly. Not only light, but air and especially water act strongly in destroying color. It has been even asserted that thread well soaked, and PG 239 spread on the grass at night bleaches better than that which is exposed after soaking to the sunlight. Thus in this case, water proves to be a solving and conducting agent, removing the accidental quality and restoring the substance to a general or colorless state. The extraction of color is also affected by reagent. Spirits of wine has a peculiar tendency to attract the juice which tinges plants and becomes colored with it, often in a very permanent manner. Sulfuric acid is very efficient in removing color, especially from wool and silk, and everyone is acquainted with the use of sulfur vapors in bleaching. The strongest acids have been recommended more recently as more expeditious agents in bleaching. The alkaline reagents produce the same effects, by contrary means lixiviums, alone oils and fat, combined with lixiviums to soap, and so forth. Before we dismiss this subject, we observe PG 240 that it may be well worth while to make certain delicate experiments as to how far light and air exhibit their action in the removal of color. It might be possible to expose colored substances to the light under glass bells, without air or filled with common or particular kinds of air. The colors might be those of known fugacity, and it might be observed whether any of the volatilized color attached itself to the glass, or was otherwise perceptible as a deposit or precipitate, whether again in such a case, this appearance would be perfectly like that which had gradually ceased to be visible, or whether it had suffered any change. Skillful experimentalists might devise various contrivances with a view to such researches. Having thus first considered the operations of nature as subservient to our proposes, we add a few observations on the modes in which they act against us. The art of painting is so circumstanced that the most beautiful results of mind and labor are altered and destroyed in various ways, by time. Hence, great pains have been always taken to find durable pigments, and so to unite them with each other, and with their ground that their PG 241 permanency might be further ensured. The technical history of the schools of painting affords sufficient information on this point. We may here too mention a minor art to which in relation to dyeing, we are much indebted, namely the weaving of tapestry, as the manufacturers were enabled to imitate the most delicate shades of pictures, and hence often brought the most variously colored materials together. It was soon observed that the colors were not all equally durable, but that some faded from the tapestry more quickly than others. Hence the most diligent efforts were made to ensure an equal permanency to all the colors and their gradations. This object was especially promoted in France under Colbert, whose regulations to this effect constitute an epoch in the history of dyeing. The gay dye, which only aimed at a transient beauty, was practiced by a particular guild. On the other hand, great pains were taken to define the technical processes which promised durability. And thus, after considering the artificial extraction, the evanescence, and the perishable nature of brilliant appearances of color, we are again returned to the desideratum of permanency. PG 242. Roman nomenclature. After what has been adduced respecting the origin, the increase, and the affinity of colors, we may be better enabled to judge what nomenclature would be desirable in future, and what might be retained of that hitherto in use. The nomenclature of colors, like all other modes of designation, but especially those employed to distinguish the objects of sense, proceeded in the first instance from particular to general, and from general back again to particular terms. The name of the species became a generic name to which the individual was again referred. This method might have been followed in consequence of the mutability and uncertainty of ancient modes of expression, especially since, in the early ages, more reliance may be supposed to have been placed on the vivid impressions of sense. The qualities of objects were described indistinctly, because they were impressed clearly on every imagination. PG 243. The pure chromatic circle was limited, It is true but specific, as it appears to have been applied to innumerable objects, while it was circumscribed by qualifying characteristics. If we take a glance at the copiousness of the Greek and Roman terms, we shall perceive how mutable the words were, and how easily each was adapted to almost every point in the colorific circle note W. In modern ages, terms for many new gradations were introduced, in consequence of the various operations of dyeing even the colors of fashion, and their designations represented an endless series of specific hues. We shall on occasion employ the chromatic terminology of modern languages, whence it will appear that the aim has gradually been to introduce more exact definitions, and to individualize and arrest a fixed and specific state by language equally distinct. With regard to the German terminology, it has the advantage of possessing 4 monosyllabic names, no longer to be traced to their origin, viz. Yellow, gelb, blue, red, green. They represent the most general idea of color to the imagination, without reference to any very specific modification. pg 244. If we were to add 2 other qualifying terms to each of these 4 as thus red yellow, and yellowed red blue, and blued yellow green, and green yellow blue green, and green blue, one we should express the gradations of the chromatic circle with sufficient distinctness. And if we were to add the designations of light and dark, and again define in some measure the degree of purity or its opposite by the monosyllables black, white, gray, brown, we should have a tolerably sufficient range of expressions to describe the ordinary appearances presented to us, without troubling ourselves whether they were produced dynamically or atomically. The specific and proper terms in use might, however, still be conveniently employed, and we have thus made use of the words orange and violet. We have in like manner employed the word purpur to designate a pure central red, because the secretion of the murex or purpura is to be carried to the highest point of culmination by the action of the sunlight on fine linen, saturated with the juice. pg 245. Roman 50 minerals. The colors of minerals are all of a chemical nature, and thus the modes in which they are produced may be explained in a general way by what has been said on the subject of chemical colors. Among the external characteristics of minerals, the description of their colors occupies the first place, and great pains have been taken in the spirit of modern times to define and arrest every such appearance exactly. By this means, however, new difficulties it appears to us have been created, which occasion no little inconvenience in practice. It is true this precision, when we reflect how it arose, carries with it its own excuse. The painter has at all times been privileged in the use of colors, the few specific hues in themselves admitted of no change, but from these innumerable gradations were artificially produced, which imitated the surface of natural objects. It was therefore not to be wondered, pg 246, at that these gradations should also be adopted as criterions, and that the artist should be invited to produce tinted patterns with which the objects of nature might be compared and according to which they were to receive their designations. But after all, the terminology of colors which has been introduced in mineralogy is open to many objections. The terms, for instance, have not been borrowed from the mineral kingdom, as was possible enough in most cases, but from all kinds of visible objects. Too many specific terms have been adopted, and in seeking to establish new definitions, by combining these, the nomenclators have not reflected that they thus altogether efface the image from the imagination and the idea from the understanding. Lastly, these individual designations of colors, employed to a certain extent, as elementary definitions, are not arranged in the best manner, as regards their respective derivation from each other. Hence, the scholar must learn every single designation, and impress an almost lifeless but positive language on his memory. The further consideration of this would be too foreign to our present subject. 1. pg 247. Roman 51 plants. The colors of organic bodies in general may be considered as a higher kind of chemical operation, for which reason the ancients employed the word concoction to designate the process. All the elementary colors, as well as the combined and secondary hues, appear on the surface of organic productions, while on the other hand, the interior, if not colorless, appears strictly speaking negative when brought to the light. As we propose to communicate our views respecting organic nature to a certain extent in another place, we only insert here what has been before connected with the doctrine of colors, while it may serve as an introduction to the further consideration of the views alluded to and first of plants. Seeds, bulbs, roots, and what is generally shut out from the light, or immediately surrounded by the earth, appear for the most part white. Plants reared from seed in darkness are white or approaching to yellow light. On the pg 248 other hand, in acting on their colors, acts at the same time on their form. Plants which grow in darkness make it as true long shoots from joint to joint, but the stems between two joints are thus longer than they should be. No side stems are produced, and the metamorphosis of the plant does not take place. Light, on the other hand, places it at once in an active state. The plant appears green, and the course of the metamorphosis proceeds uninterruptedly to the period of reproduction. We know that the leaves of the stem are only preparations and presignifications of the instruments of florification and fructification, and accordingly, we can already see colors in the leaves of the stem, which as it were announce the flower from afar, as is the case in the amaranthus. There are white flowers whose petals have wrought or refined themselves to the greatest purity. There are colored ones, in which the pg 249 elementary hues may be said to fluctuate to and fro. There are some which, in tending to the higher state, have only partially emancipated themselves from the green of the plant. Flowers of the same genus, and even of the same kind, are found of all colors. Roses, and particularly mallows, for example, vary through a great portion of the colorific circle from white to yellow, then through reedy yellow to bright red, and from thence to the darkest hue it can exhibit as it approaches blue. Others already begin from a higher degree in the scale, as for example the poppy, which is yellowed in the first instance, and which afterwards approaches a violet hue. Yet the same colors in species varieties, and even in families and classes, if not constant, are still predominant. Especially, the yellow color blue is throughout rarer. A process somewhat similar takes place in the juicy capsule of the fruit, for it increases in color from the green through the yellowish pg 250, and yellow up to the highest red, the color of the rind, thus indicating the degree of ripeness. Some are colored all round, some only on the sunny side, in which last case the augmentation of the yellow into red, the gradations crowding in and upon each other, may be very well observed. Many fruits too are colored internally. Pure red juices especially are common. The color which is found superficially in the flower and penetratingly in the fruit spreads itself through all the remaining parts, coloring the roots and the juices of the stem, and this with a very rich and powerful hue. So again, the color of the wood passes from yellow through the different degrees of red up to pure red, and on to brown. Blue woods are unknown to me. And thus, in this degree of organization, the active side exhibits itself powerfully, although both principles appear balanced in the general green of the plant. We have seen above that the germ pushing pg 251 from the earth is generally white and yellowish, but that by means of the action of light and air, it acquires a green color. The same happens with young leaves of trees, as may be seen for example in the birch, the young leaves of which are yellowish, and if boiled yield a beautiful yellow juice. Afterwards they become greener, while the leaves of other trees become gradually blue-green. Thus, a yellow ingredient appears to belong more essentially to leaves than a blue one, for this last vanishes in the autumn, and the yellow of the leaf appears changed to a brown color. Still more remarkable, however, are the particular cases where leaves in autumn again become pure yellow, and others increase to the brightest red. Other plants again may by artificial treatment be entirely converted to a coloring matter, which is as fine, active, and infinitely divisible as any other. Indigo and matter with which so much is affected are examples. Lichens are also used for dyes. To this fact another stands immediately opposed. pg 252, we can namely extract the coloring part of plants, and as it were exhibited apart, while the organization does not on this account appear to suffer at all. The colors of flowers may be extracted by spirits of wine, and tinge it, the petals meanwhile becoming white. There are various modes of acting on flowers, and their juices by reagents. This has been done by Boyle in many experiments. Roses are bleached by sulfur, and may be restored to their first state by other acids. Roses are turned green by the smoke of tobacco. Roman 52. Worms, insects, fishes. With regard to creatures belonging to the lower degrees of organization, we may first observe that worms which live in the earth and remain in darkness and cold moisture are imperfectly negatively colored. Worms bred in warm moisture and darkness are colorless. Light seems expressly necessary to the definite exhibition of color. pg 253. Creatures which live in water, which although a very dense medium suffers sufficient light to pass through, it appear more or less colored zoophytes, which appear to animate the purest calcareous earth, are mostly white, yet we find corals deepened into the most beautiful yellowed in other cells of worms. This color increases nearly to bright red. The shells of the crustaceous tribe are beautifully designed and colored, yet it is to be remarked that neither land snails nor the shells of crustacea of fresh water are adorned with such bright colors as those of the sea. In examining shells, particularly such as our spiral, we find that a series of animal organs similar to each other must have moved increasingly forward, and in turning on an axis, produced the shell in a series of chambers, divisions, tubes, and prominences, according to a plan for ever growing larger. We remark, however, that a tinging juice must have accompanied the development of these organs, a juice which marked the surface of the shell, probably through the immediate cooperation of the seawater, with colored lines, points, spots, and shadings. pg 254. This must have taken place at regular intervals, and thus left the indications of increasing growth lastingly on the exterior. Meanwhile, the interior is generally found white or only faintly colored. That such a juice is to be found in shellfish is besides sufficiently proved by experience, for the creatures furnish it in its liquid and coloring state. The juice of the inkfish is an example, but a much stronger is exhibited in the red juice, found in many shellfish, which was so famous in ancient times, and has been employed with advantage by the moderns. There is it appears in the entrails of many of the crustaceous tribe, a certain vessel which is filled with a red juice. This contains a very strong and durable coloring substance, so much so that the entire creature may be crushed and boiled. And yet out of this broth, a sufficiently strong tinging liquid may be extracted, but the little vessel filled with color may be separated from the animal, by which means, of course, a concentrated juice is gained. This juice has the property that when exposed to light and air it appears first yellowish, then greenish, it then passes to blue, then to a pg 255 violet, gradually growing redder, and lastly by the action of the sun, and especially if transferred to cambric, it assumes a pure bright red color. Thus we should here have an augmentation even to culmination on the minus side, which we cannot easily meet with in inorganic cases. Indeed, we might almost call this example a passage through the whole scale, and we are persuaded that by due experiments the entire revolution of the circle might really be effected, for there is no doubt that by acids duly employed the pure red may be pushed beyond the culminating point towards scarlet. This juice appears on the one hand to be connected with the phenomena of reproduction, eggs being found the embryos of future shellfish, which contain a similar coloring principle. On the other hand, in animals ranking higher in the scale of being, the secretion appears to bear some relation to the development of the blood. The blood exhibits similar properties. In regard to color, in its thinnest state it appears yellow thickened, as it is found in the veins it appears red, while the arterial blood exhibits a brighter red, probably owing to the oxidation pg 256, which takes place by means of breathing. The venous blood approaches more to violet, and by this mutability denotes the tendency to that augmentation and progression which are now familiar to us. Before we quit the element whence we derived the foregoing examples, we may add a few observations on fishes, whose scaly surface is colored either altogether in stripes or in spots, and still oftener exhibits a certain iridescent appearance, indicating the affinity of the scales with the coats of shellfish, mother of pearl, and even the pearl itself. At the same time, it should not be forgotten that warmer climates, the influence of which extends to the watery regions, produce, embellish, and enhance these colors in fishes in a still greater degree. In Ottahate Forster observed fishes with beautifully iridescent surfaces, and this effect was especially apparent at the moment when the fish died. We may here call to mind the hues of the chameleon and other similar appearances, for when similar facts are presented together, we are better enabled to trace them. Lastly, although not strictly in the same pg 257 class, the iridescent appearance of certain mollusks may be mentioned, as well as the phosphorescence, which in some marine creatures, it is said, becomes iridescent just before it vanishes. We now turn our attention to those creatures which belong to light, air, and dry warmth, and it is here that we first find ourselves in the living region of colors. Here, in exquisitely organized parts, the elementary colors present themselves in their greatest purity and beauty. They indicate, however, that the creatures they adorn are still low in the scale of organization. Precisely, Because these colors can thus appear, as it were unwrought here too heat seems to contribute much to their development. We find insects which may be considered altogether as concentrated coloring matter, among these the cochineals especially, are celebrated with regard to these. We observe that their mode of settling on vegetables, and even nestling in them at the same time, produces those excrescences which are so useful as mordants in fixing colors. Pg 258. But the power of color accompanied by regular organization exhibits itself in the most striking manner in those insects, which require a perfect metamorphosis for their development in scarab, and especially in butterflies. These last, which might be called true productions of light and air, often exhibit the most beautiful colors even in their chrysalis state, indicating the future colors of the butterfly, a consideration which, if pursued further hereafter, must undoubtedly afford a satisfactory insight into many a secret of organized being. If again we examine the wings of the butterfly more accurately, and in its net-like web, discover the rudiments of an arm, and observe further the mode in which this as it were flattened arm is covered with tender plumage, and constituted an organ of flying, we believe, we recognize a law according to which the great variety of tints is regulated. This will be a subject for further investigation hereafter. That again heat generally has an influence Pg 259 on the size of the creature, on the accomplishment of the form, and on the greater beauty of the colors, hardly needs to be remarked. Roman 53 birds. The more we approach the higher organizations, the more it becomes necessary to limit ourselves to a few passing observations, for all the natural conditions of such organized beings are the result of so many premises that without having at least hinted at these, our remarks would only appear daring, and at the same time insufficient. We find in plants that the consummate flower and fruit are as it were rooted in the stem, and that they are nourished by more perfect juices than the original roots first afforded. We remark too that parasitical plants which derive their support from organized structures exhibit themselves especially endowed as to their energies and qualities. We might in some sense compare the feathers of birds with plants of this description. The feathers spring up as a last structural result from the surface of a body Pg 260, which has yet much in reserve for the completion of the external economy, and thus are very richly endowed organs. The quills not only grow proportionally to a considerable size, but are throughout branched, by which means they properly become feathers, and many of these feathered branches are again subdivided, thus again recalling the structure of plants. The feathers are very different in shape and size, but each still remains the same organ forming and transforming itself according to the constitution of the part of the body from which it springs. With the form the color also becomes changed, and a certain law regulates the general order of hues, as well as that particular distribution by which a single feather becomes parti-colored. It is from this that all combination of variegated plumage arises, and whence at last the eyes in the peacock's tail are produced. It is a result similar to that which we have already unfolded in treating of the metamorphosis of plants, and which we shall take an early opportunity to prove. Pg 261. Although time and circumstances compel us here to pass by this organic law, yet we are bound to refer to the chemical operations, which commonly exhibit themselves in the tinting of feathers, in a mode now sufficiently known to us. Plumage is of all colors, yet on the whole yellow deepening to red, is commoner than blue. The operation of light on the feathers and their colors is to be remarked in all cases. Thus, for example, the feathers on the breast of certain parrots are strictly yellow. The scale-like anterior portion, which is acted on by the light, is deepened from yellow to red. The breast of such a bird appears brighted, but if we blow into the feathers, the yellow appears. The exposed portion of the feathers is in all cases very different from that which in a quiet state is covered. It is only the exposed portion, for instance in ravens, which exhibits the iridescent appearance. The covered portion does not, from which indication the feathers of the tail, when ruffled together, may be at once placed in the natural order again. Pg 262. Roman 54. Mammalia and human beings. Here the elementary colors begin to leave us altogether. We are arrived at the highest degree of the scale, and shall not dwell on its characteristics long. An animal of this class is distinguished among the examples of organized being. Everything that exhibits itself about him is living. Of the internal structure we do not speak, but confine ourselves briefly to the surface. the hairs are already distinguished from feathers inasmuch as they belong more to the skin inasmuch as they are simple thread-like, not branched. They are however like feathers shorter, longer, softer, and firmer, colorless or colored, and all this in conformity to laws which might be defined. White and black, yellow, yellowed and brown alternate in various modifications, but they never appear in such a state as to remind us of the elementary hues. On the contrary, pg 263, they are all broken colors subdued by organic concoction, and thus denote more or less the perfection of life in the being they belong to. One of the most important considerations connected with morphology, so far as it relates to surfaces, is this, that even in quadrupeds the spots of the skin have a relation with the parts underneath them capriciously as nature here appears on a hasty examination to operate. She nevertheless consistently observes a secret law. The development and application of this, it is true, are reserved only for accurate and careful investigation and sincere cooperation. If in some animals portions appear variegated with positive colors, this of itself shows how far such creatures are removed from a perfect organization, for it may be said the nobler a creature is, the more all the mere material of which he is composed is disguised by being wrought together, the more essentially his surface corresponds with the internal organization, the less can it exhibit the elementary colors. Where all tends to make up a perfect whole, any detached specific developments cannot take place. Of man we have little to say, for he is entirely pg 264, distinct from the general physiological results, of which we now treat so much in this case, is in affinity with the internal structure, that the surface can only be sparingly endowed. When we consider that brutes are rather encumbered than advantageously provided with intercutaneous muscles, when we see that much that is superfluous tends to the surface, as for instance large ears and tails, as well as hair manes, tufts, we see that nature in such cases had much to give away and to lavish. On the contrary, the general surface of the human form is smooth and clean, and thus in the most perfect examples, the beautiful forms are apparent. For it may be remarked in passing that a superfluity of hair on the chest, arms, and lower limbs rather indicates weakness than strength. Poets only have sometimes been induced, probably, by the example of the fairy nature, so strong in other respects, to extol similar attributes in their rough heroes. But we have here chiefly to speak of color, and observe that the color of the human skin in all its varieties is never an elementary color pg 265, but presents by means of organic concoction a highly complicated result. Note Roman 10. That the color of the skin and hair has relation with the differences of character is beyond question, and we are led to conjecture that the circumstance of one or other organic system predominating produces the varieties. We see a similar hypothesis may be applied to nations, in which case it might perhaps be observed that certain colors correspond with certain conformations, which has always been observed of the Negro physiognomy. Lastly, we might here consider the problematical question whether all human forms and hues are not equally beautiful, and whether custom and self-conceit are not the causes why one is preferred to another. We venture, however, after what has been adduced, to assert that the white man, that is, he whose surface varies from white to reddish, yellowish, brownish, in short, whose surface appears most neutral in hue, and least inclines to any particular or positive color, is the most beautiful. On the same principle, a similar point of perfection in human conformation may be defined hereafter. When the question relates to form, we do not pg 266 imagine that this long-disputed question is to be thus once for all settled, for there are persons enough who have reason to leave this significancy of the exterior in doubt, but we thus express a conclusion derived from observation and reflection, such as might suggest itself to a mind aiming at a satisfactory decision. We subjoin a few observations connected with the elementary chemical doctrine of colors. Note Y. Roman 55. Physical and chemical effects of the transmission of light through colored mediums. The physical and chemical effects of colorless light are known, so that it is unnecessary here to describe them at length. Colorless light exhibits itself under various conditions as exciting warmth, as imparting a luminous quality to certain bodies, as promoting oxidation and deoxidation. In the modes and degrees of these effects, many varieties take place, but no difference is found indicating a principle of contrast, such as we find in the transmission of colored light. We proceed briefly to advert to this. PG 267. Let the temperature of a dark room be observed by means of a very sensible air thermometer. If the bulb is then brought to the direct sunlight, as it shines into the room, nothing is more natural than that the fluid should indicate a much higher degree of warmth. If upon this we interpose colored glasses, it follows again quite naturally that the degree of warmth must be lowered first, because the operation of the direct light is already somewhat impeded by the glass, and again, more especially because a colored glass as a dark medium admits less light through it. But here a difference in the excitation of warmth exhibits itself to the attentive observer according to the color of the glass. The yellow and the yellowed glasses produce a higher temperature than the blue, and bluered the difference being considerable. This experiment may be made with the prismatic spectrum, the temperature of the room being first remarked on the thermometer. The blue-colored light is made to fall on the bulb when a somewhat higher degree of warmth is exhibited, which still increases as the other colors PG 268 are gradually brought to act on the mercury if the experiment is made with the water prism, so that the white light can be retained in the center. This refracted indeed, but not yet colored light, is the warmest. The other colors stand in relation to each other as before. As we here merely describe without undertaking to deduce or explain this phenomenon, we only remark in passing that the pure light is by no means abruptly and entirely at an end with the red division in the spectrum, but that a refracted light is still to be observed deviating from its course, and as it were insinuating itself beyond the prismatic image, so that on closer examination it will hardly be found necessary to take refuge in invisible rays and their refraction. The communication of light by means of colored mediums exhibits the same difference. The light communicates itself to Bologna phosphorus through blue and violet glasses, but by no means through yellow and yellowed glasses. It has been even remarked that the phosphori which have been rendered luminous under violet and blue glasses become sooner extinguished, when afterwards placed under yellow and yellowed glasses, than those which have been PG 269 suffered to remain in a dark room without any further influence. These experiments, like the foregoing, may also be made by means of the prismatic spectrum when the same results take place. To ascertain the effect of colored light on oxidation and deoxidation, the following means may be employed. Let moist perfectly white muriate of silver 1 be spread on a strip of paper, place it in the light so that it may become to a certain degree gray, and then cut it in 3 portions of these. 1 may be preserved in a book as a specimen of this state. Let another be placed under a yellowed, and the third under a blued glass. The last will become a darker gray, and exhibit a deoxidation. The other under the yellowed glass will on the contrary become a lighter gray, and thus approach nearer to the original state of more perfect oxidation. The change in both may be ascertained by a comparison with the unaltered specimen. An excellent apparatus has been contrived to PG 270 perform these experiments with the prismatic image. The results are analogous to those already mentioned, and we shall hereafter give the particulars, making use of the labors of an accurate observer who has been for some time carefully prosecuting these experiments. 2. Roman 56 Chemical effect in dioptrical achromatism. We first invite our readers to turn to what has been before observed on the subject 280, 298, to avoid unnecessary repetition here. We can thus give a glass the property of producing much whiter colored edges, without refracting more strongly than before, that is, without displacing the object much more perceptibly. This property is communicated to the glass by means of metallic oxides. Minium melted and thoroughly united with a pure glass produces PG 271 this effect, and thus flintglass 291 is prepared with oxide of lead. Experiments of this kind have been carried farther, and the so-called butter of antimony, which according to a new preparation may be exhibited as a pure fluid, has been made use of in hollow lenses and prisms, producing a very strong appearance of color with a very moderate refraction, and presenting the effect which we have called hyperchromatism in a very vivid manner. In common glass, the alkaline nature obviously preponderates, since it is chiefly composed of sand and alkaline salts. Hence a series of experiments exhibiting the relation of perfectly alkaline fluids to perfect acids might lead to useful results. For could the maximum and minimum be found, it would be a question whether a refracting medium could not be discovered, in which the increasing and diminishing appearance of color, an effect almost independent of refraction, could not be done away with altogether, while the displacement of the object would be unaltered. How desirable, therefore, it would be with pg 272 regard to this last point, as well as for the elucidation of the whole of this third division of our work, and indeed for the elucidation of the doctrine of colors, generally, that those who are occupied in chemical researches with new views ever opening to them should take this subject in hand, pursuing into more delicate combinations what we have only roughly hinted at, and prosecuting their inquiries with reference to science as a whole. pg 273. Part Roman 4. General characteristics. We have hitherto in a manner forcibly kept phenomena asunder, which partly from their nature, partly in accordance with our mental habits, have as it were constantly sought to be reunited. We have exhibited them in three divisions. We have considered colors first as transient, the result of an action and reaction in the eye itself, next as passing effects of colorless light transmitting, transparent or opaque mediums, on light, especially on the luminous image. Lastly, we arrived at the point where we could securely pronounce them as permanent and actually inherent in bodies. In following this order, we have as far as possible endeavored to define, to separate, and to class the appearances, but now that we need no longer be apprehensive of mixing or confounding them, we may proceed first to state the general nature of these appearances, considered abstractedly as an independent circle of facts, and in the next place, to show how this particular circle is connected with other classes of analogous phenomena in nature. pg 274. The facility with which color appears. We have observed that color under many conditions appears very easily. The susceptibility of the eye with regard to light, the constant reaction of the retina against it, produce instantaneously a slight iridescence. Every subdued light may be considered as colored, nay, we ought to call any light colored, inasmuch as it is seen colorless. Light, colorless surfaces are in some sort abstract ideas. In actual experience, we can hardly be said to be aware of them. Note Z. If light impinges on a colorless body, is reflected from it, or passes through it, color immediately appears. But it is necessary here to remember what has been so often urged by us, namely, that the leading conditions of refraction, reflection, Roman 100, are not of themselves sufficient to produce the appearance. Sometimes it is true light acts with these merely as light, but oftener as a defined circumscribed appearance, as a luminous image. The semi-opacity of the medium is often a necessary condition, while half and double shadows are required for many colored appearances. In all cases, however, color appears instantaneously. We find again that by means of pressure, breathing, heat, 432, 471, by various kinds of motion, and pg 275, alteration on smooth, clean surfaces, 461, as well as on colorless fluids, 470, color is immediately produced. The slightest change has only to take place in the component parts of bodies, whether by a mixture with other particles or other such effects, and color either makes its appearance or becomes changed. The force of color. The physical colors, and especially those of the prism, were formerly called colors emphatici, on account of their extraordinary beauty and force. Strictly speaking, however, a high degree of effect may be ascribed to all appearances of color, assuming that they are exhibited under the purest and most perfect conditions. The dark nature of color, its full rich quality, is what produces the grave, and at the same time fascinating impression we sometimes experience, and as color is to be considered a condition of light, so it cannot dispense with light as the cooperating cause of its appearance, as its basis or ground, as a power, thus displaying and manifesting color. pg 276. The definite nature of color. The existence and the relatively definite character of color are one and the same thing. Light displays itself, and the face of nature, as it were, with a general indifference, informing us as to surrounding objects perhaps devoid of interest or importance, but color is at all times specific, characteristic, significant. Considered in a general point of view, color is determined towards one of two sides. It thus presents a contrast which we call a polarity, and which we may fitly designate by the expressions plus and minus. Plus, minus. Yellow, blues. Action, negation, 1. Light, shadow. Brightness, darkness. Force, weakness. Warmth, coldness. Proximity, distance. Repulsion, attraction. Affinity with acids, affinity with alkalis. pg 277. Combination of the two principles. If these specific contrasted principles are combined, the respective qualities do not therefore destroy each other, for if in this intermixture the ingredients are so perfectly balanced that neither is to be distinctly recognized, the union again acquires a specific character. It appears as a quality by itself, in which we no longer think of combination. This union we call green. Thus, if two opposite phenomena springing from the same source do not destroy each other when combined, but in their union present a third appreciable and pleasing appearance, this result at once indicates their harmonious relation. The more perfect result yet remains to be adverted to. Augmentation to red. Blue and yellow do not admit of increased intensity without presently exhibiting a new appearance. In addition to their own, each color in its lightest state is a dark. If condensed, it must become darker. But this effect no sooner takes place than the hue assumes an appearance which we designate by the word reddish. pg 278. This appearance still increases so that when the highest degree of intensity is attained, it predominates over the original hue. A powerful impression of light leaves the sensation of red on the retina in the prismatic yellowed, which springs directly from the yellow. We hardly recognize the yellow. This deepening takes place again by means of colorless semi-transparent mediums, and here we see the effect in its utmost purity and extent. Transparent fluids, colored with any given hues, in a series of glass vessels exhibit it very strikingly. The augmentation is unremittingly rapid and constant. It is universal, and obtains in physiological as well as in physical and chemical colors. Junction of the two augmented extremes. As the extremes of the simple contrast produce a beautiful and agreeable appearance by their union, so the deepened extremes on being united will present a still more fascinating color. Indeed, it might naturally be expected that we should here find the acme of the whole phenomenon. pg 279. Completeness, the result of variety. And such is the fact, for pure red appears a color to which from its excellence we have appropriated the term purpur too. There are various modes in which pure red may appear by bringing together the violet edge and yellowed border in prismatic experiments, by continued augmentation in chemical operations, and by the organic contrast in physiological effects. As a pigment, it cannot be produced by intermixture or union, but only by arresting the hue in substances chemically acted on at the high culminating point. Hence, the painter is justified in assuming that there are three primitive colors from which he combines all the others. The natural philosopher, on the other hand, assumes only two elementary colors from which he in like manner develops and combines the rest. Completeness, the result of variety in color. The various appearances of color arrested in pg 280, their different degrees, and seen in juxtaposition, produce a whole. This totality is harmony to the eye. The chromatic circle has been gradually presented to us. The various relations of its progression are apparent to us. Two pure original principles in contrast are the foundation of the whole. In augmentation manifests itself by means of which both approach a third state. Hence there exists on both sides a lowest and highest, a simplest and most qualified state. Again, two combinations present themselves, first that of the simple primitive contrasts, then that of the deepened contrasts. Harmony of the complete state. The whole ingredients of the chromatic scale seen in juxtaposition produce an harmonious impression on the eye. The difference between the physical contrast and harmonious opposition in all its extent should not be overlooked. The first resides in the pure restricted original dualism, considered in its antagonizing elements. The other results from the fully developed effects of the complete state. Every single opposition, in order to be harmonious, must comprehend the whole. The pg 281 physiological experiments are sufficiently convincing on this point. A development of all the possible contrasts of the chromatic scale will be shortly given. 3. Facility with which color may be made to tend either to the plus or minus side. We have already had occasion to take notice of the mutability of color in considering its so-called augmentation and progressive variations round the whole circle, but the hues even pass and repass from one side to the other rapidly, and of necessity. Physiological colors are different in appearance as they happen to fall on a dark or on a light ground in physical colors, The combination of the objective and subjective experiments is very remarkable. The apoptical colors, it appears, are contrasted according as the light shines through or upon them. To what extent the chemical colors may be changed by fire and alkalis has been sufficiently shown in its proper place. Evanescence of color. All that has been adverted to as subsequent pg 282 to the rapid excitation and definition of color immixture, augmentation, combination, separation, not forgetting the law of compensatory harmony, all takes place with the greatest rapidity and facility, but with equal quickness color again altogether disappears. The physiological appearances are in no wise to be arrested. The physical last only as long as the external condition lasts. Even the chemical colors have great mutability. They may be made to pass and repass from one side to the other by means of opposite reagents, and may even be annihilated altogether. Permanence of color. The chemical colors afford evidence of very great duration. Colors fixed in glass by fusion, and by nature in gems, defy all time and reaction. The art of dyeing again fixes color very powerfully. The hues of pigments, which might otherwise be easily rendered mutable by reagents, may be communicated to substances in the greatest permanency by means of mordants. pg 283. Part Roman 5. Relation to other pursuits. Relation to philosophy. The investigator of nature cannot be required to be a philosopher, but it is expected that he should so far have attained the habit of philosophizing as to distinguish himself essentially from the world. In order to associate himself with it again, in a higher sense, he should form to himself a method in accordance with observation. But he should take heed not to reduce observation to mere notion, to substitute words for this notion, and to use and deal with these words as if they were things. He should be acquainted with the labors of philosophers in order to follow up the phenomena which have been the subject of his observation into the philosophically reach. It cannot be required that the philosopher should be a naturalist, and yet his cooperation in physical researches is as necessary as it is desirable. He needs not an acquaintance with details for this, but only a clear view of those conclusions where insulated facts meet. pg 284. We have before 175 alluded to this important consideration, and repeat it here where it is, in its place. The worst that can happen to physical science, as well as to many other kinds of knowledge, is that men should treat a secondary phenomenon as a primordial one, and since it is impossible to derive the original fact from the secondary state, seek to explain what is in reality the cause by an effect made to usurp its place. Hence arises an endless confusion, a mere verbiage, a constant endeavor to seek and to find subterfuges whenever truth presents itself and threatens to be overpowering. While the observer, the investigator of nature, is thus dissatisfied in finding that the appearances he sees still contradict a received theory, the philosopher can calmly continue to operate in his abstract department on a false result, for no result is so false, but that it can be made to appear valid as form without substance by some means or other. If, on the other hand, the investigator of nature can attain to the knowledge of that which we have called a primordial phenomenon, he is safe, and the philosopher with him, the investigator pg 285 of nature, is safe, since he is persuaded that he has here arrived at the limits of his science, that he finds himself at the height of experimental research, a height whence he can look back upon the details of observation in all its steps and forwards into. If he cannot enter the regions of theory, the philosopher is safe, for he receives from the experimentalist an ultimate fact which in his hands now becomes an elementary one. He now justly pays little attention to appearances which are understood to be secondary, whether he already finds them scientifically arranged, or whether they present themselves to his casual observation scattered and confused. Should he even be inclined to go over this experimental ground himself, and not be averse to examination in detail, he does this conveniently instead of lingering too long in the consideration of secondary and intermediate circumstances, or hastily passing them over without becoming accurately acquainted with them. To place the doctrine of colors nearer in this sense within the philosopher's reach was the author's wish, and although the execution of his purpose from various causes does not correspond with his intention, he will still keep this object in view in an intended recapitulation, pg 286, as well as in the polemical and historical portions of his work. for he will have to return to the consideration of this point hereafter on an occasion where it will be necessary to speak with less reserve. Relation to mathematics. It may be expected that the investigator of nature who proposes to treat the science of natural philosophy in its entire range should be a mathematician. In the Middle Ages, mathematics was the chief organ by means of which men hoped to master the secrets of nature, and even now geometry in certain departments of physics is justly considered of first importance. The author can boast of no attainments of this kind, and on this account confines himself to departments of science which are independent of geometry, departments which in modern times have been opened up far and wide. It will be universally allowed that mathematics, one of the noblest auxiliaries which can be employed by man, has in one point of view been of the greatest use to the physical sciences, but that by a false application of its methods, pg 287, it has in many respects been prejudicial to them, is also not to be denied. We find it here and there reluctantly admitted. The theory of colors in particular has suffered much, and its progress has been incalculably retarded by having been mixed up with optics, generally a science which cannot dispense with mathematics, whereas the theory of colors in strictness may be investigated quite independently of optics. But besides this, there was an additional evil. A great mathematician was possessed with an entirely false notion on the physical origin of colors, yet owing to his great authority as a geometer, the mistakes which he committed as an experimentalist long became sanctioned in the eyes of a world ever fettered in prejudices. The author of the present inquiry has endeavored throughout to keep the theory of colors distinct from the mathematics, although there are evidently certain points where the assistance of geometry would be desirable, had not the unprejudiced mathematicians with whom he has had, or still has the good fortune, to be acquainted pg 288, been prevented by other occupations from making common cause with him, his work would not have wanted some merit in this respect. But this very want may be in the end advantageous, since it may now become the object of the enlightened mathematician to ascertain where the doctrine of colors is in need of his aid, and how he can contribute the means at his command, with a view to the complete elucidation of this branch of physics. In general, it were to be wished that the Germans who render such good service to science, while they adopt all that is good from other nations, could by degrees accustom themselves to work in concert. We live it must be confessed in an age, the habits of which are directly opposed to such a wish. Every one seeks not only to be original in his views, but to be independent of the labors of others, or at least to persuade himself that he is so even in the course of his life and occupation. It is very often remarked that men who undoubtedly have accomplished much quote themselves only their own writings, journals, and compendiums, whereas it would be far more advantageous for the individual and for the world if many were devoted to a common pursuit. The conduct of our neighbors, the French, is in this respect worthy pg 289 of imitation. We have a pleasing instance in Cuvier's preface to his Tableau élémentaire de l'histoire naturelle des animaux. He who has observed science and its progress with an unprejudiced eye might even ask whether it is desirable that so many occupations and aims, though allied to each other, should be united in one person, and whether it would not be more suitable for the limited powers of the human mind to distinguish, for example, the investigator and inventor from him who employs and applies the result of experiment. Astronomers who devote themselves to the observation of the heavens and the discovery or enumeration of stars have in modern times formed to a certain extent a distinct class from those who calculate the orbits, consider the universe in its connection, and more accurately define its laws. The history of the doctrine of colors will often lead us back to these considerations. Relation to the technical operations of the dyer. If in our labors we have gone out of the province of the mathematician, we have on the other hand endeavored to meet the practical pg 290 views of the dyer. And although the chapter which treats of color in a chemical point of view is not the most complete and circumstantial, yet in that portion, as well as in our general observations respecting color, the dyer will find his views assisted far more than by the theory hitherto in vogue, which failed to afford him any assistance. It is curious in this view to take a glance at the works containing directions on the art of dyeing, as the Catholic on entering his temple sprinkles himself with holy water, and after bending the knee proceeds perhaps to converse with his friends on his affairs, without any especial devotion, so all. The treatises on dyeing begin with a respectful allusion to the accredited theory, without afterwards exhibiting a single trace of any principle deduced from this theory, or showing that it has thrown light on any part of the art, or that it offers any useful hints in furtherance of practical methods. On the other hand, there are men who, after having become thoroughly and experimentally acquainted with the nature of dyes, have not been able to reconcile their observations with the received theory, who have, in short, discovered pg 291 its weak points, and sought for a general view more consonant to nature and experience. When we come to the names of Castell and Gillick, in our historical review, we shall have occasion to enter into this more fully, and an opportunity will then present itself to show that an assiduous experience in taking advantage of every accident may in fact be said almost to exhaust the knowledge of the province to which it is confined. The high and complete result is then submitted to the theorist, who, if he examines facts with accuracy and reasons with candor, will find such materials eminently useful as a basis for his conclusions. Note A. Relation to physiology and pathology. If the phenomena adduced in the chapter where colors were considered in a physiological and pathological view are for the most part generally known, still some new views mixed up with them will not be unacceptable to the physiologist. We especially hope to have given him cause to be satisfied by classing certain phenomena which stood alone under analogous facts, and thus, in some measure, to have prepared the way for his further investigations. The appendix on pathological colors, again pg 292, is admitted to be scanty and unconnected. We reflect, however, that Germany can boast of men who are not only highly experienced in this department, but are likewise so distinguished for general cultivation that it can cost them but little to revise this portion to complete what has been sketched, and at the same time to connect it with the higher facts of organization. Relation to natural history. If we may at all hope that natural history will gradually be modified by the principle of deducing the ordinary appearances of nature from higher phenomena, the author believes he may have given some hints and introductory views bearing on this object. Also, as color in its infinite variety exhibits itself on the surface of living beings, it becomes an important part of the outward indications by means of which we can discover what passes underneath. In one point of view, it is certainly not to be too much relied on account of its indefinite and mutable nature. Yet even this mutability, inasmuch as it exhibits itself as a constant quality, again becomes a criterion of immutable vitality, and the author wishes nothing more pg 293 than that time may be granted him to develop the results of his observations on this subject more fully. Here they would not be in their place. Relation to general physics. The state in which general physics now is appears again particularly favorable to our labors for natural philosophy, owing to indefatigable and variously directed research, has gradually attained such eminence that it appears not impossible to refer a boundless empiricism to one center. Without referring to subjects which are too far removed from our own province, we observe that the formal, under which the elementary appearances of nature are expressed, altogether tend in this direction, and it is easy to see that through this correspondence of expression, a correspondence in meaning will necessarily be soon arrived at. True observers of nature, however they may differ in opinion in other respects, will agree that all which presents itself as appearance, all that we meet with as phenomenon, must either pg 294 indicate an original division, which is capable of union, or an original unity which admits of division, and that the phenomenon will present itself accordingly to divide the united to unite the divided. Is the life of nature, this is the eternal systole, and diastole the eternal collapsion and expansion, the inspiration and expiration of the world in which we live and move. It is hardly necessary to observe that what we here express as number and restrict to dualism is to be understood in a higher sense, the appearance of a fourth order of facts progressively developing themselves, is to be similarly understood, but actual observation should above all be the basis of all these expressions. Iron is known to us as a peculiar substance, different from other substances in its ordinary state. We look upon it as a mere material remarkable only on account of its fitness for various uses and applications. How little, however, is necessary to do away with the comparative insignificancy of this substance. A twofold power is called fourth one, which, while it tends again to a pg 295 state of union, and as it were seeks itself, acquires a kind of magical relation with its like, and propagates this double property, which is in fact but a principle of reunion throughout all bodies of the same kind. We here first observe the mere substance iron. We see the division that takes place in it, propagate itself, and disappear and again, easily become re-excited. This, according to our mode of thinking, is a primordial phenomenon in immediate relation with its idea, and which acknowledges nothing earthly beyond it. Electricity is again peculiarly characterized as a mere quality. We are unacquainted with it. For us, it is a nothing, a zero, a mere point, which however dwells in all apparent existences, and at the same time is the point of origin whence on the slightest stimulus a double appearance presents itself, an appearance which only manifests itself to vanish. The conditions under which this manifestation is excited are infinitely varied, according to the nature of particular bodies, from the rudest mechanical friction of very different substances with one another, to the mere contiguity of two entirely similar bodies. The phenomenon is present and stirring, nay, striking and powerful, and so decided and specific that, when we employ the terms or formal pg 296 polarity plus and minus for north and south for glass and resin, we do so justifiably and in conformity with nature. This phenomenon, although it especially affects the surface, is yet by no means superficial. It influences the tendency or determination of material qualities, and connects itself in immediate cooperation with the important double phenomenon, which takes place so universally in chemistry, oxidation and deoxidation. To introduce and include the appearances of color in this series, this circle of phenomena, was the object of our labors. What we have not succeeded in others will accomplish. We found a primordial vast contrast between light and darkness, which may be more generally expressed by light and its absence. We looked for the intermediate state, and sought by means of it to compose the visible world of light, shade, and color. In the prosecution of this, we employed various terms applicable to the development of the phenomena, terms which we adopted from the theories of magnetism, of electricity, and of chemistry. It was necessary, however, to extend this terminology, since we found ourselves in an abstract region, and had to express more complicated relations. pg 297. If electricity and galvanism in their general character are distinguished as superior to the more limited exhibition of magnetic phenomena, it may be said that color, although coming under similar laws, is still superior, for since it addresses itself to the noble sense of vision, its perfections are more generally displayed. Compare the varied effects, which result from the augmentation of yellow and blue to red, from the combination of these two higher extremes to pure red, and the union of the two inferior extremes to green. What a far more varied scheme is apparent here than that in which magnetism and electricity are comprehended. These last phenomena may be said to be inferior again on another account, for though they penetrate and give life to the universe, they cannot address themselves to man in a higher sense. In order to his employing them aesthetically, the general simple physical law must first be elevated and diversified itself in order to be available for elevated uses. If the reader in this spirit recalls what has been stated by us throughout generally, and in detail with regard to color, he will himself pursue and unfold what has been here only lightly hinted at. He will augur well for pg 298 science, technical processes, an art, if it should prove possible, to rescue the attractive subject of the doctrine of colors from the atomic restriction and isolation in which it has been banished, in order to restore it to the general dynamic flow of life and action, which the present age loves to recognize in nature. These considerations will press upon us more strongly when, in the historical portion, we shall have to speak of many an enterprising and intelligent man who failed to possess his contemporaries with his convictions. Relation to the theory of music. Before we proceed to the moral associations of color and the aesthetic influences arising from them, we have here to say a few words on its relation to melody. That a certain relation exists between the two has been always felt. This is proved by the frequent comparisons we meet with, sometimes as passing allusions, sometimes as circumstantial parallels. The error which writers have fallen into in trying to establish this analogy, we would thus define: color and sound do not admit of being directly compared together in any way, but both are referable to a higher formula. Both are derivable pg 299, although each for itself from this higher law. They are like two rivers which have their source in one and the same mountain, but subsequently pursue their way under totally different conditions in two totally different regions, so that throughout the whole course of both no 2 points can be compared. Both are general elementary effects, acting according to the general law of separation and tendency, to union of undulation and oscillation, yet acting thus in wholly different provinces, in different modes, on different elementary mediums, for different senses. Note BB. Could some investigator rightly adopt the method in which we have connected the doctrine of colors with natural philosophy, generally, and happily supply what has escaped or been missed by us, the theory of sound, we are persuaded, might be perfectly connected with general physics. At present, it stands as it were isolated within the circle of science. It is true it would be an undertaking of the greatest difficulty to do away with the positive character, which we are now accustomed to attribute to music, a character resulting from the achievements of practical skill, from accidental pg 300 mathematical aesthetical influences, and to substitute for all this a merely physical inquiry tending to resolve the science into its first elements, yet considering the point at which science and art are now arrived, considering the many excellent preparatory investigations that have been made relative to this subject, we may perhaps still see it accomplished. Concluding observations on terminology. We never sufficiently reflect that a language, strictly speaking, can only be symbolical and figurative, that it can never express things directly, but only as it were reflectedly. This is especially the case in speaking of qualities, which are only imperfectly presented to observation, which might rather be called powers than objects, and which are ever in movement throughout nature. They are not to be arrested, and yet we find it necessary to describe them. Hence, we look for all kinds of formal in order, figuratively, at least, to define them. Metaphysical formal have breadth as well as depth, but on this very account, they require a corresponding import. The danger here is vagueness. Mathematical expressions may in many cases be very conveniently and happily pg 301 employed, but there is always an inflexibility in them, and we presently feel their inadequacy, for even in elementary cases, we are very soon conscious of an incommensurable idea. They are besides only intelligible to those who are especially conversant in the sciences to which such formal are appropriated. The terms of the science of mechanics are more addressed to the ordinary mind, but they are ordinary in other senses, and always have something unpolished. They destroy the inward life, to offer from without an insufficient substitute for it. The formal of the corpuscular theories are nearly allied to the last. Through them, the mutable becomes rigid description and expression uncouth, while again moral terms, which undoubtedly can express nicer relations, have the effect of mere symbols in the end, and are in danger of being lost in a play of wit. If, however, a writer could use all these modes of description and expression with perfect command, and thus give forth the result of his observations on the phenomena of nature in a diversified language, if he could preserve himself from predilections, still embodying a lively meaning, in as animated an expression, we might look for much instruction communicated in the most agreeable of forms. pg 302. Yet how difficult it is to avoid substituting the sign for the thing, how difficult to keep the essential quality still living before us, and not to kill it with the word. With all this we are exposed in modern times to a still greater danger, by adopting expressions and terminologies from all branches of knowledge and science, to embody our views of simple nature, astronomy, cosmology, geology, natural history, nay, religion and mysticism are called in aid, and how often do we not find a general idea and an elementary state, rather hidden and obscured than elucidated and brought nearer to us by the employment of terms, the application of which is strictly specific and secondary. We are quite aware of the necessity which led to the introduction and general adoption of such a language. We also know that it has become in a certain sense indispensable, but it is only a moderate, unpretending recourse to it, with an internal conviction of its fitness, that can recommend it. After all, the most desirable principle would be that writers should borrow the expressions employed to describe the details of a given province of investigation from the province itself, treating the simplest phenomenon as an elementary pg 303 formula, and deriving and developing the more complicated designations from this. The necessity and suitableness of such a conventional language, where the elementary sign expresses the appearance itself, has been duly appreciated by extending, for instance, the application of the term polarity, which is borrowed from the magnet, to electricity. Roman 100. the plus and minus which may be substituted for this, have found as suitable an application to many phenomena, even the musician probably, without troubling himself about these other departments, has been naturally led to express the leading difference in the modes of melody by major and minor. For ourselves, we have long wished to introduce the term polarity into the doctrine of colors, with what right, and in what sense the present work may show perhaps, we may hereafter find room to connect the elementary phenomena together, according to our mode, by a similar use of symbolical terms, which must at all times convey the directly corresponding idea. We shall thus render more explicit what has been here only alluded to generally, and perhaps too vaguely expressed. Pg 304. Part Roman 6, Affective Color, with reference to moral associations. Since color occupies so important a place in the series of elementary phenomena, filling, as it does the limited circle assigned to it with fullest variety, we shall not be surprised to find that its effects are at all times decided and significant, and that they are immediately associated with the emotions of the mind. We shall not be surprised to find that these appearances presented singly are specific, that in combination they may produce an harmonious characteristic, often even an inharmonious effect, on the eye by means of which they act on the mind, producing this impression, in their most general elementary character, without relation to the nature or form of the object on whose surface they are apparent. Hence color, considered as an element of art, may be made subservient to the highest aesthetical ends. Note Roman 200. People experience a great delight in color, generally. The eye requires it as much as it requires light. We have only to remember the Pg 305 refreshing sensation we experience if on a cloudy day the sun illumines a single portion of the scene before us and displays its colors. That healing powers were ascribed to colored gems may have arisen from the experience of this indefinable pleasure. The colors which we see on objects are not qualities entirely strange to the eye. The organ is not thus merely habituated to the impression. No, it is always predisposed to produce color of itself, and experiences a sensation of delight if something analogous to its own nature is offered to it from without, if its susceptibility is distinctly determined towards a given state. From some of our earlier observations, we can conclude that general impressions produced by single colors cannot be changed, that they act specifically, and must produce definite specific states in the living organ. They likewise produce a corresponding influence on the mind. Experience teaches us that particular colors excite particular states of feeling. It is related of a witty Frenchman, il prétendait, que son ton de conversation, avec Pg 306, Madame etait change, depuis qu'elle avoit change en cramoisi le meuble de son cabinet, qui était bleu. In order to experience these influences completely, the eye should be entirely surrounded with one color. We should be in a room of one color, or look through a colored glass. We are then identified with the hue. It attunes the eye and mind in mere unison with itself. The colors on the plus side are yellow, radiello, orange, yellowed, minium. Cinnabar. The feelings they excite are quick, lively, aspiring. Yellow. This is the color nearest the light. It appears on the slightest mitigation of light, whether by semi-transparent mediums or faint reflection from white surfaces. In prismatic experiments, it extends itself alone and widely in the light space, and while the two poles remain separated from each other before it mixes with blue to produce green, it is to be seen in its utmost purity and beauty how the chemical yellow develops itself in and upon the white has been circumstantially described in its proper place. Pg 307. In its highest purity, it always carries with it the nature of brightness, and has a serene, gay, softly exciting character. In this state applied to dress hangings, carpeting, Roman 100, it is agreeable gold in its perfectly unmixed state, especially when the effect of polish is superadded, gives us a new and high idea of this color. In like manner, a strong yellow, as it appears on satin, has a magnificent and noble effect. We find from experience again that yellow excites a warm and agreeable impression. Hence, in painting, it belongs to the illumined and emphatic side. This impression of warmth may be experienced in a very lively manner if we look at a landscape through a yellow glass, particularly on a gray winter's day. The eye is gladdened, the heart expanded, and cheered. A glow seems at once to breathe towards us. If, however, this color in its pure and bright Pg 308 state is agreeable and gladdening, and in its utmost power is serene and noble. It is, on the other hand, extremely liable to contamination, and produces a very disagreeable effect if it is sullied, or in some degree, tends to the minus side. Thus the color of sulfur, which inclines to green, has a something unpleasant in it. When a yellow color is communicated to dull and coarse surfaces such as common cloth felt, or the like, on which it does not appear with full energy, the disagreeable effect alluded to is apparent by a slight and scarcely perceptible change. The beautiful impression of fire and gold is transformed into one not undeserving the epithet foul, and the color of honor and joy reversed to that of ignominy and aversion. To this impression, the yellow hats of bankrupts and the yellow circles on the mantles of Jews may have owed their origin. Rhetorical. As no color can be considered as stationary, so we can very easily augment yellow into reddish by condensing or darkening it. The color increases in energy and appears in red yellow more powerful and splendid. Pg 309. All that we have said of yellow is applicable here in a higher degree. The red yellow gives an impression of warmth and gladness, since it represents the hue of the intenser glow of fire, and of the milder radiance of the setting sun. Hence it is agreeable around us, and again, as clothing in greater or less degrees, is cheerful and magnificent. A slight tendency to red immediately gives a new character to yellow, and while the English and Germans content themselves with bright pale yellow colors, in leather the French, as Castel has remarked, prefer a yellow enhanced to red. Indeed, in general everything in color is agreeable to them which belongs to the active side. Yellowed. As pure yellow passes very easily to red yellow, so the deepening of this last to yellowed is not to be arrested. The agreeable cheerful sensation which red yellow excites increases to an intolerably powerful impression in bright yellowed. The active side is here in its highest energy, and it is not to be wondered at that impetuous, robust, uneducated men should be, especially Pg 310, pleased with this color. Among savage nations, the inclination for it has been universally remarked, and when children left to themselves begin to use tints, they never spare vermilion and minium. In looking steadfastly at a perfectly yellowed surface, the color seems actually to penetrate the organ. It produces an extreme excitement, and still acts thus when somewhat darkened. A yellowed cloth disturbs and enrages animals. I have known men of education to whom its effect was intolerable, if they chanced to see a person dressed in a scarlet cloak on a gray, cloudy day. The colors on the minus side are blue, red, blue, and bluard. They produce a restless, susceptible, anxious impression. Blue. As yellow is always accompanied with light, so it may be said that blue still brings a principle of darkness with it. This color has a peculiar and almost indescribable Pg 311 effect on the eye. As a hue it is powerful, but it is on the negative side, and in its highest purity is as it were a stimulating negation. Its appearance, then, is a kind of contradiction between excitement and repose. As the upper sky and distant mountains appear blue, so a blue surface seems to retire from us. But as we readily follow an agreeable object that flies from us, so we love to contemplate blue, not because it advances to us, but because it draws us after it. Blue gives us an impression of cold, and thus again reminds us of shade. We have before spoken of its affinity with black. Rooms which are hung with pure blue appear in some degree larger, but at the same time empty and cold. The appearance of objects seen through a blue glass is gloomy and melancholy. Pg 312. When blue partakes in some degree of the plus side, the effect is not disagreeable. Sea green is rather a pleasing color. Red blues. We found yellow very soon tending to the intense state, and we observed the same progression in blue. Blue deepens very mildly into red, and thus acquires a somewhat active character. Although it is on the passive side, its exciting power is, however, of a very different kind from that of the red yellow. It may be said to disturb rather than enliven. As augmentation itself is not to be arrested, so we feel an inclination to follow the progress of the color, not, however, as in the case of the red yellow, to see it still increase in the active sense, but to find a point to rest in. In a very attenuated state, this color is known to us under the name of lilac, but even in this degree, it has a something lively without gladness. Pg 313. This unquiet feeling increases as the hue progresses, and it may be safely assumed that a carpet of a perfectly pure deep bluard would be intolerable on this account, When it is used for dress ribbons or other ornaments, it is employed in a very attenuated and light state, and thus displays its character, as above defined, in a peculiarly attractive manner. As the higher dignitaries of the Church have appropriated this unquiet color to themselves, we may venture to say that it unceasingly aspires to the cardinal's red through the restless degrees of a still impatient progression. Red. We are here to forget everything that borders on yellow or blue. We are to imagine an absolutely pure red like fine carmine, suffered to dry on white porcelain. We have called this color purpur by way of distinction, although we are quite aware that the purple of the ancients inclined more to blue. Whoever is acquainted with the prismatic pg 314 origin of red will not think it paradoxical if we assert that this color, partly actu partly potentia, includes all the other colors. We have remarked a constant progress or augmentation in yellow and blue, and seen what impressions were produced by the various states. Hence, it may naturally be inferred that now in the junction of the deepened extremes, a feeling of satisfaction must succeed, and thus in physical phenomena, this highest of all appearances of color arises from the junction of two contrasted extremes, which have gradually prepared themselves for a union. As a pigment, on the other hand, it presents itself to us already formed, and is most perfect as a hue in cochineal, a substance, which, however, by chemical action, may be made to tend to the plus or the minus side, and may be considered to have attained the central point in the best carmine. The effect of this color is as peculiar as its nature. It conveys an impression of gravity and dignity, and at the same time of grace and attractiveness, the first in its dark deep state pg 315, the latter in its light attenuated tint, and thus the dignity of age and the amiableness of youth may adorn itself with degrees of the same hue. History relates many instances of the jealousy of sovereigns with regard to the quality of red. Surrounding accompaniments of this color have always a grave and magnificent effect. The red glass exhibits a bright landscape in so dreadful a hue as to inspire sentiments of awe. Kermes and cochineal, the two materials chiefly employed in dyeing to produce this color, incline more or less to the plus or minus state, and may be made to pass and repass the culminating point by the action of acids and alkalis. It is to be observed that the French arrest their operations on the active side, as is proved by the French scarlet, which inclines to yellow. The Italians, on the other hand, remain on the passive side, for their scarlet has a tinge of blue. By means of a similar alkaline treatment, the so-called crimson is produced, a color which the French must be particularly prejudiced pg 316 against, since they employ the expression sot en cramosi mecant en cramosi to mark the extreme of the silly and the reprehensible. Green. If yellow and blue, which we consider as the most fundamental and simple colors, are united, as they first appear in the first state of their action, the color which we call green is the result. The eye experiences a distinctly grateful impression from this color, if the two elementary colors are mixed in perfect equality, so that neither predominates. The eye and the mind repose on the result of this junction. As upon a simple color, the beholder has neither the wish nor the power to imagine a state beyond it. Hence, for rooms to live in constantly, the green color is most generally selected. Completeness and harmony. We have hitherto assumed, for the sake of clearer explanation, that the eye can be compelled to assimilate or identify itself with a single color, but this can only be possible for an instant. pg 317. For when we find ourselves surrounded by a given color, which excites its corresponding sensation on the eye, and compels us by its presence to remain in a state identical with it, this state is soon found to be forced, and the organ unwillingly remains in it. When the eye sees a color, it is immediately excited, and it is its nature spontaneously, and of necessity at once, to produce another which, with the original color, comprehends the whole chromatic scale. A single color excites by a specific sensation the tendency to universality. To experience this completeness, to satisfy itself, the eye seeks for a colorless space next every hue in order to produce the complemental hue upon it. In this resides the fundamental law of all harmony of colors, of which every one may convince himself by making himself accurately acquainted with the experiments which we have described in the chapter on the physiological colors. pg 318. If again the entire scale is presented to the eye externally, the impression is gladdening, since the result of its own operation is presented to it in reality, we turn our attention therefore in the first place to this harmonious juxtaposition. As a very simple means of comprehending the principle of this, the reader has only to imagine a movable diametrical index in the colorific circle, the index, as it revolves round the whole circle indicates at its two extremes the complemental colors, which after all may be reduced to three contrasts. Yellow demands red-blue. Blue demands red-yellow. Red demands green. And contrariwise. In proportion, as one end of the supposed index deviates from the central intensity of the colors arranged, as they are in the natural order, so the opposite end changes its place in the contrasted gradation, and by such a simple PG 319 contrivance, the complemental colors may be indicated at any given point. A chromatic circle might be made for this purpose, not confined like our own to the leading colors, but exhibiting them with their transitions in an unbroken series. This would not be without its use, for we are here considering a very important point, which deserves all our attention too. We before stated that the eye could be in some degree pathologically affected by being long confined to a single color, that again definite moral impressions were thus produced at one time lively, and aspiring at another susceptible and anxious, no, exalted to grand associations now reduced to ordinary ones. We now observe that the demand for completeness, which is inherent in the organ, frees us from this restraint. The eye relieves itself by producing the opposite of the single color forced upon it, and thus attains the entire impression which is so satisfactory to it. Simple, therefore, as these strictly harmonious contrasts are as presented to us in the narrow circle, the hint is important that nature tends to emancipate the sense from confined PG 320 impressions by suggesting and producing the whole, and that in this instance, we have a natural phenomenon immediately applicable to aesthetic purposes. While therefore we may assert that the chromatic scale as given by us produces an agreeable impression by its ingredient hues, we may here remark that those have been mistaken who have hitherto adduced the rainbow as an example of the entire scale, for the chief color pure red is deficient in it, and cannot be produced, since in this phenomenon, as well as in the ordinary prismatic series, the yellowed and blued cannot attain to union. Nature perhaps exhibits no general phenomenon where the scale is in complete combination by artificial experiments. Such an appearance may be produced in its perfect splendor. The mode, however, in which the entire series is connected, in a circle, is rendered most intelligible by tints on paper, till after much experience and practice aided by due susceptibility of the organ, we become penetrated with the idea of this harmony, and feel it present in our minds. PG 321. Besides these pure harmonious self-developed combinations, which always carry the conditions of completeness with them, there are others which may be arbitrarily produced, and which may be most easily described by observing that they are to be found in the colorific circle not by diameters, but by chords in such a manner that an intermediate color is passed over. We call these combinations characteristic because they have all a certain significancy, and tend to excite a definite impression, an impression, however, which does not altogether satisfy, inasmuch as every characteristic quality of necessity presents itself only as a part of a whole with which it has a relation, but into which it cannot be resolved. As we are acquainted with the impressions produced by the colors, singly as well as in their harmonious relations, we may at once conclude that the character of the arbitrary combinations will be very different from each other as regards their significancy. We proceed to review them separately. PG 322. Yellow and blues. This is the simplest of such combinations. It may be said that it contains too little, for since every trace of red is wanting in it, it is defective as compared with the whole scale. In this view, it may be called poor, and as the two contrasting elements are in their lowest state, may be said to be ordinary, yet it is recommended by its proximity to green, in short, by containing the ingredients of an ultimate state. Yellow and red. This is a somewhat preponderating combination, but it has a serene and magnificent effect. The two extremes of the active side are seen together without conveying any idea of progression from one to the other. As the result of their combination in pigments is yellowed, so they in some degree represent this color. Blue and red. The two ends of the passive side, with the excess of the upper end of the active side, the effect of this juxtaposition approaches that of the bluard produced by their union. Pg 323. Yelloward and bluard. These, when placed together, as the deepened extremes of both sides, have something exciting elevated. They give us a presentiment of red which, in physical experiments, is produced by their union. These four combinations have also the common quality of producing the intermediate color of our colorific circle by their union, a union which actually takes place if they are opposed to each other in small quantities, and seen from a distance, a surface, covered with narrow blue and yellow stripes, appears green at a certain distance. If again the eye sees blue and yellow next each other, it finds itself in a peculiar disposition to produce green without accomplishing it, while it neither experiences a satisfactory sensation in contemplating the detached colors, nor an impression of completeness in the two. Thus it will be seen that it was not without reason we called these combinations characteristic, the more so, since the character of each Pg 324 combination must have a relation to that of the single colors of which it consists. Combinations, non-characteristic. We now turn our attention to the last kind of combinations. These are easily found in the circle. They are indicated by shorter chords, for in this case, we do not pass over an entire intermediate color, but only the transition from one to the other. These combinations may justly be called non-characteristic inasmuch as the colors are too nearly alike for their impression to be significant, yet most of these recommend themselves to a certain degree, since they indicate a progressive state, though its relations can hardly be appreciable. Thus yellow and yellowed and red blue and bluard and red represent the nearest degrees of augmentation and culmination, and in certain relations, as to quantity, may produce no unpleasant effect. The juxtaposition of yellow and green has Pg 325 always something ordinary, but in a cheerful sense blue and green, on the other hand, is ordinary in a repulsive sense. Our good forefathers called these last fools colors. Relation of the combinations to light and dark. These combinations may be very much varied by making both colors light or both dark or one light, and the other dark, in which modifications, however, all that has been found true in a general sense, is applicable to each particular case. With regard to the infinite variety thus produced, we merely observe. The colors of the active side placed next to black gain in energy, those of the passive side lose the active conjoined with white and brightness, lose in strength, the passive gain in cheerfulness, red and green, with black appear dark and grave, with white they appear gay. To this, we may add that all colors may be more or less broken or neutralized, may to a certain degree be rendered nameless, and thus combined partly together and partly with pure colors. But although the relations may thus Pg 326 be varied to infinity, still all that is applicable with regard to the pure colors will be applicable in these cases. Considerations derived from the evidence of experience and history. The principles of the harmony of colors having been thus far defined, it may not be irrelevant to review what has been adduced in connection with experience and historical examples. The principles in question have been derived from the constitution of our nature and the constant relations which are found to obtain in chromatic phenomena. In experience, we find much that is in conformity with these principles, and much that is opposed to them. Men in a state of nature, uncivilized nations, children have a great fondness for colors in their utmost brightness, and especially for yellowed. They are also pleased with the motley. By this expression, we understand the juxtaposition of vivid colors without an harmonious balance. But if this balance is observed through instinct or accident, an agreeable effect may be produced. I remember a Hessian officer, returned Pg 327 from America, who had painted his face with the positive colors in the manner of the Indians. A kind of completeness, or due balance, was thus produced, the effect of which was not disagreeable. The inhabitants of the south of Europe make use of very brilliant colors for their dresses. The circumstance of their procuring silk stuffs at a cheap rate is favorable to this propensity. The women, especially with their bright-colored bodices and ribbons, are always in harmony with the scenery, since they cannot possibly surpass the splendor of the sky and landscape. The history of dyeing teaches us that certain technical conveniences and advantages have had great influence on the costume of nations. We find that the Germans wear blue very generally, because it is a permanent color in cloth, So in many districts, all the country people wear green twill, because that material takes a green dye well. If a traveler were to pay attention to these circumstances, he might collect some amusing and curious facts. Colors as connected with particular frames pg 328 of mind are again a consequence of peculiar character and circumstances lively nations. The French, for instance, love intense colors, especially on the active side sedate nations, like the English and Germans, wear straw-colored or leather-colored yellow accompanied with dark blue nations, aiming at dignity of appearance. The Spaniards and Italians, for instance, suffer the red color of their mantles to incline to the passive side. In dress, we associate the character of the color with the character of the person. We may thus observe the relation of colors singly and in combination to the color of the complexion, age, and station. The female sex in youth is attached to rose color, and sea-green in age to violet and dark green. The fair-haired prefer violet, as opposed to light yellow, the brunettes blue as opposed to yellowed. And all on good grounds. The Roman emperors were extremely jealous with regard to their purple. The robe of the Chinese emperor is orange embroidered with red, his attendants, and the ministers of religion wear citron yellow. pg 329. People of refinement have a disinclination to colors. This may be owing partly to weakness of sight, partly to the uncertainty of taste, which readily takes refuge in absolute negation. Women now appear almost universally in white and men in black. An observation very generally applicable may not be out of place here, namely, that man, desirous, as he is of being distinguished, is quite as willing to be lost among his fellows. Black was intended to remind the Venetian noblemen of republican equality. To what degree the cloudy sky of northern climates may have gradually banished color may also admit of explanation. The scale of positive colors is obviously soon exhausted. On the other hand, the neutral subdued so-called fashionable colors present infinitely varying degrees and shades, most of which are not unpleasing. pg 330. It is also to be remarked that ladies in wearing positive colors are in danger of making a complexion which may not be very bright, still less so, and thus, to preserve a due balance with such brilliant accompaniments, they are induced to heighten their complexions artificially. An amusing inquiry might be made, which would lead to a critique of uniforms, liveries, cockades, and other distinctions according to the principles above hinted at. It might be observed generally that such dresses and insignia should not be composed of harmonious colors. Uniforms should be characteristic and dignified. Liveries might be ordinary and striking to the eye. Examples, both good and bad, would not be wanting, since the scale of colors usually employed for such purposes is limited, and its varieties have been often enough tried. 3. Aesthetic influence. From the moral associations connected with the appearance of colors, single or combine their aesthetic influence, may now be deduced pg 331. For the artist, we shall touch the most essential points to be attended to, after first considering the general condition of pictorial representation, light and shade, with which the appearance of color is immediately connected. Chiaroscuro. We apply the term chiaroscuro helduncle to the appearance of material objects, when the mere effect produced on them by light and shade is considered. Note Roman 1000. In a narrower sense, a mass of shadow lighted by reflexes is often thus designated, but we here use the expression in its first and more general sense. The separation of light and dark from all appearance of color is possible and necessary. The artist will solve the mystery of imitation sooner by first considering light and dark independently of color, and making himself acquainted with it in its whole extent. Chiaroscuro exhibits the substance as substance inasmuch as light and shade inform us as to degrees of density. pg 332. We have here to consider the highest light, the middle tint, and the shadow, and in the last the shadow of the object itself, the shadow it casts on other objects, and the illumined shadow or reflection. The globe is well adapted for the general exemplification of the nature of chiaroscuro, but it is not altogether sufficient. The softened unity of such complete rotundity tends to the vapory, and in order to serve as a principle for effects of art, it should be composed of plane surfaces, so as to define the gradations more. The Italians call this manner il piazzoso in German. It might be called das Flaschenhaft, for, if therefore the sphere is a perfect example of natural chiaroscuro, A polygon would exhibit the artist-like treatment, in which all kinds of lights, half-lights, shadows, and reflections would be appreciable. Note E. The bunch of grapes is recognized as a good example of a picturesque completeness, in chiaroscuro the more so, as it is fitted from its form to represent a principal group. But it is only pg 333 available for the master who can see in it what he has the power of producing. In order to make the first idea intelligible to the beginner, for it is difficult to consider it abstractedly even in a polygon, we may take a cube the three sides of which that are seen represent the light, the middle tint, and the shadow in distinct order. To proceed again to the chiaroscuro of a more complicated figure, we might select the example of an open book, which presents a greater diversity. We find the antique statues of the best time treated very much with reference to these effects. The parts intended to receive the light are wrought with simplicity. The portion originally in shade is, on the other hand, in more distinct surfaces, to make them susceptible of a variety of reflections. Here the example of the polygon will be remembered. Note FF. The pictures of Herculaneum and the Aldobrandini marriage are examples of antique painting in the same style. pg 334. Modern examples may be found in single figures by Raphael, in entire works by Correggio, and also by the Flemish masters, especially Rubens. Tendency to color. A picture in black and white seldom makes its appearance. Some works of Polidoro are examples of this kind of art. Such works, inasmuch as they can attain form and keeping, are estimable, but they have little attraction for the eye, since their very existence supposes a violent abstraction. If the artist abandons himself to his feeling, color presently announces itself. Black no sooner inclines to blue than the eye demands yellow, which the artist instinctively modifies and introduces, partly pure in the light, partly reddened and subdued as brown in the reflexes, thus enlivening the whole. Note GG. All kinds of cameo or color on similar color end in the introduction, either of a complemental contrast or some variety of hue. Thus Polidoro, in his black and white frescoes pg 335, sometimes introduced a yellow vase, or something of the kind. In general, it may be observed that men have at all times instinctively striven after color in the practice of the art. We need only observe daily how soon amateurs proceed from colorless to colored materials. Paolo Uccello painted colored landscapes to colorless figures. Note HH. Even the sculpture of the ancients could not be exempt from the influence of this propensity. The Egyptians painted their bas-relief statues, had eyes of colored stones, porphyry draperies were added to marble heads and extremities, and variegated stalactites were used for the pedestals of busts. The Jesuits did not fail to compose the statue of their S. Luigi in Rome in this manner. And the most modern sculpture distinguishes the flesh from the drapery by staining the latter. Keeping. If linear perspective displays the gradation of objects in their apparent size as affected by distance, aerial perspective shows us their gradation pg 336 in greater or less distinctness as affected by the same cause. Although from the nature of the organ of sight, we cannot see distant objects so distinctly as nearer ones, yet aerial perspective is grounded strictly on the important fact that all mediums called transparent are in some degree Roman 1499. The atmosphere is thus always more or less semi-transparent. This quality is remarkable in southern climates, even when the barometer is high, the weather dry, and the sky cloudless, for a very pronounced gradation is observable between objects, but little removed from each other. The appearance on a large scale is known to every one. The painter, however, sees, or believes he sees, the gradation in the slightest varieties of distance. He exemplifies it practically by making a distinction, for instance, in the features of a face according to their relative position as regards the plane of the picture. The direction of the light is attended to in like manner. This is considered to produce a gradation from side to side, while keeping has reference to depth, to the comparative distinctness of near and distant things. pg 337. In proceeding to consider this subject, we assume that the painter is generally acquainted with our sketch of the theory of colors, and that he has made himself well acquainted with certain chapters and rubrics, which especially concern him. He will thus be enabled to make use of theory as well as practice in recognizing the principles of effect in nature, and in employing the means of art. Color in general nature. The first indication of color announces itself in nature together with the gradations of aerial perspective for aerial perspective, is intimately connected with the doctrine of semi-transparent mediums. We see the sky distant objects, and even comparatively near shadows blue at the same moment. The illuminating and illuminated objects appear yellow, gradually deepening to red in many cases. The physiological suggestion of contrasts comes into the account, and an entirely colorless landscape, by means of these assisting and counteracting tendencies, appears to our eyes completely colored. Pg 338. Local colors are composed of the general elementary colors, but these are determined or specified according to the properties of substances and surfaces on which they appear. This specification is infinite. Thus there is at once a great difference between silk and wool similarly dyed. Every kind of preparation and texture produces corresponding modifications, roughness, smoothness, polish, all are to be considered. It is therefore one of the pernicious prejudices of art that the skillful painter must never attend to the material of draperies, but always represent, as it were, only abstract folds. Is not all characteristic variety thus done away with, and is the portrait of Leo Roman X less excellent because velvet, satin, and moreen are imitated in their relative effect? In the productions of nature, colors appear more or less modified, specified, even individualized. This may be readily observed in minerals Pg 339, and plants, in the feathers of birds and the skins of beasts. The chief art of the painter is always to imitate the actual appearance of the definite hue, doing away with the recollection of the elementary ingredients of color. This difficulty is in no instance greater than in the imitation of the surface of the human figure. The color of flesh as a whole belongs to the active side, yet the bluish of the passive side mingles with it. The color is altogether removed from the elementary state and neutralized by organization. To bring the coloring of general nature into harmony with the coloring of a given object will perhaps be more attainable for the judicious artist after the consideration of what has been pointed out in the foregoing theory, for the most fancifully beautiful and varied appearances may still be made true to the principles of nature. Characteristic coloring. The combination of colored objects, as well as the color of their ground, should depend on Pg 340 considerations, which the artist pre-establishes for himself. Here a reference to the effect of colors, singly or combined on the feelings, is especially necessary on this account. The painter should possess himself with the idea of the general dualism, as well as of particular contrasts, not forgetting what has been adverted to with regard to the qualities of colors. The characteristic in color may be comprehended under three leading rubrics, which we here define as the powerful, the soft, and the splendid. The first is produced by the preponderance of the active side, the second by that of the passive side, and the third by completeness, by the exhibition of the whole chromatic scale in due balance. The powerful impression is attained by yellow-yellowed, and red, which last color is to be arrested on the plus side, but little violet and blue, still less green, are admissible. The soft effect is produced by blue-violet, and red, which in this case is arrested on the minus side. A moderate addition of yellow and yellowed, but much green may be admitted. Pg 341. If it is proposed to produce both these effects in their full significancy, the complemental colors may be excluded to a minimum, and only so much of them may be suffered to appear as is indispensable to convey an impression of completeness. Harmonious coloring. Although the two characteristic divisions as above defined may in some sense be also called harmonious, the harmonious effect, properly so called, only takes place when all the colors are exhibited together in due balance. In this way, the splendid as well as the agreeable may be produced. Both of these, however, have of necessity a certain generalized effect, and in this sense may be considered the reverse of the characteristic. This is the reason why the coloring of most modern painters is without character, for while they follow their general instinctive feeling, only the last result of such a tendency must be mere completeness. This they more or less attain, but thus at the same time neglect the characteristic Pg 342 impression which the subject might demand. But if the principles before alluded to are kept in view, it must be apparent that a distinct style of color may be adopted on safe grounds. For every subject, the application requires it is true infinite modifications, which can only succeed in the hands of genius. Genuine tone. If the word tone, or rather tune, is to be still borrowed in future from music, and applied to coloring it, might be used in a better sense than heretofore. For it would not be unreasonable to compare a painting of powerful effect with a piece of music in a sharp key, a painting of soft effect with a piece of music in a flat key, while other equivalents might be found for the modifications of these two leading modes. False tone. The word tone has been hitherto understood to mean a veil of a particular color, spread over pg 343. The whole picture, it was generally yellow, for the painter instinctively pushed the effect towards the powerful side. If we look at a picture through a yellow glass, it will appear in this tone. It is worthwhile to make this experiment again and again, in order to observe what takes place in such an operation. It is a sort of artificial light deepening, and at the same time darkening the plus side and neutralizing the minus side. This spurious tone is produced instinctively through uncertainty as to the means of attaining a genuine effect, so that instead of completeness, monotony is the result. Weak colorings. It is owing to the same uncertainty that the colors are sometimes so much broken as to have the effect of a gray camus, the handling being at the same time as delicate as possible. The harmonious contrasts are often found to be very happily felt in such pictures, but without spirit owing to a dread of the motley. pg 344. The motley. A picture may easily become parti-colored or motley when the colors are placed next each other in their full force, as it were only mechanically and according to uncertain impressions. If, on the other hand, weak colors are combined, even although they may be dissonant, the effect, as a matter of course, is not striking. The uncertainty of the artist is communicated to the spectator, who on his side can neither praise nor censure. It is also important to observe that the colors may be disposed rightly in themselves, but that a work may still appear motley if they are falsely arranged in relation to light and shade. This may the more easily occur as light and shade are already defined in the drawing, and are as it were comprehended in it, while the color still remains open to selection. Dread of theory. A dread of, nay, a decided aversion for all pg 345 theoretical views respecting color, and everything belonging to it, has been hitherto found to exist among painters, a prejudice, for which after all they were not to be blamed, for what has been hitherto called theory was groundless, vacillating, and akin to empiricism. We hope that our labors may tend to diminish this prejudice, and stimulate the artist practically to prove and embody the principles that have been explained. Ultimate aim. But without a comprehensive view of the whole of our theory, the ultimate object will not be attained. Let the artist penetrate himself with all that we have stated. It is only by means of harmonious relations in light and shade, in keeping in true and characteristic coloring, that a picture can be considered complete in the sense we have now learnt to attach to the term. Grounds. It was the practice of the earlier artists to paint on light grounds. This ground consisted of gypsum, and was thickly spread on linen or panel, and then levigated after the outline was drawn. The subject was washed in with a pg 346 blackish or brownish color. Pictures prepared in this manner for coloring are still in existence by Leonardo da Vinci and Fra Bartolomeo. There are also several by Guido. Note Roman II. When the artist proceeded to color and had to represent white draperies, he sometimes suffered the ground to remain untouched. Titian did this latterly when he had attained the greatest certainty in practice, and could accomplish much with little labor. The whitish ground was left as a middle tint, the shadows painted in, and the high lights touched on. Note KK. In the process of coloring, the preparation merely washed as it were underneath was always effective. A drapery, for example, was painted with a transparent color. The white ground shone through it, and gave the color life, so the parts previously prepared for shadows exhibited the color subdued, without being mixed or sullied. This method had many advantages for the painter, had a light ground for the light portions of his work, and a dark ground for the shadowed portions. The whole picture was prepared. The pg 347 artist could work with thin colors in the shadows, and had always an internal light to give value to his tints. In our own time, painting in watercolors depends on the same principles. Indeed, a light ground is now generally employed in oil painting, because middle tints are thus found to be more transparent, and are in some degree enlivened by a bright ground. The shadows, again, do not so easily become black. It was the practice for a time to paint on dark grounds. Tintoret probably introduced them Titian's best pictures are not painted on a dark ground. The ground in question was red-brown, and when the subject was drawn upon it, the strongest shadows were laid in the colors of the lights impasted very thickly in the bright parts, and scumbled towards the shadows, so that the dark ground appeared through the thin color, as a middle tint effect was attained in finishing by frequently going over the bright parts and touching on the high lights. pg 348. If this method especially recommended itself in practice on account of the rapidity it allowed of, yet it had pernicious consequences, the strong ground increased and became darker, and the light colors losing their brightness by degrees, gave the shadowed portions more and more preponderance, the middle tints became darker and darker, and the shadows at last quite obscure the strongly impasted lights alone remained bright, and we now see only light spots on the painting. The pictures of the Bolognese school and of Caravaggio afford sufficient examples of these results. We may here in conclusion observe that glazing derives its effect from treating the prepared color underneath as a light ground. By this operation, colors may have the effect of being mixed to the eye, may be enhanced, and may acquire what is called tone, but they thus necessarily become darker. Pigments. We receive these from the hands of the chemist, and the investigator of nature. Much has been recorded respecting coloring substances, pg 349, which is familiar to all by means of the press, but such directions require to be revised from time to time. The master meanwhile communicates his experience in these matters to his scholar, and artists generally to each other. Those pigments which according to their nature are the most permanent are naturally much sought after, but the mode of employing them also contributes much to the duration of a picture. The fewest possible coloring materials are to be employed, and the simplest methods of using them cannot be sufficiently recommended. For from the multitude of pigments coloring has suffered much. Every pigment has its peculiar nature as regards its effect on the eye. Besides this, it has its peculiar quality, requiring a corresponding technical method in its application. The former circumstance is a reason why harmony is more difficult of attainment with many materials than with few. The latter, why chemical action and reaction may take place among the coloring substances. We may refer besides to some false tendencies, pg 350, which the artists suffer themselves to be led away with. Painters are always looking for new coloring substances, and believe when such a substance is discovered that they have made an advance in the art. They have a great curiosity to know the practical methods of the old masters and lose much time in the search. Towards the end of the last century, we were thus long tormented with wax painting. Others turn their attention to the discovery of new methods, through which nothing new is accomplished, for after all it is the feeling of the artist only that informs every kind of technical process. Allegorical, symbolical, mystical application of color. It has been circumstantially shown above that every color produces a distinct impression on the mind, and thus addresses at once the eye and feelings. Hence, it follows that color may be employed for certain moral and aesthetic ends. Such an application, coinciding entirely with nature, might be called symbolical, since the color would be employed in conformity with its effect, and would at once express its meaning. If, for example, pure red were assumed to pg 351 designate majesty, there can be no doubt that this would be admitted to be a just and expressive symbol. All this has been already sufficiently entered into. Another application is nearly allied to this. It might be called the allegorical application. In this, there is more of accident and caprice, inasmuch as the meaning of the sign must be first communicated to us, before we know what it is to signify. What idea, for instance, is attached to the green color, which has been appropriated to hope? That lastly color may have a mystical illusion, may be readily surmised, for since every diagram in which the variety of colors may be represented points to those primordial relations, which belong both to nature and the organ of vision, there can be no doubt that these may be made use of as a language in cases where it is proposed to express similar primordial relations, which do not present themselves to the senses in so powerful and varied a manner. The mathematician extols the value and applicability of the triangle. The triangle is revered by the mystic, much admits of being expressed in it by diagrams, and among other things, the law pg 352 of the phenomena of colors. In this case, indeed, we presently arrive at the ancient mysterious hexagon. When the distinction of yellow and blue is duly comprehended, and especially the augmentation into red by means of which the opposite qualities tend towards each other and become united in a third, then certainly, an especially mysterious interpretation will suggest itself, since a spiritual meaning may be connected with these facts. And when we find the two separate principles producing green on the one hand and red in their intenser state, we can hardly refrain from thinking in the first case on the earthly, in the last, on the heavenly generation of the Elohim. Note Roman 100. But we shall do better not to expose ourselves in conclusion to the suspicion of enthusiasm, since if our doctrine of colors finds favor, applications and allusions, allegorical, symbolical, and mystical, will not fail to be made in conformity with the spirit of the age. Concluding observations. In reviewing this labor which has occupied me long and which at last I give, but as a pg 353 sketch, I am reminded of a wish once expressed by a careful writer, who observed that he would gladly see his works printed at once, as he conceived them in order, then to go to the task with a fresh eye, since everything defective presents itself to us more obviously in print than even in the cleanest manuscript. This feeling may be imagined to be stronger in my case, since I had not even an opportunity of going through a fair transcript of my work before its publication, these pages having been put together at a time when a quiet, collected state of mind was out of the question. 5. Some of the explanations I was desirous of giving are to be found in the introduction, but in the portion of my work to be devoted to the history of the doctrine of colors, I hope to give a more detailed account of my investigations and the vicissitudes they underwent. One inquiry, however, may not be out of place, here the consideration namely of the question, what can a man accomplish who cannot devote his whole life to scientific pursuits? What can he perform as a temporary guest on an estate not his own for the advantage of the proprietor? When we consider art in its higher character, we might wish that masters only had to do with pg 354, it that scholars should be trained by the severest study, that amateurs might feel themselves happy in reverentially approaching its precincts for a work of art. Should be the effusion of genius, the artist should evoke its substance and form, from his inmost being treat his materials with sovereign command, and make use of external influences only to accomplish his powers. But if the professor in this case has many reasons for respecting the dilettante, the man of science has every motive to be still more indulgent, since the amateur here is capable of contributing what may be satisfactory and useful. The sciences depend much more on experiment than art, and for mere experiment, many a votary is qualified. Scientific results are arrived at by many means, and cannot dispense. With many hands, many heads. Science may be communicated, the treasure may be inherited, and what is acquired by one may be appropriated by many. Hence, no one perhaps ought to be reluctant to offer his contributions. How much do we not owe to accident, to mere practice, to momentary observation? All who are endowed only with habits of attention, women, children, are capable of communicating striking and true remarks. In science it cannot therefore be required that he who endeavors to furnish something in pg 355, its age, should devote his whole life to it, should survey and investigate it in all its extent. For this, in most cases, would be a severe condition even for the initiated. But if we look through the history of science in general, especially the history of physics, we shall find that many important acquisitions have been made by single inquirers in single departments, and very often by unprofessional observers. To whatever direction a man may be determined by inclination or accident, whatever class of phenomena especially strike him, excite his interest, fix his attention, and occupy him, the result will still be for the advantage of science. For every new relation that comes to light, every new mode of investigation, even the imperfect attempt, even error itself, is available. It may stimulate other observers, and is never without its use, as influencing future inquiry. With this feeling, the author himself may look back without regret on his endeavors. From this consideration, he can derive some encouragement for the prosecution of the remainder of his task, and although not satisfied with the result of his efforts, yet reassured by the sincerity of his intentions, he ventures to recommend his past and future labors to the interest of his contemporaries and posterity. Multi pertrincibunt et augibiter scientia. pg 357. Notes. Note A par 18. Leonardo da Vinci observes that a light object relieved on a dark ground appears magnified, and again objects seen at a distance appear out of proportion. This is because the light parts transmit their rays to the eye more powerfully than the dark. A woman's white headdress once appeared to me much wider than her shoulders owing to their being dressed in black one. It is now generally admitted that the excitation produced by light is propagated on the retina, a little beyond the outline of the image. Professor Plateau of Ghent has devoted a very interesting special memoir to the description and explanation of phenomena of this nature. See his memoir Sur l'irradiation, published in the 11th vol of the Transactions of the Royal Academy of Sciences at Brussels to SF. Note BPAR 23. The duration of ocular spectra produced by strongly exciting the retina may be conveniently measured by minutes and seconds, but to ascertain the duration of more evanescent phenomena recourse must be had to other means. The Chevalier d'Arcy, Mem de Elicad, Des SCPG 358 1765, endeavored to ascertain the duration of the impression produced by a glowing coal in the following manner. He attached it to the circumference of a wheel, the velocity of which was gradually increased until the apparent trace of the object formed a complete circle, and then measured the duration of a revolution, which was obviously that of the impression. To ascertain the duration of a revolution, it is sufficient merely to know the number of revolutions described in a given time. Recently, more refined experiments of the same kind have been made by Professors Plateau and Wheatstone S.F. Note Roman 100 par 50. Every treatise on the harmonious combination of colors contains the diagram of the chromatic circle more or less elaborately constructed. These diagrams, if intended to exhibit the contrasts produced by the action and reaction of the retina, have one common defect: the opposite colors are made equal in intensity, whereas the complemental color pictured on the retina is always less vivid and always darker or lighter than the original color. This variety undoubtedly accords more with harmonious effects in painting. The opposition of two pure hues of equal intensity, differing only in the abstract quality of color, would immediately be pronounced crude and inharmonious. It would not, however, be strictly correct to say that such a contrast is too violent. On the contrary, it appears the contrast is not carried far enough, for though differing in color, the two hues may be exactly similar in purity and intensity. Complete contrast, on the other hand, supposes dissimilarity in all respects. In addition to the mere difference of hue, the eye, it seems, requires difference in the lightness or darkness of the hue. The spectrum of a color relieved as a dark on a light ground is a light color on a dark ground, and vice versa. Thus, if we look at a bright red wafer on the whitest PG 359 surface, the complemental image will be still lighter than the white surface. If the same wafer is placed on a black surface, the complemental image will be still darker. The color of both these spectra may be called greenish, but it is evident that a color must be scarcely appreciable as such if it is lighter than white and darker than black. It is, however, to be remarked that the white surface round the light greenish image seems tinged with a reddish hue, and the black surface round the dark image becomes slightly illuminated with the same color, thus in both cases assisting to render the image apparent. 58. The difficulty or impossibility of describing degrees of color in words has also had a tendency to mislead, by conveying the idea of more positive hues than the physiological contrast warrants, thus supposing scarlet to be relieved as a dark. The complemental color is so light in degree and so faint in color that it should be called a pearly gray, whereas the theorists looking at the quality of color abstractedly would call it a green-blue, and the diagram would falsely present such a hue equal in intensity to scarlet, or as nearly equal as possible. Even the difference of mass which good taste requires may be suggested by the physiological phenomena, for unless the complemental image is suffered to fall on a surface precisely as near to the eye as that on which the original color was displayed, it appears larger or smaller than the original object. 22, and this in a rapidly increasing proportion. Lastly, the shape itself soon becomes changed. 26. That vivid color demands the comparative absence of color, either on a lighter or darker scale, as its contrast may be inferred again from the fact that bright colorless objects produce strongly colored spectra in darkness. The spectrum which is first white or nearly white is followed by red and light. The spectrum which is first black is followed by green. 3944 All color, as the author observes 259, is to be considered as half-light, inasmuch as it PG 360 is in every case lighter than black and darker than white. Hence, no contrast of color with color, or even of color with black or white, can be so great as regards lightness or darkness, as the contrast of black and white or light, and dark abstractedly. This distinction between the differences of degree and the differences of kind is important, since a just application of contrast in color may be counteracted by an undue difference in lightness or darkness. The mere contrast of color is happily employed in some of Guido's lighter pictures. But if intense darks had been opposed to his delicate carnations, their comparative whiteness would have been unpleasantly apparent. On the other hand, the flesh color in Giorgione Sebastian del Piombo, his best imitator, and Titian, was sometimes so extremely glowing one that the deepest colors and black were indispensable. Accompaniments. The manner of Titian, as distinguished from his imitation of Giorgione, is golden rather than fiery, and his biographers are quite correct in saying that he was fond of opposing red lake and blue to his flesh. 2. The correspondence of these contrasts with the physiological phenomena will be immediately apparent, while the occasional practice of Rubens in opposing bright red to a still cooler flesh color will be seen to be equally consistent. The effect of white drapery, the comparative absence of color in enhancing the glow of Titian's flesh color, has been frequently pointed out. 3. The shadows of white, thus opposed to flesh, often present again the physiological contrast, however delicately. According to the hue of the carnation pg 361, the lights, on the other hand, are not and probably never were quite white, but from the first partook of the quality of depth, a quality assumed by the colorists to pervade every part of a picture more or less. 4. It was before observed that the description of colors in words may often convey ideas of too positive a nature, and it may be remarked generally that the colors employed by the great masters are in their ultimate effect more or less subdued or broken. The physiological contrasts are, however, still applicable in the most comparatively neutral scale. Again, the works of the colorists show that these oppositions are not confined to large masses, except perhaps in works to be seen only at a great distance. On the contrary, they are more or less apparent in every part, and when at last the direct and intentional operations of the artist may have been insufficient to produce them in their minuter degrees, the accidental results of glazing and other methods may be said to extend the contrasts to infinity. In such productions, where every smallest portion is an epitome of the whole, the eye still appreciates the fascinating effect of contrast, and the work is pronounced to be true and complete in the best sense of the words. The Venetian method of scumbling and glazing exhibits these minuter contrasts within each other, and is thus generally considered more refined than the system of breaking the colors, since it ensures a fuller gradation of hues, and produces another class of contrasts, those namely which result from degrees of transparence and opacity in some of the Flemish and Dutch masters, and sometimes in Reynolds. The two methods are combined in great perfection. pg 362. The chromatic diagram does not appear to be older than the last century. It is one of those happy adaptations of exacter principles to the objects of taste, which might have been expected from Leonardo da Vinci. That its true principle was duly felt is abundantly evident from the works of the colorists, as well as from the general observations of early writers. 5. The more practical directions, occasionally, to be met with in the treatises of Leon Battista, Alberti, Leonardo da Vinci, and others are conformable to the same system. Some Italian works not written by painters, which pretend to describe this harmony, are however very imperfect. 6. A passage in Lodovico Dolce's dialogue on colors is perhaps the only one worth quoting. He says, that writer who wishes to combine colors that are agreeable to the eye will put gray next dusky orange yellow green, next rose color blue next orange dark, purple black next dark green, white next black and white next flesh color. 7. The dialogue on painting by the same author has the reputation of containing some of Titian's precepts. If the above passage may be traced to the same source, it must be confessed that it is almost the only one of the kind in the treatise from which it is taken. Note Roman 500 par 66. In some of these cases, there can be no doubt that Goethe pg 363 attributes the contrast too exclusively to the physiological cause, without making sufficient allowance for the actual difference in the color of the lights. The purely physical nature of some colored shadows was pointed out by Pullman, and Dr. Eckermann took some pains to convince Goethe of the necessity of making such distinction. Goethe at first adhered to his extreme view, but some time afterwards confessed to Dr. Eckermann that in the case of the blue shadows of Snow 74, the reflection of the sky was undoubtedly to be taken into the account, Both causes may however operate together, he observed, and the contrast which a warm yellow light demands may heighten the effect of the blue. This was all his opponent contended one. With a few such exceptions, the general theory of Goethe with regard to colored shadows is undoubtedly correct. The experiments with 2 candles 68, and with colored glass and fluids 80, as well as the observations on the shadows of snow 75, are conclusive, for in all these cases, only one light is actually changed in color, while the other still assumes the complemental hue. Colored shadows, Dr. J. Muller observes, are usually ascribed to the physiological influence of contrast, the complementary color presented by the shadow being regarded as the effect of internal causes acting on that part of the retina, and not of the impression of colored rays from without. This explanation is the one adopted by Rumford, Goethe, Grot, thus Brands, Tortual, Pullman, and most authors who have studied the subject too. In the historical part, the author gives an account of a scarce French work, Observations sur les ombres coloris, Paris, 1782. The writer 3 concludes that the color pg 364 of shadows is as much owing to the light that causes them as to that which more faintly illumines them. Note Epar 69. This opinion of the author is frequently repeated 201, 312, 591, and as it seems at first sight to be at variance with a received principle of art, it may be as well at once to examine it. In order to see the general proposition in its true point of view, it will be necessary to forget the arbitrary distinctions of light and shade, and to consider all such modifications between highest brightness and absolute darkness, only as so many lesser degrees of light. 1. The author indeed by the word shadow always understands a lesser light. The received notion, as stated by Du Fresnoy 2, is much too positive and unconditional, and is only true when we understand the displaying light to comprehend certain degrees of half or reflected light, and the destroying shade to mean the intensest degree of obscurity. There are degrees of brightness which destroy color as well as degrees of darkness. 3. In general, color resides in a mitigated light, but a very little observation shows us that different colors require different degrees of light to display them. Leonardo da Vinci frequently inculcates the general principle above alluded to, but he as frequently qualifies it, for he not only remarks that the highest light may be comparative pg 365 privation of color, but observes with great truth that some hues are best displayed in their fully illumined parts, some in their reflections, and some in their half-lights, and again, that every color is most beautiful when lit by reflections from its own surface, or from a hue similar to its own. The Venetians went further than Leonardo in this view and practice, and he seems to allude to them when he criticizes certain painters who, in aiming at clearness and fullness of color, neglected what in his eyes was of superior importance, namely gradation and force of chiaroscuro. 5. That increase of color supposes increase of darkness, as so often stated by Goethe, may be granted without difficulty. To what extent, on the other hand, increase of darkness, or rather diminution of light, is accompanied by increase of color, is a question which has been variously answered by various schools. Examples of the total negation of the principle are not wanting, nor are they confined to the infancy of the art. Instances, again, of the opposite tendency are frequent in Venetian and early Flemish pictures, resembling the augmenting richness of gems, or of stained glass. 6 pg 366. Indeed, it is not impossible that the increase of color and shade, which is so remarkable in the pictures alluded to, may have been originally suggested by the rich and fascinating effect of stained glass, and the Venetians in this, as in many other respects, may have improved on a hint borrowed from the early German painters, many of whom painted on glass. 7. At all events, the principle of still increasing in color in certain hues seems to have been adopted in Flanders and in Venice at an early period. 8, while Giorgione, in carrying the style to the most daring extent, still recommended it, by corresponding grandeur of treatment in other respects. The same general tendency, except that the technical methods are less transparent, is however very striking in some of the painters of the school of Umbria, the instructors or early companions of Raphael. 9. The influence of pg 367. These examples, as well as that of Fra Bartolomeo in Florence, is distinctly to be traced in the works of the great artist just named, but neither is so marked as the effect of his emulation of a Venetian painter at a later period. The glowing color sometimes bordering on exaggeration which Raphael adopted in Rome, is undoubtedly to be attributed to the rivalry of Sebastian del Piombo. This painter, the best of Giorgioni's imitators, arrived in Rome, invited by Agostini Chigi in 1511, and the most powerful of Raphael's frescoes, the Heliodorus and Mass of Bolsena, as well as some portraits in the same style, were painted in the 2 following years, in the hands of some of Raphael's scholars again. This extreme warmth was occasionally carried to excess, particularly by Pirino del Vaga, with whom it often degenerated into redness. The representative of the glowing manner in Florence was Fra Bartolomeo, and in the same quality, considered abstractedly, some painters of the school of Ferrara were second to none. In another note, par 177, some further considerations, pg 368, are offered which may partly explain the prevalence of this style in the beginning of the 16th century here. We merely add that the conditions under which the appearance itself is most apparent in nature are perhaps more obvious in Venice than elsewhere. The color of general nature may be observed in all places with almost equal convenience, but with regard to an important quality in living nature, namely the color of flesh, perhaps there are no circumstances in which its effects at different distances can be so conveniently compared as when the observer and the observed gradually approach and glide past each other on so smooth an element, and in so undisturbed a manner as on the canals, and in the gondolas of Venice, the complexions from the peculiar mellow carnations of the Italian women to the sunburnt features and limbs of the mariners, presenting at the same time the fullest variety in another sense. At a certain distance, the color being always assumed to be unimpaired by interposed atmospheric reflections, appear kindled to intenser warmth. The fiery glow of Giorgione is strikingly apparent. The color is seen in its largest relation. The macchia, an expression so emphatically used by Italian writers, appears in all its quantity, and the reflections being the focus of warmth, the hue seems to deepen in shade. A nearer view gives the detail of cooler tints more perceptibly, and the forms are at the same time more distinct. Hence Lanzi is quite correct when, in distinguishing the style of Titian from that of Giorgione, he says that Titian's pg 369 was at once more defined and less fiery. In a still nearer observation, the eye detects the minute lights, which Leonardo da Vinci says are incompatible with effects such as those we have described, and which accordingly we never find in Giorgione and Titian. This large impression of color, which seems to require the condition of comparative distance for its full effect, was most fitly employed by the same great artists in works painted in the open air, or for large altarpieces, their celebrated frescoes, on the exterior of the Fondaco de Tedeschi, at Venice, to judge from their faint remains. And the descriptions of earlier writers were remarkable for extreme warmth in the shadows. The old frescoes in the open air throughout Friuli have often the same character, and owing to the fullness of effect, which this treatment ensures, are conspicuous at a very great distance. In assuming that the Venetian painters may have acquired a taste for this breadth of color, under the circumstances above alluded to, it is moreover to be remembered that the time for this agreeable study was the evening when the sun had already set behind the hills of Bassano, when the light was glowing but diffused, when shadows pg 370 were soft conditions, all agreeing with the character of their coloring, above all, when the hour invited the fairer portion of the population to betake themselves in their gondolas to the lagoons. The scene of this promenade was to the north of Venice. The quarter in which Titian at one time lived. A letter exists written by Francesco Priscianese, giving an account of his supping with the great painter in company with Jacopo Nardi, Pietro Aretino, the sculptor Sansovino, and others. The writer speaks of the beauty of the garden, where the table was prepared. Looking over the lagoons towards Murano, which part of the sea, he continues, as soon as the sun was down, was covered with 1,000 gondolas graced with beautiful women, and enlivened by the harmony of voices and instruments, which lasted till midnight, forming a pleasing accompaniment to our cheerful repast. To return to Goethe, perhaps the foregoing remarks may warrant the conclusion that his idea of color and shadow is not irreconcilable with the occasional practice of the best painters. The highest examples of the style thus defined are or were to be found in the works of Giorgione and Titian, and hence the style itself, though within that circle pg 371 few dare walk, is to be considered the grandest, and most perfect. Its possible defects or abuse are not to be dissembled. In addition to the danger of exaggeration, it is seldom united with the plenitude of light and shade, or with roundness, yet where fine examples of both modes of treatment may be compared the charm of color, has perhaps the advantage the difficulty of uniting qualities, so different in their nature, is proved by the very rare instances in which it has been accomplished Tintoret, in endeavoring to add chiaroscuro to Venetian color, in almost every instance, fell short of the glowing richness of Titian. Pg 372. Giacomo Bassan and his imitators, even in their dark effects, still had the principle of the gem in view. Their light in certain hues is the minimum of color, their lower tones are rich, their darks intense, and all is sparkling of the great painters, who, beginning on the other hand with chiaroscuro, sought to combine with it the full richness of color. Correggio, in the opinion of many, approached perfection nearest, but we may perhaps conclude with greater justice that the desired excellence was more completely attained by Rembrandt than by any of the Italians. N.B. The same edition before described has been consulted throughout. Lux varium vivumque dabit nullum umbra colorum. Do art graphicas. Know first that light displays and shade destroys. Refulgent natures, variegated dies masons. Translation. The early Italian schools, which adhered most to the Byzantine types, appear to have been also the most remarkable for depth, or rather darkness of color. This fidelity to customary representation was sometimes, as in the schools of Umbria, and to a certain extent in those of Siena and Bologna, the result of a religious veneration for the ancient examples in others, as in Venice the circumstance of frequent intercourse with the Levant is also to be taken into the account. The Greek pictures of the Madonna, not to mention other representations, were extremely dark in exaggerated conformity. It is supposed with the tradition respecting her real complexion. C.D. Agincourt Vol Roman 4p1, a belief, which obtained so late as Lamazzo's time. For speaking of the Madonna, he observes legacy Piero ci fu il quanto Bruna Giotto, who with the independence of genius betrayed a certain contempt for these traditions, failed perhaps to unite improvement with novelty, when he substituted a pale white flesh color for the traditional brown. Some specimens of his works, still existing at Padua, present a remarkable contrast, in this respect, with the earliest productions of the Venetian and Paduan artists. His works at Florence differ as widely from those of the earlier painters of Tuscany. This peculiarity was inherited by his imitators, and at one time almost characterized the Florentine school. Leon Battista Alberti was not perhaps the first who objected to it. Vorrei io ci dai pittori fos comparato, il color bianco assai più caro che la preciosissima gem della pittura. Roman 1 Roman 2. The attachment of Fra Bartolomeo to the grave character of the Christian types is exemplified in his deep coloring, as well as in other respects. Christophori sancti specim quicumque tutor. Illo namque dinullo languor tenetur. Hence the practice of painting the figure on the outside of churches, hence its colossal size, and hence the powerful qualities in color, above described. See Maniego Storia del Bel Arti Friulane. The augmentation of color in subdued light was still more directly taught by Lamazzo. He composes the haftons of flesh merely by diminishing the quantity of white, the proportions of the other colors employed, for he enters into minute details, remaining unaltered. See his Trattato della Arte della Pittura Milan, 1584 p. 301. Note F. Par 83. The author in these instances seems to be anticipating his subsequent explanations on the effect of semi-transparent mediums, for an explanation of the general view contained in these paragraphs respecting the gradual increase of color from high light. See the last note. The anonymous French work before alluded to, among other interesting examples, contains a chapter on shadows cast by the upper light of the sky and colored by the setting sun. The effect of this remarkable combination is that the light on a wall is most colored immediately under a projecting roof and becomes comparatively neutralized in proportion to its distance from the edge of the darkest shade. Note Gpar 98. The simplest case of the phenomenon, which Goethe calls a subjective halo, and one which at once explains its cause, is the following. Regard a red wafer on a sheet of white paper, keeping the eye steadfastly fixed on a point at pg 373. Its center, when the retina is fatigued, withdraw the head a little from the paper, and a green halo will appear to surround the wafer. By this slight increase of distance, the image of the wafer itself on the retina becomes smaller, and the ocular spectrum, which before coincided with the direct image being now relatively larger, is seen as a surrounding ring S. F. Goethe mentions cases of this kind, but does not class them with subjective halos. See Par 30. Note H-bar 113. Cases of this kind are by no means uncommon. Several interesting ones are related in Sir John Herschel's article on light in the Encyclopaedia Metropolitana. Careful investigation has, however, shown that this defect of vision arises, in most if not in all cases, from an inability to perceive the red, not the blue rays. The terms are so confounded by the individuals thus affected that the comparison of colors in their presence is the only criterion. SF. Note Roman 1 par 135. The author more than once admits that this chapter on pathological colors is very incomplete and expresses a wish par 734 that some medical physiologists would investigate the subject further. This was afterwards, in a great degree, accomplished by Dr. Johannes Müller in his memoir über die Fantastischen Geschichtserscheinungen Koblenz 1826. Similar phenomena have been also investigated with great labor and success by Perkinge. For a collection of extraordinary facts of the kind recorded by these writers, the reader may consult Scott's Letters on Demonology and Witchcraft 1. The instances adduced by Müller and others are, however, intended to prove the inherent capacity of the organ of vision to produce light and colors in some maladies of the eye. The patient, it seems, pg 374, suffers the constant presence of light. Without external light, the exciting principle in this case is thus proved to be within, and the conclusion of the physiologists is that external light is only one of the causes which produce luminous and colored impressions. That this view was anticipated by Newton may be gathered from the concluding query in the third book of his Optics. Note Capar 140. Catoptrical colors. The colors included under this head are principally those of fibers and grooved surfaces. They can be produced artificially by cutting parallel grooves on a surface of metal from 2,000 to 10,000. In the Inch C. Brewster's Optics p. 120, the colors called by Goethe paroptical correspond with those produced by the diffraction or inflection of light in the received theory. C. Brewster p. 95. The phenomena included under the title epoptical colors are generally known as the colors of thin plates. They vary with the thickness of the film, and the color seen by reflection always differs from that seen by transmission. The laws of these phenomena have been thoroughly investigated. See Nobili and Brewster p. 100 SF. The colors produced by the transmission of polarized light through crystallized mediums were described by Goethe in his Mode, subsequently to the publication of his general theory, under the name of entoptic colors. See note to par 485. Note Roman 50 par 150. We have in this and the next paragraph the outline of Goethe's system. The examples that follow seem to establish the doctrine here laid down. But there are many cases which it appears cannot be explained on such principles. Hence, philosophers generally prefer the theory of absorption, according to which it appears that certain mediums have the property of absorbing some of the component pg 375 rays of white light, while they allow the passage of others. 1. Whether all the facts adduced by Goethe, for instance, that recorded in par 172, are to be explained by this doctrine, we leave to the investigators of nature to determine. Dr. Eckermann, in conversing with Goethe, thus described the two leading phenomena 156-158, as seen by him in the Alps, at a distance of 18 or 20 miles at midday in bright sunshine. The snow appeared yellow, or even reddish, while the dark parts of the mountain free from snow were of the most decided blue. The appearances did not surprise me, for I could have predicted that the mass of the interposed medium would give a deep yellow tone to the white snow. But I was pleased to witness the effect, since it so entirely contradicted the erroneous views of some philosophers who assert that the air has a blooding quality. The observation, said Goethe, is of importance, and contradicts the error you allude to completely too. The same writer has some observations to the same effect on the color of the Rhone, at Geneva, a circumstance of an amusing nature, which he relates in confirmation of Goethe's theory, deserves to be inserted here. At Strasbourg, passing by a shop, I saw a little glass bust of Napoleon, which relieved, as it was against the dark interior, pg 376 of the room, exhibited every gradation of blue from milky light blue to deep violet. I foresaw that the bust seen from within the shop with the light behind it would present every degree of yellow, and I could not resist walking in and addressing the owner, though perfectly unknown to me. My first glance was directed to the bust, in which, to my great joy, I saw at once the most brilliant colors of the warmer kind, from the palest yellow to dark ruby red. I eagerly asked. If I might be allowed to purchase the bust, the owner replied that he had only lately brought it with him from Paris from a similar attachment to the emperor to that which I appeared to feel, but as my ardor seemed far to surpass his, I deserved to possess it. So invaluable did this treasure seem in my eyes, that I could not help looking at the good man with wonder, as he put the bust into my hands for a few francs. I sent it together with a curious medal, which I had bought in Milan as a present to Goethe, and when at Frankfurt received the following letter from him, the letter which Dr. Eckermann gives entire thus concludes: when you return to Weimar you shall see the bust in bright sunshine, and while the transparent countenance exhibits a quiet blue, the thick mass of the breast and epaulets glows with every gradation of warmth from the most powerful rubber downwards. And as the granite statue of Memnon uttered harmonious sounds, so the dim glass image displays itself in the pomp of colors. The hero is victorious still in supporting the Farbenlayer 4. One effect of Goethe's theory has been to invite the attention of scientific men to facts and appearances, which had before been unnoticed or unexplained to the above cases. May be added the very common, but very important fact in painting that a light warm color passed in a semi-transparent PG 377 state over a dark one produces a cold bluish hue, while the operation reversed produces extreme warmth. On the judicious application of both these effects, but especially of the latter, the richness and brilliancy of the best-colored pictures, greatly depends. The principle is to be recognized in the productions of schools apparently opposite in their methods. Thus the practice of leaving the ground through which a light color is apparent as a means of ensuring warmth and depth is very common among the Dutch and Flemish painters. The Italians again, who preferred a solid underpainting, speak of internal light as the most fascinating quality in color when the ground is entirely covered by solid painting. As in the works of some colorists, the warmest tints in shadows and reflections have been found necessary to represent it. This was the practice of Rembrandt frequently, and of Reynolds universally, but the glow of their general color is still owing to its being repeatedly or ultimately enriched on the above principle. Lastly, the works of those masters who were accustomed to paint on dark grounds are often heavy and opaque, and even where this influence of the ground was overcome, the effects of time must be constantly diminishing the warmth of their coloring as the surface becomes rubbed, and the dark ground more apparent through it. The practice of painting on dark grounds was intended by the Carracci to compel the students of their school to aim at the direct imitation of the model, and to acquire the use of the brush for the dark ground could only be overcome by very solid painting. The result answered their expectations as far as dexterity of pencil was concerned, but the method was fatal to brilliancy of color. An intelligent writer of the 17th century 5 relates that Guido adopted his extremely light style from seeing the rapid change in some works of the Carracci soon after they were done at PG 378. Is important, however, to remark that Guido's remedy was external rather than internal brilliancy, and it is evident that so powerless a brightness as white paint can only acquire the splendor of light by great contrast, and above all by being seen through external darkness. The secret of Van Eyck and his contemporaries is always assumed to consist in the vehicle varnish or oils he employed, but a far more important condition of the splendor of color in the works of those masters was the careful preservation of internal light, by painting thinly, but ultimately with great force on white grounds. In some of the early Flemish pictures in the Royal Gallery at Munich, it may be observed that wherever an alteration was made by the painter, so that a light color is painted over a dark one, the color is as opaque as in any of the more modern pictures, which are generally contrasted with such works. No quality in the vehicle could prevent this opacity under such circumstances, and on the other hand, provided the internal splendor is by any means preserved, the vehicle is comparatively unimportant. It matters not, say the authorities on these points, whether the effect in question is attained by painting thinly over the ground in the manner of the early Flemish painters, and sometimes of Rubens, or by painting a solid light preparation, to be afterwards toned to richness, in the manner of the Venetians. Among the mechanical causes of the clearness of colors superposed on a light preparation may be mentioned that of careful grinding. All writers on art who have descended to practical details have insisted on this. From the appearance of some Venetian pictures, it may be conjectured that the colors of the solid underpainting were sometimes less perfectly ground than the scumbling colors, the light having to pass through the one and to be reflected from the other. The Flemish painters appear to have used careful ground pigments universally, This is very evident in Flemish copies from Raphael, which though pg 379, equally impasted with the originals, are to be detected among other indications by the fine Legrand colors employed. Note Roman 1000 par. 177. Without entering further into the scientific merits or demerits of this chapter on the first class of dioptrical colors, it is to be observed that several of the examples correspond with the observations of Leonardo da Vinci, and again, with those of a much older authority, namely Aristotle. Goethe himself admits, and it has been remarked by others, that his theory in many respects closely resembles that of Aristotle. Indeed, he confesses that at one time he had an intention of merely paraphrasing that philosopher's treatise on colors too. We have already remarked note on par 150 that Goethe's notion with regard to the production of warm colors by the interposition of dark transparent mediums before a light ground agrees with the practice of the best schools in coloring, and it is not impossible that the same reasons which may make this part of the doctrine generally acceptable to artists now may have recommended the very similar theory of Aristotle to the painters of the 15th and 16th centuries. At all events, it appears that the ancient theory was known to those painters. It is unnecessary to dwell on the fact that the doctrines of Aristotle were enthusiastically embraced and generally inculcated at the period in question 3. But it has not been pg 380 observed that the Italian writers, who translated, paraphrased, and commented on Aristotle's treatise on colors in particular, were in several instances the personal friends of distinguished painters. Celio Calcagnini 4 had the highest admiration for Raphael. Lodovico Dolce 5 was the eulogist of Titian. Portia 6, whose amicable relations with the Florentine painters may be inferred from various circumstances, lectured at Florence on the Aristotelian doctrines. Early in the 16th century, the Italian translations were later, but still prove that these studies were undertaken with reference to the arts, for one of them is dedicated to the painter, Sigali 7. pg 381. The writers on art from Leon Battista Alberti to Borghini, without mentioning later authorities, either tacitly coincide with the Aristotelian doctrine or openly profess to explain it. It is true this is not always done in the clearest manner, and some of these writers might say with Lodovico Dolce, I speak of colors, not as a painter, for that would be the province of the divine Titian. Leonardo da Vinci in his writings, as in everything else, appears as an original genius. He now and then alludes generally to opinions of philosophers, but he quotes no authority ancient or modern. Nevertheless, a passage on the nature of colors, particularly where he speaks of the colors of the elements, appears to be copied from Leon Battista Alberti 8, and from the mode in which some of Leonardo's propositions are stated, it has been supposed 9 that he had been accustomed at Florence to the form of the Aristotelian philosophy. At all events, some of the most important of his observations respecting light and colors have a great analogy with those contained in the treatise in question. The following examples will be sufficient to prove this coincidence. The corresponding passages in Goethe are indicated as usual by the numbers of the paragraphs. The references to Leonardo's treatise are given at the bottom of the page. Aristotle. A vivid and brilliant red appears when the weak rays of the sun are tempered by subdued and shadowy white. Leonardo. The air which is between the sun and the earth at sunrise pg 382, or sunset, always invests what is beyond it more than any other higher portion of the air. This is because it is whiter. A bright object loses its whiteness in proportion to its distance from the eye, much more when it is illuminated by the sun, for it partakes of the color of the sun, mingled with the color, tempered by the mass of the air interposed between the eye and the brightness. Aristotle. If light is overspread with much obscurity, a red color appears. If the light is brilliant and vivid, this red changes to a flame color. 160. Leonardo. This the effect of transparent colors on various grounds is evident in smoke, which is blue when seen against black, but when it is opposed to the light blue sky, it appears brownish and reddening. Aristotle. White surfaces, as a ground for colors, have the effect of making the pigments appear in greater splendor. 902. pg 383. Leonardo. To exhibit colors in their beauty, the whitest ground should be prepared. I speak of colors that are more or less transparent. Aristotle. The air near us appears colorless, but when seen in depth owing to its thinness, it appears blue, for where the light is deficient beyond it, the air is affected by the darkness, and appears blue in a very accumulated state. However, it appears, as is the case with water, quite white. 158. Leonardo. The blue of the atmosphere is owing to the mass of illuminated air interposed between the darkness above and the earth. The air in itself has no color, but assumes qualities according to the nature of the objects, which are beyond it. The blue of the atmosphere will be the more intense in proportion to the degree of darkness beyond it. Elsewhere, if the air had not darkness beyond it, it would be white. Aristotle. We see no color in its pure state, but every hue is variously intermingled with others, even when it is uninfluenced by other colors. The effect of light and shade modifies it in various ways, so that it undergoes alterations and appears unlike itself. Thus bodies seen in shade, or in pg 384 light, in more pronounced or softer sunshine, with their surfaces inclined this way or that, with every change exhibit a different color. Leonardo. No substance will ever exhibit its own hue unless the light which illumines it is entirely similar in color. It very rarely happens that the shadows of opaque bodies are really similar in color to the illumined parts. The surface of every substance partakes of as many hues as are reflected from surrounding objects. Aristotle. So again, with regard to the light of fire, of the moon, or of lamps, each has a different color, which is variously combined with differently colored objects. Leonardo. We can scarcely ever say that the surface of illumined bodies exhibits the real color of those bodies. Take a white band and place it in the dark, and let it receive light by means of 3 apertures from the sun, from fire, and from the sky. The white band will be tricolored. Aristotle. When the light falls on any object and assumes, for example, a red or green tint, it is again reflected on other substances, thus undergoing a new change. But this effect, though it really takes place, is not appreciable by the eye, though the light thus reflected to the eye is composed of a variety of colors. The principle of these only are distinguishable. Leonardo. No color reflected on the surface of another color tinges that surface with its own color merely, but will be pg 385 mixed with various other reflections impinging on the same surface. But such effects, he observes elsewhere, are scarcely, if at all, distinguishable in a very diffused light. Aristotle. Thus all combinations of colors are owing to 3 causes: the light, the medium through which the light appears, such as water or air, and lastly, the local color from which the light happens to be reflected. Leonardo. All illumined objects partake of the color of the light they receive. Every opaque surface partakes of the color of the intervening transparent medium, according to the density of such medium, and the distance between the eye and the object. The medium is of 2 kinds: either it has a surface like water, Roman 100, or it is without a common surface like the air. In the observations on trees and plants, more points of resemblance might be quoted. The passages corresponding with Goethe's views are much more numerous. It is remarkable that Leonardo, in opposition, it seems to some authorities, agrees with Aristotle in reckoning black and white as colors, placing them at the beginning and end of the scale like Aristotle. Again, he frequently makes use of the term black for obscurity. He even goes further, pg 386, for he seems to consider that blue may be produced by the actual mixture of black and white, provided they are pure. The ancient author, however, explains himself on this point as follows: we must not attempt to make our observations on these effects by mixing colors, as painters mix them, but by remarking the appearances as produced by the rays of light mingling with each other. When we consider that Leonardo's treatise professes to embrace the subject of imitation in painting, and that Aristotle's briefly examines the physical nature and appearance of colors, it must be admitted that the latter sustains the above comparison with advantage, and it is somewhat extraordinary that observations indicating so refined a knowledge of nature as regards the picturesque should not have been taken into the account, for such appears to be the fact. In the various opinions and conjectures that have been expressed from time to time on the painting of the Greeks, the treatise in question must have been written when Apelles painted or immediately before. And as a proof, pg 387, that Aristotle's remarks on the effect of semi-transparent mediums were not lost on the artists of his time, the following passage from Pliny is subjoined, for though it is well known, it acquires additional interest from the foregoing extracts. He appels past a dark color over his pictures, when finished so thin that it increased the splendor of the tints, while it protected the surface from dust and dirt. It could only be seen on looking into the picture. The effect of this operation, judiciously managed, was to prevent the colors from being too glaring, and to give the spectator the impression of looking through a transparent crystal. At the same time, it seemed almost imperceptibly to add a certain dignity of tone to colors that were too florid. This, says Reynolds, is a true and artist-like description of glazing or scumbling, such as was practiced by Titian and the rest of the Venetian painters. The account of Pliny has in this instance internal evidence of truth, but it is fully confirmed by the following passage in Aristotle. Another mode, in which the effect of colors is exhibited, is when they appear through each other, as painters employ them, when they glaze 26 a dark color over a lighter one, just as the sun, which is in itself white, assumes a red color when seen through darkness and smoke. This operation also ensures a variety of colors, for there will be a certain ratio between those which are on the surface and those which are in depth de sensu et sensili. Aristotle's notion respecting the derivation of colors from white and black may perhaps be illustrated by the following opinion on the very similar theory of Goethe. Goethe and Seebeck regard color as resulting from the mixture of white and black, and ascribe to the different pg 388 colors a quality of darkness, by the different degrees of which they are distinguished, passing from white to black, through the gradations of yellow, orange, red, violet, and blue, while green appears to be intermediate again between yellow and blue. This remark, though it has no influence in weakening the theory of colors proposed by Newton, is certainly correct, having been confirmed experimentally by the researches of Herschel, who ascertained the relative intensity of the different colored rays by illuminating objects under the microscope. By their means, Roman 100. Another certain proof of the difference in brightness of the different colored rays is afforded by the phenomena of ocular spectra. If after gazing at the sun, the eyes are closed so as to exclude the light, the image of the sun appears at first as a luminous or white spectrum upon a dark ground, but it gradually passes through the series of colors to black, that is to say, until it can no longer be distinguished from the dark field of vision, and the colors which it assumes are successively those intermediate between white and black in the order of their illuminating power, or brightness, namely yellow, orange, red, violet, and blue. If, on the other hand, after looking for some time at the sun, we turn our eyes towards a white surface, the image of the sun is seen at first as a black spectrum upon the white surface, and gradually passes through the different colors from the darkest to the lightest, and at last becomes white, so that it can no longer be distinguished from the white surface. 27 c. par 40-44. It is not impossible that Aristotle's enumeration of the colors may have been derived from or confirmed by this very experiment. Speaking of the afterimage of colors, he says the impression not only exists in the sensorium, in the act of perceiving, but remains when the organ is at rest. Thus, if we look long and intently on any object, pg 389, when we change the direction of the eyes, a responding color follows. If we look at the sun, or any other very bright object, and afterwards shut our eyes, we shall, as if in ordinary vision, first see a color of the same kind. This will presently be changed to a red color, then to purple, and so on, till it ends in black, and disappears to insomnize. Raffaello Borghini, in his attempt to describe the doctrine of Aristotle with a view to painting, observes there are two principles which concur in the production of color, namely light and transparence, but he soon loses this clue to the best part of the ancient theory, and when he has to speak of the derivation of colors from white and black, he evidently understands it in a mere atomic sense, and adds, I shall not at present pursue the opinion of Aristotle, who assumes black and white as principal colors, and considers all the rest as intermediate between them. Il Riposo, 1 Roman 2. Accordingly, like Lodovico Dolce, he proceeds to a subject where he was more at home, namely the symbolical meaning of colors. Note N par 246. The appearance of white in the center, according to the Newtonian theory, arises from each line of rays, forming its own spectrum. These spectra, superposing each other on all the middle part, leave uncorrected, unneutralized colors, only at the two edges. SF1. Note O par 252. These experiments with gray objects which exhibit different colors, as they are on dark or light grounds, were suggested. Goethe tells us by an observation of Antonius Lucas of Luttich, one of Newton's opponents, and in the opinion of the author, one of the few who made any well-founded objections, Lucas, remarks that the sun acts merely as a circumscribed image in the prismatic experiments, and that if the same sun had a lighter background than itself, the colors of the prism would be reversed. Thus in Goethe's experiments, when the gray disk is on a dark ground, it is edged with blue on being magnified. When on a light ground it is edged with yellow. Goethe acknowledges that Lucas had in some measure anticipated his own theory. Vol. Roman 2, p. 440. Note ppr 284. The earnestness and pertinacity with which Goethe insisted pg 390 that the different colors are not subject to different degrees of refrangibility are at least calculated to prove that he was himself convinced on the subject, and however extraordinary it may seem, his conviction appears to have been the result of infinite experiments and the fullest ocular evidence. He returns to the question in the controversial division of his work in the historical part, and again, in the description of the plates. In the first he endeavors to show that Newton's experiment with the blue and red paper depends entirely on the colors being so contrived as to appear elongated or curtailed by the prismatic borders. If he says we take a light blue instead of a dark one, the illusion in the latter case is at once evident according to the Newtonian theory. The yellowed red is the least refrangible color, the violet the most refrangible. Why then does Newton place a blue paper instead of a violet next the red? If the fact were as he states it, the difference in the refrangibility of the yellowed and violet would be greater than in the case of the yellowed and blue. But here comes in the circumstance that a violet paper conceals the prismatic borders less than a dark blue paper, as every observer may now easily convince himself. Roman 100 Polmischer Thale par 45 Disiguliers in repeating the experiment confess that if the ground of the colors was not black, the effect did not take place so well. Goethe adds, not only not so well, but not at all. Historischer Thale p. 459. Lucas of Luttich, one of Newton's first opponents, denied that two differently colored silks are different in distinctness when seen in the microscope. Another experiment proposed by him to show the unsoundness of the doctrine of various refrangibility was the following: let a tin plate, painted with the prismatic colors in stripes, be placed in an empty cubical vessel, so that from the spectator's point of view, the colors may be just hidden by the rim. On pouring water into this vessel, all the colors become visible in the same degree, whereas it was contended, if the Newtonian doctrine were true, some pg 391 colors would be apparent before others. Historischer Thale p. 434. Such are the arguments and experiments adduced by Goethe on this subject. They have all probably been answered in his analysis of Newton's celebrated Experimentum Crucis. He shows again that by reversing the prismatic colors refracting a dark, instead of a light, object, the colors that are the most refrangible in Newton's experiment become the least so, and vice versa. Without reference to this objection, it is now admitted that the difference of color is not a test of difference of refrangibility, and the conclusion deduced by Newton is no longer admissible as a general truth, that to the same degree of refrangibility ever belongs the same color, and to the same color ever belongs the same degree of refrangibility. Brewster's Optics, p. 72. Note QPAR 387. With the exception of two very inconclusive letters to Sulpice Boisserie and some incidental observations, in the conclusion of the historical portion, under the head of entoptic colors, Goethe never returned to the rainbow among the plates. He gave the diagram of Antonius de Dominis. An interesting chapter on halos, parhelia, and paraxylon will be found in Brewster's Optics, p. 270. Note RPAR 478. The most complete exhibition of the coloring or mantling of metals was attained by the late Cav Nobili, professor of physical science in Florence. The general mode in which these colors are produced is thus explained by him. 1. A point of platinum is placed vertically at the distance of about half a line above a lamina of the same metal laid pg 392 horizontally at the bottom of a vessel of glass or porcelain. Into this vessel, a solution of acetate of lead is poured so as to cover not only the lamina of platinum, but 2 or 3 lines of the point as well. Lastly, the point is put in communication with the negative pole of a battery, and the lamina with the positive pole. At the moment in which the circuit is completed, a series of colored rings is produced on the lamina under the point, similar to those observed by Newton in lenses pressed together. The scale of colors thus produced corresponds very nearly with that observed by Newton and others in thin plates and films, but it is fuller for it extends to 4 to 4 tints. The following list, as given by Nobili, is divided by him into 4 series, to agree with those of Newton. The numbers in brackets are those of Newton's scale. The Italian terms are untranslated, because the colors in some cases present very delicate transitions too. First series. Biondo Argentino 43-6 Fulvo Exis. Biondo 7 Rosso di Rame 6. Biondo Doro 8 Acria. Biondo Exciso 5-9 Acria Violacia. Fulvo 10 Rosso Violacio 7. Second series. Violetto 8-20 Giallo Exis. Indaco 10-21 Gilorancio. Blue Carico 22 Rancio 13. Blue 23 Rancirosixio. Blue Chiro 11-24 Ranciros. Celeste 25 Rosarancio. Celeste Gelagnolo 26 Lacarancia 14. Giallo Chirissimo 12-27 Lacca. Giallo 28 Lacca Excessa 15. Third series PG 393. Lacca Purpurea 1634 Verde Giallo 20. Lacca Churchinixia 1735 Verde Rancio. Porpora Verdignola 1836 Rancio Verde 21. Verde 1937 Rancirosio. Verde Gelagnolo 38 Laccarosia 22. Fourth series. Lacca Violacia 2443 Verde Giallo Rosixio 28. Violacio Verdagnolo 2544 Laccarosia 30. Verde 26. Verde Giallo 27. These tints, Professor Nobili observes, are disposed according to the order of the thin mantlings, which occasion them. The color of the thinnest film is numbered 1, then follow in order those produced by a gradual thickening of the medium. I cannot deceive myself in this arrangement, for the thin films, which produce the colors, are all applied with the same electrochemical process. The battery, the solution, the distances, Roman 100, are always the same. The only difference is the time the effect is suffered to last. This is a mere instant for the color of No 1, a little longer for No 2, and so on increasing for the succeeding numbers. Other criterions, however, are not wanting to ascertain the place to which each tint belongs. The scale differs from that of Newton inasmuch as there is no blue in Nobili's first series, and no green in the second. Green only appears in the third and fourth series. The first series, says the professor, is remarkable for the fire and metallic appearance of its tints, the second for clearness and brilliancy, the third and fourth for force and richness. The fourth, he observes, has the qualities of the third in a somewhat lesser degree, but the two greens are very nearly alike. It is to be observed that red and green are the principal PG 394 ingredients in the third and fourth series, blue and yellow in the second and first. Note S-bar 485. A chapter on entoptic colors contained in the supplement to Goethe's works was translated with the intention of inserting it among the notes. But on the whole, it was thought most advisable to omit it. Like many other parts of the doctrine of colors, it might have served as a specimen of what may be achieved by accurate observation, unassisted by a mathematical foundation. The whole theory of the polarization of light has, however, been so fully investigated since Goethe's time that the chapter in question would probably have been found to contain very little to interest scientific readers, for whom it seems chiefly to have been intended. One observation occurs in it, which indeed has more reference to the arts. In order to make this intelligible, the leading experiment must be first described, and for this purpose the following extracts may serve. The experiment in its simplest form is to be made as follows: let a tolerably thick piece of plate glass be cut into several squares of 1.5 inches, let these be heated to a red heat, and then suddenly cooled. The squares of glass, which do not split in this operation, are now fit to produce the entoptic colors. In our mode of exhibiting the phenomenon, the observer is above all to betake himself with his apparatus to the open air. All dark rooms, all small apertures, PG 395 foramina exigua 2, are again to be given up. A pure cloudless sky is the source whence we are derive a satisfactory insight into the appearances. The atmosphere being clear, let the observer lay the squares above described on a black surface, so placing them that two sides may be parallel with the plane of vision. When the sun is low, let him hold the squares so as to reflect to the eye that portion of the sky opposite to the sun, and he will then perceive 4 dark points in the 4 corners of a light space. If after this, he turned towards the quarters of the sky at right angles with that where his first observation was made, he will see 4 bright points on a dark ground between the two regions. The figures appear to fluctuate. From this simple reflection, we now proceed to another which but little more complicated exhibits the appearance much more distinctly a solid cube of glass, or in its stead, a cube composed of several plates is placed on a black mirror, or held a little inclined above it at sunrise, or sunset, the reflection of the sky being now suffered to fall through the cube on the mirror, the appearance above described will appear more distinctly the reflection of the sky. Opposite to the sun, presents 4 dark points on a light ground. The 2 lateral portions of the sky present the contrary appearance, namely 4 light points on a dark ground. The space not occupied by the corner points appears in the first case as a white cross in the other, as a black cross. Expressions hereafter employed in describing the phenomena before sunrise or after sunset, in a very pg 396 subdued light. The white cross appears on the side of the sun, also 3. We thus conclude that the direct reflection of the sun produces a light figure, which we call a white cross. The oblique reflection gives a dark figure, which we call a black cross. If we make the experiment all round the sky, we shall find that a fluctuation takes place in the intermediate regions. We pass over a variety of observations on the modes of exhibiting this phenomenon, the natural transparent substances, which exhibit it best, and the detail of the colors seen within for them, and proceed to an instance where the author was enabled to distinguish the direct from the oblique reflection by means of the entoptic apparatus in a painter's study. An excellent artist, unfortunately too soon taken from us, Ferdinand Jagemann, who with other qualifications had a fine eye for light and shade, color and keeping, had built himself a painting room for large as well as small works. The single high window was to the north facing the most open sky, and it was thought that all necessary requisites had been sufficiently attended to. But after our friend had worked for some time, it appeared to him in painting portraits that the faces he copied were not equally well lighted at all hours of the day, and yet his sitters always occupied the same place, and the serenity of the atmosphere was unaltered. The variations of the favorable and unfavorable light had their periods during the day. Early in the morning, the light appeared most unpleasantly gray and unsatisfactory, pg 397. It became better till at last about an hour before noon, the objects had acquired a totally different appearance. Everything presented itself to the eye of the artist in its greatest perfection, as he would most wish to transfer it to canvas in the afternoon. This beautiful appearance vanisheth. Light became worse, even in the brightest day, without any change having taken place in the atmosphere. As soon as I heard of this circumstance, I at once connected it in my own mind with the phenomena which I had been so long observing, and hastened to prove by a physical experiment what a clear-sighted artist had discovered entirely of himself, to his own surprise and astonishment. I had the second 5 entoptic apparatus brought to the spot, and the effect on this was what might be conjectured from the above statement. At midday, when the artist saw his model best lighted, the north direct reflection gave the white cross in the morning and evening. On the other hand, when the unfavorable oblique light was so unpleasant to him, the cube showed the black cross in the intermediate hours. The state of transition was apparent. The author proceeds to recall to his memory instances where works of art had struck him by the beauty of their appearance, owing to the light coming from the quarter opposite the sun in direct reflection, and adds, since these decided effects are thus traceable to their cause, the friends of art in looking at and exhibiting pictures may enhance the enjoyment to themselves and others by attending to a fortunate reflection. Note Tpar 496. Since Goethe wrote, all the earths have been decomposed and have been shown to be metallic bases united with oxygen, but this does not invalidate his statement f. Note Upar 502. The cold nature of black and its affinity to blue are assumed by the author throughout. If the quality is opaque, and consequently grayish, such an affinity is obvious, but in many fine pictures, intense black seems to be considered as the last effect of heat, and an accompanying crimson and orange may be said rather to present a difference of degree than a difference of kind. In looking at the great picture of the globe, we find this last result produced in climates where the sun has greatest power, as we find it the immediate effect of fire. The light parts of black animals are often of a mellow color. The spots and stripes on skins and shells are generally surrounded by a warm hue, and are brown before they are absolutely black in combustion. The blackness which announces the complete ignition is preceded always by the same mellow orange color. The representation of this process was probably intended by the Greeks in the black and subdued orange of their vases. Indeed, the very colors may have been first produced in the kiln, but without supposing that they were retained merely from this accident. The fact that the combination itself is extremely harmonious would be sufficient to account for its adoption. Many of the remarks of Aristotle I and Theophrastus II on the production of black are derived from the observation of the action of fire, and on one occasion, the former distinctly alludes to the terracotta kiln that the above opinion as to the nature of black was prevalent in the 16th century, may be inferred pg 399 from Lamazzo, who observes quanto all origin e generazione de colori la frigidità, e la mater della biancesa, il calor e padre del nero 3. The positive coldness of black may be said to begin when it approaches gray. When Leonardo da Vinci says that black is most beautiful in shade, he probably means to define its most intense and transparent state, when it is furthest removed from gray. Note Roman 5 par 555. The nature of vehicles or liquid mediums to combine with the substance of colors has been frequently discussed by modern writers on art, and may perhaps be said to have received as much attention as it deserves. Reynolds smiles at the notion of our not having materials equal to those of former times. And, indeed, although the methods of individuals will always differ, there seems no reason to suppose that any great technical secret has been lost in these inquiries, however, which relate merely to the mechanical causes of bright and durable coloring. The skill of the painter in the adequate employment of the higher resources of his art is as if by common consent left out of the account, and without departing from this mode of considering the question, we would merely repeat a conviction before expressed, viz., that the preservation of internal brightness, a quality compatible with various methods, has had more to do with the splendor and durability of finely colored pictures than any vehicle. The observations that follow are therefore merely intended to show how far the older written authorities on this subject agree with the results of modern investigation, without at all assuming that the old methods, if known, need be implicitly followed. On a careful examination of the earlier pictures, it is said pg 400 that a resinous substance appears to have been mingled with the colors together with the oil, that the fracture of the indurated pigment is shining, and that the surface resists the ordinary solvents. This admixture of resinous solutions or varnishes with the solid is not alluded to as far as we have seen by any of the writers on Italian practice, but as the method corresponds with that now prevalent in England, the above hypothesis is not likely to be objected to for the present. Various local circumstances and relations might seem to warrant the supposition that the Venetian painters used resinous substances, an important branch of commerce between the mountains of Friuli and Venice. Still, consists in the turpentine or furacin, two similar substances produced from various trees and known under the common name of balsams. 3 were imported from the east through Venice for general use before the American balsams. 4 in some degree superseded them, and a Venetian painter, Marco Baschini, in his description of the archipelago, does not omit to speak of the abundance of mastic produced in the island of Scio. 5. The testimonies, direct or indirect, against the employment pg 401 of any such substances by the Venetian painters in the solid part of their work seem notwithstanding very conclusive. We begin with the writer just named in his principal composition, a poem 6 describing the practice and the productions of the Venetian painters. Baschini speaks of certain colors, which they shunned, and adds, in like manner, they avoided shining liquids and varnishes, which I should rather call lacquers. 7, for the surface of flesh, if natural and unadorned, assuredly does not shine. Nature speaks as to this plainly after alluding to the possible alteration of this natural appearance by means of cosmetics. He continues, foreign artists set such great store by these varnishes that a shining surface seems to them the only desirable quality in art. What trash it is they prize furacin, mastic and sandarache and larcracin, not to say treacle stuff fit to polish boots. 8. If those great painters of ours had to represent armor a gold, vase a mirror, or anything of the kind, they made it shine with simple colors. 9. This writer so frequently alludes to the Flemish painters, of whose great reputation he sometimes seems jealous, that the above strong expression of opinion may have been pointed at them. On the other hand, It is to be observed that the term forestieri strangers does not necessarily mean transalpine foreigners, but includes those Italians who were pg 402 not of the Venetians state the directions given by Raphael Borghini, and after him, by Armanini respecting the use and preparation of varnishes, made from the very materials in question, may thus have been comprehended in the censure especially, as some of these recipes were copied and republished in Venice by Bisagno in 1642, that is only 6 years before Boschini's poem appeared. Ridolfi's Lives of the Venetian Painters 1648 may be mentioned with the two last. His only observation respecting the vehicle is that Giovanni Bellini, after introducing himself by an artifice into the painting room of Antonello de Messina, saw that painter dip his brush from time to time in linseed oil. This story, related about 200 years after the supposed event, is certainly not to be adduced as very striking evidence in any way. Among the next writers in order of time, prior to Bisagno, may be mentioned Caneperio 1619. His work De Atrimentes contains a variety of recipes for different purposes. One chapter, De Atrimentes Diversicoloribus, has a more direct reference to painting. His observations under this head are by no means confined to the preparation of transparent colors, but he says little on the subject of pg 403 varnishes. After describing a mode of preserving white of egg, he says others are accustomed to mix colors in liquid varnish, and linseed or noodle, for a liquid and oily varnish, binds the different layers of colors better together, and thus forms a very fit glazing material. On the subject of oils, he observes that linseed oil was in great request among painters, who however were of opinion that Newton excelled it in giving brilliancy to pictures, in preserving them better, and in rendering the colors more Roman 50,818. Lamazzo, a Milanese, says nothing on the subject of vehicles in his principal work, but in his Idea del Tempio della Pittura, he speaks of grinding the colors in noodle and spicle, and other things. The and here evidently means or and by other things. We are perhaps to understand other oils. Poppy oil, drying oils, Roman 100. The directions of Raphael Borghini and Vasari cannot certainly be considered conclusive as to the practice of the Venetians, but they are very clear on the subject of varnish. These writers may be considered the earliest Italian authorities who have entered much into practical methods. In the few observations on the subject of vehicles in Leonardo da Vinci's treatise, there is nothing, as Roman 1000 Marami observes, to show that he was in the habit of mixing varnish with his colors. Sennini says but little on the subject. Pg 404 of Olpainting. Leon Battista Alberti is theoretical rather than practical, and the published extracts of Lorenzo Ghiberti's MS chiefly relate to sculpture. Borghini and Vasari agree in recommending noodle in preference to linseed oil. Both recommend adding varnish to the colors in painting on walls in oil, because the work does not then require to be varnished afterwards. But in the ordinary modes of painting on panel or cloth, the varnish is omitted. Borghini expressly says that oil alone, senza più, is to be employed. He also recommends a very sparing use of it. The treatise of Armanini 1587 was published at Ravenna, and he himself was a Faenza, so that his authority again cannot be considered decisive as to the Venetian practice. After all, he recommends the addition of common varnish only for the ground or preparation, as a consolidating medium for the glazing colors, and for those dark pigments which are slow in drying. Many of his directions are copied from the writers last named. The recipes for varnishes in particular are to be found in Borghini. Cristoforo, sort 1580, briefly alludes to the subject in question. After speaking of the methods of distemper, he observes that the same colors may be used in oil, except that instead of mixing them with size, they are mixed on the palette with noodle, or if slow in drying with boiled linseed oil. He does not mention varnish. The Italian writers next in order are earlier than Vasari, and may therefore be considered original, but they are all very concise. Pg 405. The treatise of Michelangelo Biondo 1549, remarkable for its historical mistakes, is not without interest in other respects. The list of colors he gives is in all probability a catalogue of those in general use in Venice at the period he wrote. With regard to the vehicle, he merely mentions oil and size as the mediums for the two distinct methods of oil painting and distemper, and does not speak of varnish. The passages in the Dialogue of Doni 1549, which relate to the subject in question, are to the same effect in coloring in oil. He observes the most brilliant colors that we see in pictures are prepared by merely mixing them with the end of a knife on the palette. Speaking of the perishable nature of works in oil painting, as compared with sculpture, he says that the plaster of Paris gesso and mastic with other ingredients, of which the ground is prepared, are liable to decay. Roman 100 and elsewhere, in comparing painting in general with mosaic, that in the former the colors must of necessity be mixed with various things, such as oils, gums, white or yolk of egg, and juice of figs, all which tend to impair the beauty of the tints. This catalogue of vehicles is derived from all kinds of painting to enforce the argument, and is by no means to be understood as belonging to one and the same method. An interesting little work still in the form of a dialogue. Fabio and Lauro appeared a year earlier. The author Paolo Pino was a Venetian painter. In speaking of the practical methods, Fabio observes as usual that oil painting is of all modes of imitation the most perfect, but his reasons for this opinion seem to have a reference to the Venetian pg 406 practice of going over the work. Repeatedly Lauro asks whether it is not possible to paint in oil on the dry wall, as Sebastian del Piombo Roman 999. Fabio answers the work cannot last, for the solidity of the plaster is impenetrable, and the colors, whether in oil or distemper, cannot pass the surface. This might seem to warrant the inference that absorbent grounds were prepared for oil painting, but there are proofs enough that resins as well as oil were used with the gesso to make the preparation compact. See Doni Armanini Roman 100. This writer again does not speak of varnish. These appear to be the chief Venetian and Italian authorities of the 16th and part of the following century, and although Boschini wrote latest, he appears to have had his information from good sources, and more than once distinctly quotes Palma Giovane. In all these instances, it will be seen that there is no allusion to the immixture of varnishes with the solid colors, except in painting on walls in oil, and that the processes of distemper and oil are always considered as separate arts. 26 pg 407. On the other hand, the prohibition of Boschini cannot be understood to be universal, for it is quite certain that the Venetians varnished their pictures when done after Titian had finished his whole-length portrait of Pope Paul Roman III. It was placed in the sun to be varnished again, in the archives of the Church of S. Niccolò at Treviso. A sum is noted, Sep 21, 1521, per far la vernized un vernissar la palla del altar grando. And the same day a second entry appears of a payment to a painter per esser venuto a dar la verniz alla palla Roman 10,029. It is to be observed that in both these cases the pictures were varnished. As soon as done, the varnish employed was perhaps the thin compound of naphtha aglio di sasso and melted turpentine aglio d'Abso described by Borghini, and after him by Armanini. The last-named writer remarks that he had seen pg 408 this varnish used by the best painters in Lombardy, and had heard that it was preferred by Correggio. The consequence of this immediate varnishing may have been that the warm resinous liquid, whatever it was, became united with the colors, and thus at a future time the pigment may have acquired a consistency capable of resisting the ordinary solvents. Not only was the surface of the picture required to be warm, but the varnish was applied soon after it was taken from the fire. Many of the treatises above quoted contain directions for making the colors dry. Some of these recipes, and many in addition, are to be found in Palomino, who, however defective as an historian, has left very copious practical details, evidently of ancient date. His drying recipes are numerous, and although sugar of lead does not appear, Cardinillo verdigris, which is perhaps as objectionable, is admitted to be the best of all dryers. It may excite some surprise that the Spanish painters should have bestowed so much attention on this subject in a climate like theirs, but the rapidity of their execution must have often required such an assistance. One circumstance alluded to by Palomino in his very minute practical directions deserves to be mentioned. After pg 409, saying what colors should be preserved in their saucers under water, and what colors should be merely covered with oiled paper, because the water injures them, he proceeds to communicate a curious mode of preserving oil colors, and of transporting them from place to place. The important secret is to tie them in bladders, the mode of doing which he enters into with great minuteness, as if the invention was recent. It is true Cristoforo Sort, in describing his practice in watercolor drawing, says he was in the habit of preserving a certain vegetable green with gum water in a bladder. But as the method was obviously new to Palomino, there seems sufficient reason to believe that oil colors, when once ground, had up to his time been kept in saucers, and preserved under water among the items of expense in the Treviso document. Before, alluded to, we find a pan and saucers for the painters. This is in accordance with Cennini's directions, and the same system appears to have been followed till after 170,037. The Flemish accounts of the early practice of oilpainting are all later than Vasari van Mander, in correcting the Italian historian in his dates, still follows his narrative in other respects verbatim. If Vasari's story is to be accepted as true, it might be inferred that the Flemish secret consisted in an oil varnish like Copel. Vasari says that Van Pg 410 Eyck boiled the oils with other ingredients, that the colors, when mixed with this kind of oil, had a very firm consistence, that the surface of the pictures so executed had a luster, so that they needed no varnish when done, and that the colors were in no danger from water. Certain colors, as is well known if mixed with oil alone, may be washed off after a considerable time. Leonardo da Vinci remarks that verdigris may be thus removed. Carmine Palomino observes, may be washed off after 6 years. It is on this account the Italian writers recommend the use of varnish with certain colors, and it appears the Venetians, and perhaps the Italians, generally employed it solely in such cases, but it is somewhat extraordinary that Vasari should teach a mode of painting in oil so different in its results, inasmuch as the work thus required varnish at last from the Flemish method, which he so much extols, a method which he says the Italians long endeavored to find out in vain. If they knew it, it is evident, assuming his account to be correct, that they did not practice it. Odici stras si fan cavedal. Dojo davzo mastasai I sendraka. I trementina per nadir triaka. Robe chi illustrave ogni stivalp 338. The alliteration of the words trementina and triaka is of course lost in a translation. Note Wpar 608. In the second volume, Goethe gives the nomenclature of the Greeks and Romans at some length. The general notions of the ancients with regard to colors are thus described. The ancients derive all colors from white and black, from light and darkness. They say all colors are between white and black, and are mixed out of these. We must not, however, suppose that they understand by this mere atomic mixture, although they occasionally use the word one for in the remarkable passages where they wish to express a kind of reciprocal dynamic action of the two contrasting principles. They employ the words union, combination, thus again the mutual influence of light and darkness, and of colors among each. Pg 411 other is described by the word, an expression of similar import. The varieties of colors are differently enumerated, some mention 7, others 12, but without giving the complete list. From a consideration of the terminology, both of the Greeks and Romans, it appears that they sometimes employed general for specific terms and vice versa. Their denominations of colors are not permanently and precisely defined, but mutable and fluctuating, for they are employed even with regard to similar colors, both on the plus and minus side. Their yellow on the one hand inclines to red, on the other to blue. The blue is sometimes green, sometimes red. The red is at one time yellow, at another blue. Pure red. Purpur fluctuates between warm red and blue, sometimes inclining to scarlet, sometimes to violet. Thus the ancients not only seem to have looked upon color as a mutable and fleeting quality, but appear to have had a presentiment of the physical and chemical effects of augmentation and reaction. In speaking of colors, they make use of expressions which indicate this knowledge. They make yellow redden, because its augmentation tends to red. They make red become yellow, for it often returns thus to its origin. The hues thus specified undergo new modifications. The colors arrested at a given point are attenuated by a stronger light, darkened by a shadow, nay deepened and condensed in themselves. For the gradations, which thus arise, the name of the species only is often given, but the more generic terms are also employed. Every color of whatever kind can, according to the same view, be multiplied into itself, condensed, enriched, and will in consequence appear more or less dark. The ancients called color in this state Roman 100. Then follow the designations of general states of color and those of specific hues. Another essay on the notions of the ancients, respecting Pg 412, the origin and nature of color, generally shows how nearly Goethe himself has followed in the same track, the dilating effect of light. Objects, the action and reaction of the retina, the colored afterimage, the general law of contrast, the effect of semi-transparent mediums in producing warm or cold colors, as they are interposed before a dark or light background. All this is either distinctly expressed or hinted at, But continues Goethe, how a single element divides itself into two remained a secret for them. They knew the nature of the magnet in amber, only as attraction polarity was not yet distinctly evident to them. And in very modern times, have we not found that scientific men have still given their almost exclusive attention to attraction, and considered the immediately excited repulsion only as a mere afteraction? An essay on the painting of the ancients, too, was contributed by Heinrich Mayer. Note Roman 10 par 670. This agrees with the general recommendation, so often given by high authorities in art, to avoid a tinted look in the color of flesh. The great example of Rubens, whose practice was sometimes an exception to this, may however show that no rule of art is to be blindly or exclusively adhered to. Reynolds, nevertheless, in the midst of his admiration for this great painter, considered the example dangerous, and more than once expresses himself to this effect, observing on one occasion that Rubens, like Baroccio, is sometimes open to the criticism made on an ancient painter, namely that his figures looked as if they fed on roses. Ludovico Dolce, who is supposed to have given the viva voce precepts of Titian in his dialogue, 1, makes Aretino pg 413, say, "I would generally banish from my pictures those vermilion cheeks with coral lips for faces thus treated look like masks," Propertius reproving his Cynthia for using cosmetics desires, that her complexion might exhibit the simplicity and purity of color, which is seen in the works of Apelles. Those who have written on the practice of painting have always recommended the use of few colors for flesh. Reynolds, and others quote even ancient authorities, as recorded by Pliny and Boschini, gives several descriptions of the method of the Venetians, and particularly of Titian, to the same effect. They used, he says, earths more than any other color, and at the utmost only added a little vermilion minium, and like abhorring as a pestilence Biodetti Giali Santi Smaltini Verdiazzeri Giallini. 2 elsewhere, he says 3 earths should be used rather than other colors. After repeating the above prohibited list, he adds, "I speak of the imitation of flesh, for in other things every color is good." Again, our great Titian used to say that he who wishes to be a painter should be acquainted with 3 colors, white, black, and red. 4, assuming this pg 414 account to be a little exaggerated, it is still to be observed that the monotony to which the use of few colors would seem to tend is prevented by the nature of the Venetian process, which was sufficiently conformable to Goethe's doctrine, the gradations being multiplied, and the effect of the colors heightened by using them as semi-opaque mediums. Immediately after the passage last quoted, we read, "He also gave this true precept, that to produce a lively coloring in flesh, it is not possible to finish at once 5, as these particulars may not be known to all. We add some further abridged extracts, explaining the order and methods of these different operations. The Venetian painters, says this writer, 6, after having drawn in their subject, got in the masses, with very solid color, without making use of nature or statues. Their great object in this stage of their work was to distinguish the advancing and retiring portions, that the figures might be relieved by means of chiaroscuro of the most important departments of color and form, and indeed of invention. Having decided on their scheme of effect when this preparation was dry, they consulted nature and the antique not servilely, but with the aid of a few lines on paper quattrosegni in carta, they corrected their figures without any other model. Then returning to their brushes, they began to paint smartly on this preparation, producing the color of flesh. The passage before quoted follows, stating that they used earths chiefly, that they carefully avoided certain colors and likewise varnishes, and whatever produces a shining surface. 7, when this second painting was dry, they proceeded to scumble over this or that figure with a low tint, to make the one next it come forward, giving another at the same time an additional light, for example pg 415, on a head, a hand, or a foot, thus detaching them, so to speak, from the canvas. Tintoret's Prigenia di S. Rocco is here quoted by thus still multiplying these well-understood retouchings were required on the dry surface. A secco, they reduced the whole to harmony. In this operation, they took care not to cover entire figures, but rather went on gemming them giolindole with vigorous touches. In the shadows too, they infused vigor frequently by glazing with asphaltum, always leaving great masses in middle tint with many darks, in addition to the partial glazings and few lights. The introduction to the subject of Venetian coloring in the poem by the same author is also worth transcribing, but as the style is quaint and very concise, a translation is necessarily a paraphrase. 8. The art of coloring has the imitation of qualities for its object, not all qualities, but those secondary ones which are appreciable by the sense of sight. The eye, especially sees colors the imitation of nature in painting, is therefore justly called coloring, but the painter arrives at his end by indirect means. He gives the varieties of tone in masses 9 pg 416. He smartly impinges, lights, he clothes his preparation with more delicate local hues, he unites, he glazes. Thus everything depends on the method, on the process. For if we look at color abstractedly, the most positive may be called the most beautiful. But if we keep the end of imitation in view, this shallow conclusion falls to the ground. The refined Venetian manner is very different from mere direct sedulous imitation. Everyone who has a good eye may arrive at such results. But to attain the manner of Paolo of Bassan, of Palma Tintoret, or Titian is a very different undertaking. The effects of semi-transparent mediums in some natural productions seem alluded to in the following passage. Nature sometimes accidentally imitates figures in stones and other substances, and although they are necessarily incomplete in form, yet the principle of effect depth resembles the Venetian practice. In a passage that follows there appears to be an allusion to the production of the atmospheric colors by semi-transparent mediums. Importa el nudo, ecum ben l'importa. Un quadro sentinudo ecum apont. Un disnar senza pan si ben gisant. Per pudilitia confecera, e tortap 346. In his preface he anticipates, and thus answers the objections to his Venetian, dialect me chi son Venetian, in Venetia e chi parlo de pittori venetiani, ho de andarm, a stravester garda el cielo. Malerivar e la maniera al trot. Verbi gratia de Paulo del Bassan. Del vecchio tentorido editition. Per dio la cosa de deventer matop, 294-297. Note Wipar 672. The author's conclusion here is unsatisfactory, for the color of the black races may be considered at least quite as negative as that of Europeans. It would be safer to say that the white skin is more beautiful than the black, because it is more capable of indications of life and indications of emotion, a degree of light which would fail to exhibit the finer varieties of form on a dark surface would be sufficient to display them on a light one, and the delicate mantlings, pg 417 of color, whether the result of action or emotion, are more perceptible for the same reason. Note Zipar 690. The author appears to mean that a degree of brightness which the organ can bear at all must of necessity be removed from dazzling white light. The slightest tinge of color to this brightness implies that it is seen through a medium, and thus in painting, the lightest whitest surface should partake of the quality of depth. Goethe's view here again accords, it must be admitted, with the practice of the best colorists, and with the precepts of the highest authorities. See note Roman 100. Note Par 732. Ample details respecting the opinions of Louis Bertrand Castel, a Jesuit, are given in the historical part. The coincidence of some of his views with those of Goethe is often apparent. He objects, for instance, to the arbitrary selection of the Newtonian spectrum, observing that the colors change with every change of distance between the prism and the recipient surface. Farbinal, Vol. Roman 2 p. 527. Jeremias Friedrich Gillick was a dyer in the neighborhood of Stuttgart. He published an elaborate work on the technical details of his own pursuit. Farbinal, Vol. Roman 2 p. 630. Note BB Par 748. Goethe, in his account of Castel, suppresses the learned Jesuit's attempt at colorific music. The Clavecin oculaire, founded on the Newtonian doctrine. Castel was complimented, perhaps ironically, on having been the first to remark that there were but three principal colors. In asserting his claim to the discovery, he admits that there is nothing new. In fact, the notion of three colors is to be found in Aristotle, for that philosopher enumerates no pg 418 more in speaking of the rainbow one, and Seneca calls them by their right names. To compare with Dante Parod Roman 100, the relation between colors and sounds is in like manner adverted to by Aristotle. He says it is possible that colors may stand in relation to each other in the same manner as concords in music, for the colors, which are to each other in proportions corresponding with the musical concords, are those which appear to be the most agreeable. 3. In the latter part of the 16th century, Arcimboldo, a Milanese painter, invented a colorific music. An account of his principles and method will be found in a treatise on painting, which appeared about the same time. Amaistrato dal quai ordine monocremones, Dalla viola musico dell'imperatore Rodolfo, Roman tu trovo sul gravissimo tut quel consonans, chi dal ar simboldo irano segnate coi colori sopra una carta 4. Note Roman 200 par 758. The moral associations of colors have always been a more favorite subject with poets than with painters. This is to be traced to the materials and means of description as distinguished from those of representation. An image is more distinct for the mind when it is compared with something that resembles it. An object is more distinct for the eye when it is compared with something that differs from it. Association is the auxiliary in the one case, contrast in the pg 419. The poet of necessity succeeds best in conveying the impression of external things by the aid of analogous, rather than of opposite qualities. So far from losing their effect by this means, the images gain in distinctness. Comparisons that are utterly false and groundless never strike us as such if the great end is accomplished of placing the thing described more vividly before the imagination in the common language of laudatory description. The color of flesh is like snow mixed with vermilion. These are the words used by Aretino in one of his letters, in speaking of a figure of St. John, by Titian. Similar instances without end might be quoted from poets. Even a contrast can only be strongly conveyed in description by another contrast that resembles it. On the other hand, it would be easy to show that whenever poets have attempted the painter's method of direct contrast, the image has failed to be striking for the mind's eye cannot see the relation between two colors. Under the same category of effect produced by association may be classed the moral qualities in which poets have judiciously taken refuge when describing visible forms and colors, to avoid competition with the painter's elements, or rather to attain their end more completely. But a little examination would show that very pleasing moral associations may be connected with colors, which would be far from agreeable to the eye. All light positive colors, light green, light purple, white, are pleasing to the mind's eye, and no degree of dazzling splendor is offensive the moment. However, we have to do with the actual sense of vision. The susceptibility of the eye itself is to be considered. The law of comparison is reversed. Colors become striking by being opposed to what they are not, and their moral associations are not owing to the colors themselves, pg 420, but to the modifications such colors undergo in consequence of what surrounds them. This view, so naturally consequent on the principles the author has himself arrived at, appears to be overlooked in the chapter under consideration, the remarks in which in other respects are acute and ingenious. Her beauty hangs upon the cheek of night, like a rich jewel in an Ethiop's ear. Romeo and Juliet. Note Roman 1000 par 849. According to the usual acceptation of the term chiaroscuro in the artist world, it means not only the mutable effects produced by light and shade, but also the permanent differences in brightness and darkness, which are owing to the varieties of local color. Note E par 855. The mannered treatment of light and shade here alluded to by the author is very seldom to be met with in the works of the colorists. The taste may have first arisen from the use of plaster casts, and was most prevalent in France and Italy in the early part of the last century. Piazzetta represented it in Venice. Subliras in Rome and France. Ristout taught his pupils that a globe ought to be represented as a polyhedron. Greuze most implicitly adopted the doctrine, and in practice showed that he considered the round cheeks of a young girl or an infant as bodies cut into fastes. 1. Note ff par 859. All this was no doubt suggested by Heinrich Mayer, whose chief occupation in Rome at one time was making pg 421 sepia drawings from sculpture. See Goethe's Italienisch. Rise. It is hardly necessary to say that the observation respecting the treatment of the surface in the antique statues is very fanciful. Note GG par 863. This observation might have been suggested by the drawings of Claude, which with the slightest means exhibit an harmonious balance of warm and cold. Note HH par 865. The coloring of Paolo Uccello, according to Vasari's account of him, was occasionally so remarkable that he might perhaps have been fairly included among the instances of defective vision given by the author. His skill in perspective, indicating an eye for gradation, may be also reckoned among the points of resemblance. See par 105. Note Roman 2 par 902. The quotation before given from Boschini shows that the method described by the author and which is true with regard to some of the Florentine painters, was not practiced by the Venetians, for their first painting was very solid. It agrees, however, with the manner of Rubens, many of whose works sufficiently corroborate the account of his process. Given by Descamps in the early state of Rubens' pictures, says that writer 1 everything appeared like a thin wash, but although he often made use of the ground in producing his tones, the canvas was entirely covered, more or less, with color, in this system of leaving the shadows transparent from the first, with the ground shining through them. It would have been obviously destructive of richness to use white mixed with the darks. The brightness, in fact, already existed underneath. Hence the pg 422 well-known precept of Rubens, to avoid white in the shadows, a precept like many others, belonging to a particular practice, and involving all the conditions of that practice too. Scarmigliani, whose Aristotelian treatise on color was published in Germany when Rubens was 23, observes painters with consummate art lock up the bright colors with dark ones, and on the other hand, employ white the poison of a picture very sparingly. Artificiosissime pictures, claros obscuris obsepiant et contra candido picturarum venina. Some parcents, Roman 100. Note KK par 903. The practice here alluded to is more frequently observable in slight works by Paul Veronese. His ground was often pure white, and in some of his works, it is left as such. Titian's white ground was covered with a light warm color, probably at first, and appears to have been similar to that to which Armanini gives the preference, namely quella ci tira al color di carne chirissima, con un non so ci di fiammeggiant. 1. pg 423. Note Roman 100 par 919. The notion which the author has here ventured to express may have been suggested by the remarkable passage in the last canto of Dante's Paradise. Nella profonda e chiara sussistenza del alto lume parametri giri di tre colori e d'una continenza. Roman 100. After the concluding paragraph, the author inserts a letter from a landscape painter, Philip Otto Runge, which is intended to show that those who imitate nature may arrive at principles analogous to those of the Farben layer.